Hi everyone and welcome back to PrepFusion. So today in this video we will totally cover linear algebra in a marathon. Okay, this will be a one shot of linear algebra. This series is called as the R-PYQ series, where we do revision with PYQ. We just don't solve PYQs. Of course, we'll solve PYQs, which will be new actually, which will be different PYQs. We will do revision of every single topic. So every single topic from matrices, determinants, types of matrices, solution of linear equations, what are the different formats, rank, eigenvectors, eigenvalues, vector space. And then at the end, we will solve GATE PYQs of ECEE, IN, CSIT. Okay, because these four branches are the most important ones which can have similar questions. That's why I have taken these four branches, and we will solve the latest PYQs from 2020 onwards. So I will not skip any concept. I will try to take all whatever I have taught in my full course. It is around 25 hours. I don't remember actually, 20 to 25 hours. In this whole single video, I will try to cover it. Now, of course, you will say, will this video be enough? My simple answer is nothing is enough, right? But of course, I'm compressing my topic, right? I'm compressing my hours to this small amount. I cannot totally promise you that you will be able to solve all questions, but that what I can guarantee is I have covered every single topic. It's not like I have skipped. So I have even covered vector spaces, right? Even though it does not get asked that much in ECEE, but still I have covered that. I have tried to cover every single topic so that even if you have studied a bit in your college or somewhere, right, still you can watch this video and you can go ahead. If you don't have much time left right now, and if you want to say, sir, I don't have time to study linear algebra completely, I just want to watch this video, will this be enough? Of course, nothing will be enough, but of course, if you watch this video, I can assure you at least 80% of the questions you will be able to solve. 80% of the questions you will be able to solve, because in GATE, 80% of the questions are easy, right? 20% question is difficult. So 80% of the questions you will be able to solve. Of course, 20% of the question you might need to practice more, right? Concept I will teach you, but you need more practice. For that, obviously, assignment videos, all those things are there, right? All those things are already there, so you can watch those videos. Okay, so yeah, if you are enjoying this series, so that's only my request. Like this video, and if you are enjoying some concept, maybe you have studied from somewhere else, now you are studying from here, you are learning something new. If you learn something new, please tell us in the comments below how you are enjoying this series. If you put this series, like if you give more likes and comments, right, then I will obviously upload the next chapters like calculus and all those things. If you don't support this series enough, then I have to stop this, right? So it's totally up to you how much you support this series. And trust me, after you watch this video, even if you don't have, even if you have not studied for GATE, if you have studied bit of, about linear algebra in college or in school, right, still if you watch this video, you will be able to solve 80% of the question. That's my guarantee. Don't worry. I have not skipped any topic. You need to practice more questions. For practice, already resources are mentioned in the starting of this playlist, right, of the R-PYQ series. So let's start with the first topic, that is matrices. Let's begin with linear algebra. So first of all, let us discuss what is linear algebra. A linear equation, like first, okay, sorry, before linear algebra, like what is a linear equation? So linear algebra is combination of two terms, linear and algebra. So we will do algebra on linear equations. Okay, so before understanding linear algebra, we need to understand what is linear equation. So a linear equation is an equation in which highest power of the variable is always 1. Let me take few examples like this, right? Ax plus by equal to c, where a, b, c all are constant, only x and y are variable. So the power of all the variables, variable meaning the terms which are varying, okay, should always be 1. Here you see the power is 1, right? I will show you a few more examples as well. It is also known as a 1 degree equation because the degree is known as the power. Degree of all the variables is 1. The graph of a linear equation always forms a straight line. Okay, the graph of a linear equation will always form a straight line. We will plot the graphs, we will see. Okay, this is the reason why it is called linear equation. So we will plot the graph of this equation, right, and we will identify whether this is a linear equation or not. So this is very simple. Like out of these four, tell me which are linear equation. A, B, C, D. Very easy to understand. Here the power of x is 1, power of y is 1. So of course A will be a linear equation. Let me change the pen color. A will be a linear equation. Okay, what about what about this under root y plus x equals to 6? Is this a linear equation? No, because the power of x, even though it is 1, but what is the power of y? Power of y is 1 by 2. So of course it will not be a linear equation. What about the third one? Again, in the third option C, the power of y is 1 but power of x is 2. So this also will not be a linear equation. In the fourth and final equation, power of y is 1, power of x is 1. So of course this will be a linear equation. So let us plot this, right, in the graph. So if I plot the first function x minus 3y, so like I'm not telling you how to plot. I hope you know how to plot. So if I plot, it will come out as a linear line, straight line. So that's why it is called linear. Okay, whenever you will plot a graphical like whenever you will plot a linear equation in graph, it will always come out to be a straight line, linear. Okay, here also you see this was not a linear equation, so my graph was not coming straight line. Here also my equation was not linear, that's why graph also was not coming straight line. Here the equation was linear and the graph also was coming out to be straight line. Okay, so yeah, now these are my three linear equations. Now I want to solve my linear equation. Solve, right? Let's say I have these equations, right? This first equation, this I have two equations simultaneous. These are called simultaneous linear equations. Why simultaneous? Because simultaneously I have two equations. That's why these are called simultaneous linear equation. Linear because they are linear. Okay, so I have A, B, C, three simultaneous linear equations of two variables, right? And I need to solve for x and y. What do I mean by solve for x and y? For what values of x and y this simultaneous equation will satisfy? So it will come out to be a unique value. It can be a unique value in class class 9th or 8th. I think you remember that you used to solve for this, right? You used to find the value of x and value of y out of these two equations. I hope something is coming out in your memory. But there is a caveat here. It is not always that you will get a unique solution, that is a single solution. There can be infinite number of solutions. There can be no solution as well. What do I mean? Let me explain. So let us solve the first one. So I have already solved it using elimination. So I am not telling you how to solve using elimination. I hope you know how to solve using elimination. So once I will solve using elimination, the value of x will come out to be 1. And if the value of x is 1, right, I will put x equals to 1 here. The value of y will come out to be minus 1. So x equals to 1 and y equals to minus 1, right, is a solution for this equation. Okay, x equals to 1 and y equals to minus 1. So you can solve, right? I hope you can solve using elimination. But graphically, what does it mean? Graphically, if I plot that both the linear equation, this is the equation 1, this is the equation 1. Graphically, it means where does my equations intersect? Where does my lines intersect with each other? Okay, where does my lines intersect with each other? So I see my lines intersect with each other here. My lines intersect with each other at this particular point. What is the point? Which we have already solved. Graphically also you will get the same point, that is 1 comma minus 1. Graphically also you will get the same point, that is 1 comma minus 1. Okay. Now let's come to the second one actually. For the second one, if I solve using method of elimination, you will see something peculiar happening. Once you will try to solve the value of x, right, you will see you are not able to solve for x. You are getting an equation like 0 equal to 0 by elimination method. But 0 equal to 0 is always true, right? 0 equal to 0 is always true. That basically means I can put any value of x, right? It will always satisfy. For any value of x, the equation will always satisfy. Both these equations will always satisfy. How is it possible? It is possible because these two equations are nothing but the same. If I divide by 2 here, right, I will get my previous equation. So actually, you have been only given one equation. You only have been given one equation. Here, because there were two unknowns, for solving two unknowns, you need two equations, right? And these two equations were unique, so your solution was also unique. But here, actually what is happening, this is the same equation only, because if I divide by minus 2, I will get back my first equation. So the thing is that it is actually a single equation. So with a single equation, can you find values of two variables, unknown variables? No. So there are actually infinite solution. Why? Because I can choose a value of x. Let's say x equal to 1. For x equal to 1, I will get some y value. For x equal to 2, I will get some y value. So there are infinite values. So it is called as they have infinite solutions. Infinite solutions. Okay. What does it mean graphically? Graphically basically means both the lines will intersect with each other. You can go in matplot, okay, matplotlib, or like any in Desmos in a browser, okay, and try to plot these two equations. You will see both the equations are overlapping with each other because they are intersecting. Like at every point they are intersecting. So that's why there are infinite solutions. Let's come to the third one. Okay, here. Now with the third one, if I try to solve, right, you will get an equation. Whenever you will try elimination method, you will get an equation like 0 equals to minus 6. Now 0 equal to minus 6, what does it mean basically? It basically means it is never true. Is it ever true? No. 0 is never equals to minus 6. 0 is never equals to minus 6, right? So it is never true. Now if it is never true, what does it mean? That basically means there doesn't exist a solution, right? Here 0 was equals to 0, which is always true, right? 0 was equals to 0, which was always true. But here as 0 is equals to minus 6, so it is never true. So no solutions exist. No solutions exist. Okay. So how like why no solution exists? Because you see this, right, is just the negative. So if I multiply minus 1 here, I will get this equation, but the constant term is different. Basically it means the graphs are parallel, they are never overlapping. Like there is no intersection. So if I plot the lines, the lines are parallel to each other. There is no intersection at all. Basically the slopes are same for both of the graphs and they are parallel. So there is no intersection. So that basically means there is no solution, because we'll get a solution whenever there is an intersection. So the conclusion is, if I have, we discussed for two linear equations. If I have n linear equations, I will need, first thing is, if I have n variables, n unknown variables, right? If I have n unknown variables, to solve n unknown variables, first of all, you will need n linear equations. That is the minimum to get a unique solution. This condition must be met. Let's say there are three unknown variables x, y, z, and you have only two equations, two simultaneous linear equations in terms of x and y and z, equation 1 and 2. Will you be able to find a solution? No. Simple answer is no, you will not be able to find a solution. Okay, you will not be able to find a unique solution. Okay, infinite solution is a possibility. Okay, if both the lines are overlapping with each other. Okay, and no solution is also a possibility if both the lines are parallel to each other. But unique solution is definitely not possible. Okay, because you will need three equations to get a unique solution, right? Okay, now if I have, let's say, n linear equations, right? Now there are few terms: consistent set of equations and inconsistent set of equations. So whenever there is no solution, right, then it is called inconsistent set of equations. So the equations that were given to you, right, this last one, option C, these are my inconsistent set of linear equations. These are not consistent. What does it mean? Basically with this equation, right, with this set of equations, I will get no solution. So that's why these are called inconsistent set of equation. Okay, when does it happen? When the lines are parallel with each other, basically when there is no intersection. Now if solution exists, right, whatever linear equation are given to you, then those equations are called as consistent set of equations. So here these equations are consistent set of equations because these are together. So that's why these are called consistent set of equations, and these two are actually these two also are called consistent set of equations. Okay, Yeah, and in inconsistent set of equations there are two options, right? There are two results. Two things can happen: either whatever solution you will get unique, so that means all the lines, all the equations will be intersecting at a single point only, or you will get infinite number of solutions. That means the lines are overlapping with each other. The lines are overlapping with each other. Okay, so yeah, now one more term I want to explain as non-trivial and non-repeated. Okay, so non-trivial basically means uh, unique. Trivial means boring. Trivial means a boring solution, right? Trivial actually means zero solution. Zero is a solution. Trivial solution means zero is a solution. Okay, we will learn about this later on. For now I'm just explaining you that x equal to y equal to 0, like x equal to y equal to, and whatever number of unknown variables I have, all equal to 0 is a solution. Trivial solution meaning x equal to y equal to 0 is a solution. Okay, and non-trivial means like x equal to y equal to z equal to whatever are the unknown variables, they are not equal to 0, they are non-repeated, they are unique. Whenever if in any question they say you non-trivial, that means the solutions are unique. Okay, this is just a term, English term. Now let's come to matrix representation, because in linear algebra what do we see? We see matrix. But actually linear algebra is study of solution of equations. Linear algebra is study of solution of equations. But to solve these equations, we will not solve using elimination like this, right? These things we will not do. This is much easier for smaller number of equations, right? Doing elimination and stuff. Like you can do it till when the number of equations, unknown variables are 3. Beyond 3, right, it becomes a bit difficult. So we have a representation known as matrix representation. Okay, so in matrix representation, let's say I have these set of linear equations. What I can do, I can write the coefficients of the matrix, coefficients of the variables in a matrix format. Okay, it becomes much easier, and we will use this everywhere else. Okay, so this, right, coefficient of x is 1, coefficient of y is -3, coefficient of x is 3, coefficient of y is 1. Then I write this column matrix. Column, why is it called column? Because it is in a column. Okay, that's why it is called a column matrix. So this is called as a variable matrix. This can also be called as a variable matrix, and this can be called as a coefficient matrix. This matrix contains the information about the all the coefficients of the set of linear equations. Okay, this will be equals to my constant matrix, that is 4 comma 2. So how can I come back from this matrix format to this one? So what you can do, you can simply, like, this is a matrix multiplication. Don't worry, we will discuss about matrix multiplication later on as well. So in matrix multiplication, what do? You multiply the row with a column, and then you equate with the row of the right hand side. So what is the row of the left hand side? So this is a 2 cross 2 matrix, right? Why 2 cross 2? Because I have 2 rows. So this represents the number of rows of the matrix, and this represents the number of columns. So we have a 2 cross 2 matrix. Okay, 2 cross 2 matrix, and here we have a 2 cross 1 matrix, because how many number of rows I have? 2. How many number of columns I have? 1. I have only a single column, right? And I have 2 rows. Okay, so this will be yeah, so here, right, if I cross multiply the row and column, this will, first of all I will multiply the first row and the first column, first element in the column and the row. So this will be 1 cross x. Then I will write plus sign, okay, because we always add. Then I will multiply the second element in the row and the second element in the column. So minus 3 into y. So this is actually my first row, first element of the first row. Okay, because the what will be the resultant of this multiplication? The resultant is always the number of rows of the this matrix and the number of columns of the other matrix, because whatever is at the starting it will contain the number of rows, and whatever is at the ending, it will contain the number of columns. And don't worry, I will discuss about matrix multiplication later on as we move along. For now, just take my word. Okay, so this will be 1 cross x plus 3 cross y will be equals to the row here, that is 4. Okay, now similarly I can, now once the first row is done, I can move on to the next row. Next row, first element into the first element of the column, so 3 cross x, okay, plus a second element of the row into second element of the column, so 1 cross y. Okay, 1 cross y will be equals to the second element of the row of the right hand side, that is 2. So that's how you will come back, you will see that we are actually getting our same equation. Similarly, we can use a row matrix representation. Generally we use column matrix because it is easier for us to print on the paper. That's why we use column matrix. But we can use row matrix as well, because this column matrix will take less space, because generally our paper is portrait, right? That's why we use row matrix, sorry, column matrix. But we can use row matrix. Why is it called row matrix? Because it's a single row, that's why. But when just be careful, if you are using the row representation, that means you have to write the row matrix first. The coefficient matrix, if you observe, has not changed. Just the, like this column matrix has become row matrix. Just be careful regarding that. Okay, sorry, coefficient matrix also has changed. How has it changed? So simply there is a thing, I will come to that, right? If I have a matrix A cross B, right? If I take the whole transpose of this, I will get back this matrix. So if I take like A cross B equal to C, this is my equation, A cross B equals to C, and I have not explained you what is a transpose. So for the students who don't understand transpose, we will understand it later on, don't worry. For the students who know, if I take the whole transpose of this matrix, right, on both sides obviously, then this will become what? This will be B transpose into A transpose, B transpose into A transpose into C transpose. So you see the transpose of this is 4 2, because I am interchanging the rows and columns. Don't worry if you don't know transpose, I will come to it later on. Okay, for the students who know, I am talking to them. Next, this B transpose actually moves at the starting, right? So this right will be transpose, it will become xy, but it will move at the starting, that's why it is at the starting. And again I have to obviously do A transpose. Okay, so if I do the A transpose, this will be 1 3 minus 3 1. Okay, that is my A transpose basically. Okay, that is clear, I hope. Yeah, so that was a short intro about matrix multiplication and how to represent matrix. So matrix, what is the size of the matrix? Size of the matrix basically is the total number of elements inside the matrix. It is always the number of elements in the rows into the number of elements in the column, that is basically number of rows into number of columns, so R into C. In this case, right, in this case it is 2 cross 2, that is 4. I have 4 elements in the matrix. Okay, so this is the definition of the matrix, you can read. Just it is a way to represent similar objects. Remember, these are all similar, right? These are all coefficients, these are all variables, these are all the constant terms on the right hand side. So you can only put things in a matrix when the objects are similar. You cannot arrange dissimilar items. Okay, you cannot keep gold, like some element made of gold and some element made of silver together in a matrix, because they are not similar in nature. So basically they have to be somewhat similar, then only I can arrange them in matrix format. Okay, so this kind of matrix, right, is called square matrix. Whenever my number of rows and number of columns are same, they are called as square matrix. Otherwise they are called rectangular matrix if the number of rows and number of columns are not same. So this is called as a rectangular matrix. Another name for this is column matrix, special matrix, because it consists only of a single column. And this is also a rectangular matrix, but it is also called as a row matrix because it consists of a single row. Okay, so any system of linear equation Ax plus b can be represented in a matrix format Ax plus b, where A will be the coefficient matrix, X will be the unknown vector. Okay, vector because sometimes a row matrix or column matrix is called as a vector, and the constant vector. Okay, so a system, now as we have discussed the conclusion, same thing is written over here. A system of equation is said to be consistent if it has at least one solution. At least it should have one solution, then the system, whatever the system of equation you are given, is consistent set of equation. So if it has infinite solution, then also it is consistent. If it has unique solution, then also it is consistent. Basically it needs to have at least one solution. When does it have only one solution? Unique solution. If it has more than one solution, that means we have infinite solutions. Okay, a system of equation is said to be inconsistent if it has no solution. Okay, that we have already discussed using the diagram, right? When there are more variables and equations, it is hard to do calculation by hand or graphically. In this situation, the system of equation is converted into matrix form, and the rank is determined to find out the nature of solution. Okay, so in this situation, the system of equation is converted into matrix form, and the rank is determined to find out the nature of the solution. So what we do is we convert our system of equations, right, into matrix format. Then there is a term known as rank. Okay, what is rank? I have not told you, so you don't know. We will see. So rank of the combined matrix and the individual coefficient matrix, we find it out. We compare the rank. Okay, we see the results, and then we conclude from the rank whether the set of linear equations is consistent or inconsistent, whether I have no solution, whether I have unique solution, whether I have infinite solution. Okay, so that is the reason we study, like this is the actual reason why we study linear algebra. So we use linear algebra to study how to solve linear system of equation. But to solve linear system of equation, it depends on the rank concept of rank, that we will discuss once we understand matrix. Okay, so to understand matrices better, we need to learn the fundamentals of determinant. Okay, so yeah, so we need to actually solve linear equations. To solve that, we need to understand what is a rank of a matrix. To understand rank of a matrix, there is another thing known as determinants. It is like a operation on matrices. So we need to understand that, then only we will be able to actually solve linear equation, understand linear equation. So now if you have enjoyed, right, if you have understood finally why we study linear algebra, put a like in the video and drop down a comment. Okay, so now let's come to determinant. What do I mean by determinant? So a determinant is nothing but just a simple scalar value. Sometimes for a 2 cross 2 matrix, the determinant represents the area. Okay, for a 3 cross 3 matrix, it represents a volume, but I am not going into that significance. I am just simply telling you determinant is just an operation on a matrix. Remember, it is only valid on a square matrix. Let's say I have a matrix here 1 2 3 4. Okay, so what is the determinant of this matrix? So I know you already know, like you have studied all these things. So the determinant of this matrix will be 1 into 4 minus 3 into 2. So that is 4 minus 6, that is minus 2. How do you represent? You represent by a 2 bars on the both sides of my E matrix, or in matrix format we represent it by 2 bars. Okay, so this is the answer. So it is just a scalar value. Okay, it is sometimes represented by 2 bars or determinant of A, det or delta. Anything is fine. So for a 2 cross 2 matrix, the simple formula is first I multiply the diagonal elements, then I multiply the off diagonal. So this side is called as the off diagonal, and then I subtract the off diagonal element from the main diagonal element. Okay, for a 3 cross 3 matrix, how can I solve? For a 3 cross 3 matrix, what we do is we break it down into smaller 2 cross 2 matrix. Okay, so let's say what we do is we open the determinant either through one column or row. For a 3 cross 3 matrix, will open the determinant either through one column or row. So I can actually show you an example, and through that we can understand. Okay, let me delete this. So let me take an example, A matrix. Okay, let me take a very basic example. 1 1 2 3, or let me take 1 0 0 0 2 0 and 0 0 3. So how will you find the determinant of this matrix? Just give me 1 second. Give me 1 second. How will you find the determinant of this matrix? So what you will do is you will open this matrix about a column or a row. Okay, about a column or a row. So this will be 1 2 into 3 minus 0 minus 0. Now, like I am opening about a row, first row, right? So first I will write that row, and then I will not use the elements of that particular row and column. As I'm using this element 1, so I will not use this row and this column and this row. Okay, I'll only use this. So I will solve the determinant of this smaller matrix. So that is what I'm doing basically, 2 into 3 minus 0. So I'm solving the determinant of this smaller matrix. Here also, then once this determinant is done, then you have to follow actually a sign. So sign is plus minus plus minus plus minus plus minus plus. So that's how you move. Okay, so you don't go like this, plus minus plus, then from here you start with minus. No, you start from here actually. Okay, you start with continuation. So I will start, if I'm going in this direction, right? So it will be plus minus plus, then minus, then plus minus plus minus plus. Okay, you can start with any direction. Let's say I'm starting with this direction. So plus minus plus minus plus minus plus minus plus. So you can do anything. Okay, but generally we follow this this rule, or you can follow this rule. Okay, that is the general rule. So this plus minus basically means the sign in front of the element. Here, for an example, let's say that this was negative. So the sign is plus, right? But this is already negative. So of course I will put the element here. And let's say if the element, let's say if this was 0, the element was here minus 1. Okay, then what will happen? Then first of all I will write this determinant. Now I will actually not solve this, because already I know the coefficient of this determinant is 0. So 0, like I will multiply 0, right? And anything multiplied by 0 is always 0. Anything multiplied by 0 is always 0. So this will be 0. This will be basically 0. Okay. Now I will write here minus because this sign is minus. Now after writing minus, again I will put the element. What is the element? Element is minus 1. So don't forget to put the minus 1 element. Then finally you write the matrix form. So if I am choosing this element, so I have to cancel out this particular column and this particular row. So only this and this are forming a matrix. So 0 into 3, 0 into 0. So this is forming a matrix, right? 0 0 0 3. So the matrix is 0 0 0 3, and determinant of this will be simply 0. Whenever you have a rows of 0 or column of 0, right, the determinant of that particular matrix will always be 0, because like you're again breaking it down. So here also you can do it, right? So this will be 0. Okay, then again plus 0 basically because this is 0. Okay, so that's how you solve a 3 cross 2 matrix. The same thing I've shown here, the sign convention and all. Okay, general method to solve a 3 cross 2 matrix. I know you already know this things, right? But still, as I'm covering every single thing, so I'm covering the basics as well. Okay, so as I have discussed, determinant will not exist for a non-square matrix. Determinant will only exist for a square matrix. For a n cross n determinant, the maximum number of terms will be n factorial. Okay, not that important, you can ignore this third statement. Okay. Okay, so there are few properties of determinant. So let's say if I'm making a matrix C that is a product of two matrices A and B. So what I can say, if I want to calculate the determinant of C, right, it will be the determinant of AB. So I can actually separate the determinants out. So if I individually know the determinant of A and individually know the determinant of B, so I can directly say what will be the determinant of C. These are properties. And inverse I have not discussed yet, but for the students who understand these things, so if let's say B is inverse of A, right, or what is the determinant of a inverse? What is the determinant of a inverse? The determinant of a inverse is simply inverse. Okay, so determinant of this, right, like let's say B is B is equals to A inverse, so the determinant of B will be A inverse. Okay, 1 by determinant of A, that is what my determinant of B would be equals to. Okay, so I hope that part is clear. So few more properties are there. If two rows or two columns of a determinant are interchanged, then the sign of determinant will change. What do I mean by it? Let's say I have a matrix, A11, A12, these are the elements. Okay, and here what I am doing, I have simply interchanged the two rows, right? The row 2 and row 3 have been interchanged over here. So what will be the determinant? So if this is determinant of A, then determinant of B matrix, right, will be simply minus of determinant of A, negative, because interchanging two rows will simply make it negative. If you want to, you can prove it as well. Okay, simply for a 2 cross 2 matrix, let's say I have this 1, 2, 3, 4, and now I'm interchanging the rows, making it 3, 4, 1, 2. You will see that this determinant and this will be negative of each other. These two will be negative of each other. Okay, same thing if you do, if you swap two rows. So here what I am doing, actually, first of all I swapped the two columns. If you see, sorry, two rows, right, I swapped the two rows. But here what I am doing, actually, this, right, this matrix is nothing but this one, but with swapped what, okay, again I have swapped the rows. So initially I swapped this row 1 and row 2, right, swapped the row 1 and row 2. But here again what I am doing, from this matrix B, right, I am swapping the row 2 and row 3 from the matrix B. From the matrix B, I am swapping the row 2 and row 3. You see, the row 2 and row 3 are swapped. So this, right, again I am swapping. So this will be the negative of the determinant of which matrix? Of B. Because I have swapped the two rows of matrix B. So this will be B, negative of B. And what is determinant of B? Negative of A. So your determinant of C will be negative of B, that is negative of A. So this will be plus A. Okay. Now same thing you could have said that if let's say I am swapping the rows twice. So here, right, from this A matrix, once I swapped the rows, again I swapped. If you swap it twice, right, then there will be no change in the determinant. Determinant remains same. But from A to B I swapped once, right? Then from B to A, B to C again I swapped. But I swapped the B. That's why it was negative of B. But from A to C, because I swapped twice, right, the determinant was same, positive. Okay, so basically if you swap the rows or columns, two rows and two columns, right, then the determinant is negative. Determinant sign will change, it will become negative, not negative actually, sign will change. Sign will change, determinant sign will change. Previously if it was minus 5, this will be plus 5. If it was minus 5, this will be plus 5. Okay, I hope that part is clear. If any two rows or two columns of a determinant are proportional, then the determinant of the matrix will always be 0. Basically the rows are linearly dependent on each other. Simple thing, right? You see, if 1 2 2 4, you find out the determinant, you will see it is 0. 1 3 2 6. Whenever your row is linearly dependent or proportional, directly proportional, not linearly dependent, directly proportional to any other row, then the determinant of the matrix will 100% be 0 always. Okay. If all the elements of any row or column is all 0, it will be 0 as discussed previously. If 3 rows or 3 columns are interchanged, then the sign of determinant remains unchanged. Okay. So basically from here to here what am I doing? Okay, like basically they are swapping thrice. Whatever I've discussed, if you are swapping the rows or columns thrice, then the sign of the determinant will not change. And determinant is, whenever determinant is 0, it is called as a singular matrix. Whenever the determinant of any matrix is 0, it is called as a singular matrix. Okay. Now let's discuss addition of matrices. Okay. So how like which matrices can be added, like which kind of matrices can be added and which kind of matrices I cannot add together. Let's say I have a matrix here, it is like a rectangular matrix 1 2 plus 1 2. Can I add this? No, not possible. For adding two matrices, their size must be same, otherwise I cannot add them. So here it is mn, I can definitely add. Here also I can definitely add, size is same. Here right, size are not same. This is n cross m and this one is m cross n. Size is different, like size is different, right? I cannot add. Like you will say why? Because what will be the resultant matrix size? Here right, the size is defined of the resultant matrix. It will be m cross n, right? The element, like if I am adding these matrices, right, let's say 1 2 0 2 plus 3 0 1 2, so I can simply add this, right? I know what will be the first element. First element will be the sum of the all the first element, that is 1 plus 3. This will be 3, right? This will be 3. Then this will be 2 plus 0, so 2. Then this will be 0 plus 1, so 1. Then this will be 2 plus 2, 4. Okay. So we got the sum of the matrix. So that's how you find out the sum. Their size must be same. Okay. Orders of the matrix must be same for proper addition. Okay. Now one thing, one few properties about addition of matrix is addition is commutative. Basically commutative means if I am doing a plus b, it will be same as b plus a. But in multiplication it will not be same. Okay, just be careful. In multiplication it will not be same. Addition is also associative, addition of matrices. So if I am doing a plus b, then I am adding c, or first I add b and c, then I add a. So both are same thing together. Okay. So addition, like so how to perform subtraction? Simply you perform addition and you multiply a -1 with this matrix. That will be my subtraction. Okay. Now one more property is there. If let's say a plus b is equals to a plus c, I can cancel this out. Simply that means b matrix and c matrix both are same. If this equation is given to you, that basically means that b and c matrix both are same. Okay. Now let's discuss about this thing, that if you have been given this equation that z is equals to x plus y, z equals to x plus y, and you have to find out the determinant of z. So you cannot simply say that determinant of z will be determinant of x plus determinant of y. No, that is not possible. Okay, determinant of z will be less than determinant of x plus y. Why? Like we will follow simple triangle law. If you have studied bit of triangle law, you will know that the if you have three sides, right, then the third side will always be less than or equals to sum of the other two sides for a triangle law. So we will, there is some proof. Of course, we don't want to get into the proof right now. Just believe me right now that the sum, right, if z is equals to x plus y, then the determinant always will be less than or equals to determinant of x plus y. A good question can be framed from inequality. It will not be equal, okay, not be equal, but it will be less than or equal to. So a good question can be framed from inequality from this particular topic. So it might feel like, okay, I'm teaching you basics, you already know all these things. Yes, I understand, you know all these things, but GATE professors, right, IT professors, they always focus on a very small thing, very basic but very important thing. So they might frame a question from here. So this is a important point, and trust me, no other place, institute will give emphasis to this point, right? They will skip all this. Like if they are teaching you some crash course, they will skip all these things, but these are important, and that's why our R-PYQ batch will be different. So if you are enjoying, make sure to hit the like button, so so that other people can also understand what kind of content we are teaching over here. Okay. So similarly, if D is equals to A plus B plus C, so the determinant of D will be less than or equals to determinant of A plus determinant of B plus determinant of C. Okay. Now we will discuss about multiplication of matrices. How can I multiply two matrices? So let's say I have my matrix A and B. How can I multiply? Although I have already explained how to multiply, but let's see. So let's say I have this C matrix, right? So we will start from the first row of the first matrix, that is pre-multiplied, and the column. So 1 into 1, 2 into 2, that will happen, right? So row into column basically. So it will be 1 into 1 plus 2 into 2. That will be my first element. So first row and first column will yield me the first element. Okay. Again, second row and second column will yield me the second element. Now, can you tell me what will be the size of the matrix? Size of the resultant matrix? As I have told you, whichever is at the front, right? This is a 3 cross 2 matrix, because I have 3 rows and 2 columns, and this is a 2 cross 3 matrix because I have 2 rows and 3 columns. So if I multiply these, right, I will take the rows of this matrix and I will take the columns of this matrix. Okay, I will take the rows of this matrix and I will take the columns of this matrix. Okay, so this will be 3 cross 3 matrix. So yeah, so the resultant will be a 3 cross 3 matrix. So if the resultant is a 3 cross 3 matrix, now I will start with the second element of my matrix. So second element will contain the first row and the second column. Second element will contain the first row and the second column. Why? Because we remember we are multiplying A into B, and A, the resultant has 3 rows. So first of all, it will have 3 rows. So the first row will be multiplied by all the columns. Then the second row will be multiplied by all the columns for getting the second row in the resultant matrix, and the third row will be multiplied by all the columns for getting the third row in the resultant matrix. So that is how you do matrix multiplication. So first row will be multiplied by the first column to get the first element. Again, first row will be multiplied by the second column to get the first element. Sorry, to get the second element. Basically, it is, what is the location of this element? Row 1, column 2. So row 1 meaning row 1 of matrix A and column 2 of matrix B. So that's why row 1, column 2, that is the location, and according to the location we will do the matrix multiplication. So this, what was the location of this? Row 1, column 1. So that's why we multiplied row 1 and column 1. Okay, so row 1 into column 2. So this will be 1 into 3 plus 2 into 4, and you can go on. Okay, I will not go on. Okay, you can obviously do the matrix multiplication. The purpose is just to explain you how to do matrix multiplication. Okay, so few kinds of matrix multiplication are not valid. So for proper matrix multiplication, I forgot to tell you that your number of columns of the first matrix and number of rows of the second matrix must match with each other. Here you see it is 3 cross 2 into 2 cross 3. So they are matching. So matrix multiplication is possible. Otherwise, matrix multiplication will not be possible. Let's say I have this matrix 2 1 and I have this matrix 2 0 1 0. So this is 2 cross 1. It is 2 cross 2. So you see the number of rows and number of columns are not equal. So number of columns and number of rows are not equal, right, in the first and the second matrix respectively. So this, right, matrix multiplication will not be valid here. This matrix multiplication will not be valid over here. Okay, so yeah, here uh, right. uh, so if you want to try, you can try. So I will multiply the first row and the first column. Then again, what shall be the resultant matrix? Resultant matrix according to us is 2 cross 2, right? So it should be 2 cross 2. So I will multiply the first row and the first column, that is fine. Then I will multiply the first row and the second column. Okay, 2 cross 1. Now I'm just checking one thing. First row, yeah, if I once I multiply the first row and the first column, right, this will be 2 cross 2, correct? But something I need to multiply with 1, right? Because here what I was doing, I was multiplying 1 into 1, then 2 into 2, correct? But here I need another element. That element is simply missing, right? So that's why this matrix multiplication is not valid. Okay, so always check whether the number of columns of the first matrix, matrix A, and number of rows of the second matrix, matrix B, are same. If they are same, then only you will be able to do matrix multiplication. Otherwise, you will not be able to do matrix multiplication. Okay, so in this case, what will be the resultant size of the matrix? N cross n, because you see number of rows, number of columns, and these are same. So this is valid. This again is valid because n and n are same, and the number of rows is m, number of columns is p. Okay, so the same thing whatever I have discussed is written over here. Okay, now one more thing, if A into B is possible, right, A into B matrix is possible, it is not necessary that B into A also will be possible. It may or may not be possible. As we have discussed, for that you need to check this criteria. Okay, so yeah, that is one caveat I want to tell you. So basically here in this same example, right, if I show you the same example, that this matrix multiplication was not possible. But if I take the same matrix, right, if I take the same matrix but I flip it, okay, so now 2 0 1 0 will come first into 2 1, it will come second. Now is this possible? Yes, it is 100% possible, right, because the number of columns of my first matrix and number of rows of my second matrix are both same. Okay, are both same. So yeah, then this will be possible. There is no problem, this will be totally possible, right? But this was not possible. So even though they are same matrix, but I'm multiplying A into B, but B into A is not possible, right? So they may or may not be possible. So first thing is, matrix multiplication is not commutative. Commutative meaning, if I'm doing A into B, that will give me some matrix. If I do B into A, that will give me some other matrix, and both of them might not be equal to each other. They may be, might not be. Okay, so that's why it is not a commutative. So I cannot flip it, I cannot change the location of A and B. It is definitely associative. It is definitely associative, that is A into B into C is same as doing A into B into C. But remember the sequence must not change, because it is not commutative. Sequence must not change. ABC sequence must be same. It is definitely distributive, that is if I am doing A into B plus C, so I can distribute it A into B plus A into C. Okay, so already we have discussed that if I am multiplying two matrices, right, their determinant will be simply multiplied. So it is a very good property of a determinant. Now we will discuss few types of matrices. Okay, these are just very short topics. What are the different types of matrices? Nothing much to discuss over here. Like row matrix is nothing but which contains simply a row, also called as row vector. Column matrix, which contains only a simple column. Null matrix. Null matrix is those kind of matrix where all the elements are zero. It can be rectangular, it can be square, does not matter, but all the elements inside the matrix is zero. The property of a square null matrix is the determinant of a null matrix is always zero. If it is a square null matrix, the determinant of a null matrix is always zero. Also, if I am multiplying any matrix with a null matrix, right, okay, and if the matrix multiplication is valid, then always the resultant also will be a null matrix. The size can be different, but resultant also always will be a null matrix. It is similar to multiplying anything with 0. So null matrix is equivalent to a 0, okay, similar to a 0. Then we have this diagonal matrix. What is this? Just give me one second. What is this diagonal matrix? Remember, diagonal matrix is a square matrix. Diagonal matrix is a square matrix. Okay, so it is a square matrix where the principal diagonal, so these, right, if I have a matrix here, uh, A, B, C, D, so these elements are called as the principal diagonal elements. Okay, these elements are called as the principal diagonal elements, and these elements, right, are called as the off diagonal elements. Just give me 1 second. Off diagonal elements. Okay, these elements. So the diagonal matrix is a square matrix, first of all, whose which only contain at least one non-zero element in the principal diagonal, that is when my I is equal to j. Basically ij meaning I is the row position and j is the column position. Okay, so whenever I is equal to j, that means the row and column are same. So basically this element is 1 1, this element is 1 2, this element is 2 1, this element is 2 2. 2 2 meaning second row second column, right? So whenever I is equal to j, in that location, in diagonal location, at least we should have one non-zero element, and in all the other elements, in all other location, the elements are 0. That is what is written over here. So whenever I is equal to j, at least we have one non-zero element, and all the other elements, right, when I is not equal to j, they are always 0. So that those kind of matrix is called as a diagonal matrix. Okay, so this, right, has a okay, this is also called as the principal diagonal, main diagonal or principal diagonal. Okay, so the property of a diagonal matrix is that its determinant will be just the multiplication of the diagonal elements. So if I have a 3 cross 3 matrix, you don't need to solve the matrix fully, right? The determinant will be simply the multiplication of a multiplication of the diagonal elements. You can solve it, you will get the same answer. Okay, now there are a few other terms. When my I is less than j, that means I am lying above of diagonal. What does it mean? So basically, let me take a very small example, 0 1 2 3, right? So this, right, this element is 1 1, this element is 1 2, this element is 2 1, that is second row, and this element is 2 2, right? So what does I less than j meaning? J means, so the first number is I and the second number is j. So only in this case my I is less than j, in this case, right? So it is actually above the main diagonal. Where is my main diagonal? Main diagonal is here. So I am lying above my main diagonal, that's why it is called as above main diagonal, so or above principal diagonal. Whenever I is equal to j, that means the location is I am at the principal diagonal, correct? And whenever I is greater than j, right, whenever I is greater than j, I am below the principal diagonal. Whenever I is greater than j, I am below the principal diagonal. Okay, here below meaning this element, right? When I is greater than j, that means I am below the principal diagonal. Okay, so that is the case over here. Now yeah, that was about the diagonal matrix. Then we have identity matrix. What is identity matrix? Identity matrix, again, it is a square matrix in which it is a diagonal matrix. It is a special kind of diagonal matrix in which all the diagonal elements are 1. All the diagonal elements will be 1. The special property of identity matrix is that the determinant is 1. Also, if I multiply any matrix with identity matrix, if the orders are same, then we get back the same matrix. Okay, so if I multiply any matrix with identity matrix, I will get back the same matrix. It is similar to multiplying 1. So 3 into 1 is 1. Sorry, 3 into 1 is 3. X into 1 is x. So it is similar to this, right? This kind of thing. So it is like a unit. So I'm multiplying a into I will get back a. If the matrix multiplication is valid, of course. First of all, you have to check whether the matrix multiplication is valid or not. Okay. So then we have scalar matrix. In scalar matrix, it is nothing but where all my diagonal elements are k, not 1k. So it is again a special kind of diagonal matrix where all the diagonal elements are k. Then we okay, property of diagonal matrix. Oh, that is determinant of diagonal matrix is 1, that we already know, so we don't need to discuss about this. Then we have this upper triangular matrix. So these are actually important, okay, questions can come from this. So what is the upper triangular matrix? Upper triangular matrix are, is also kind of a diagonal matrix, but in this case all my elements are not zero actually. All the elements that are below my principal diagonal all are zero. Only the elements that are above my principal diagonal, at least one of them is non-zero, right? At least one of these are non-zero, and of course my diagonal elements are also non-zero. Then it is called as a upper triangular matrix. Simply put, at all the elements below the principal diagonal must be zero. Okay. What is the property of a upper triangular matrix? Same property, that the determinant of a upper triangular matrix will come out to be the multiplication of the diagonal elements. Similarly, lower triangular matrix, just the opposite, just the dual. Lower triangular matrix is those kind of matrix where all the elements above my principal diagonal are zero. Lower triangular because it contains elements in the lower triangular, it forms a triangle, that's why it is called as lower triangular. Again the same property, determinant of a lower triangular matrix will be multiplication of the diagonal elements. You can prove it, like it's very easy. Okay. Then we have something called as submatrix. A matrix obtained by deleting some rows or columns of a matrix is called as submatrix. Basically, let's say I have this 1, 2, 3, 4, 5, 6, right? So this will be a submatrix. How have I got it? So basically I have got here by deleting the column and deleting the row. That is my submatrix. Here also how have I got it? So I have got here by deleting the column and deleting the row. This is my submatrix. Okay. Here how have I got it? So I have got this matrix by deleting this column, this row, and this column, right? So but is this a submatrix? 8, 7. Although these elements are there, but is this a submatrix? No. I can never form this, right? 7, 8 is a submatrix, but 8, 7 is not a submatrix. Again, null matrix is not a submatrix. Okay. Equal matrix is nothing but whenever two matrices are equal, they are called as equal matrix. Okay. If two matrices are equal, that basically means their elements, respective elements, will also be equal. So next we have transpose. What do I mean by transpose? So transpose is nothing but changing the rows into columns or the columns into the rows. Let's take an example. Let's say I have a matrix over here. What will be the transpose of this matrix? It is defined by the symbol A transpose, okay, or transpose. So this will be simply, if I take the transpose of this matrix, right, it will be, I will convert the columns into rows. So this is the first column. Now this will become my first row. This is my second column. Now this will become my second row. Okay. Now this is my third column. This will become my third row. Okay. So this is my E transpose. Simply I will transform my rows into column, right? So the order also changes. So here the order was 2 cross 3, right? 2 rows, 3 columns. Order will now become 3 cross 2. So whenever I am doing transpose, the rows are simply swapped to columns. That's it. So here again, if I am taking the transpose of a square matrix, basically what will happen? All the elements of the about the principal diagonal will be flipped. The principal diagonal element will be same, because what happens, my Aij becomes Aji, right? Here if you see, I think somewhere I must have written it. Okay, I have not written it. Okay, I have not written it. So Aij, basically if I have a element in ith row and jth column, that same element will now go to the jth row and ith column. Simply it gets flipped. So in a square matrix, what will happen? The transpose of this will be simply the principal diagonal elements will be same, because if I am flipping the row and column, right, for principal diagonal I equal to j. So simply 1 1, if I swap 1 1, it is 1 1, right? So 1 1 will be 1 1, it will not change, but 2 1 will be 1 2, okay, that will get swapped. So this principal diagonal element will not change, this will be 1 5 9, but the off diagonal element will be simply swapped. So this will now go to here, this will now go to here, like this is what this element is, location of this element is 3 1, location of this element is 1 3. So these elements will be swapped basically, okay. So I hope you get the answer. So this will be 7, this will be 8, this will be 6, this will be 3, this will be 4, sorry, this will be 2, this will be 4, okay. So yeah, that will be my matrix, okay. Yeah, so properties of transpose of a matrix, there are few properties that let's say if I am taking the transpose of whole transpose of this addition or subtraction, I can break it down. So this will be B transpose plus minus C transpose, that is possible, or A plus B plus minus, this also I can break it down into individually. Now if I am multiplying two matrices and then I am taking the transpose as I mentioned during the starting, right, then this will be flipped, it will become B transpose A transpose, okay. If I have three matrices and I'm multiplying, so everything will be flipped, right? So first C transpose will come, then B transpose, then A transpose. So because the multiplication is happening like this, right, if I'm taking the transpose, what will happen, I will start from here. First I will take the C transpose, I will write it, then I will take the B transpose, I will write it, then I will take the A transpose, I will write it, okay. If I have A B C D whole transpose, then I will write D transpose first, C transpose, then B transpose, then A transpose, okay. Transpose when applied to a matrix has higher precedence than multiplication. So if it is written that AB transpose, bracket is not there, right, bracket is not there, it simply means first I will take the transpose of B, then I will do the multiplication. So simply that you convert this into this format. So it is just like a Bodmer's rule in matrix multiplication. So transpose always will have the higher precedence. First you have to apply the transpose operator, then only do the multiplication. So first you will do B transpose, then you will do the multiplication. Similarly, if there is some addition, first you will do the transpose, then you will add. It's not like you will add the matrix A and B, or it's not like you will first multiply A, B and then take the transpose. No, not correct. It's not like you will first add the matrix A and B and then take the transpose. No, this is equals to A transpose plus B transpose, but that is not what we need to solve, right? So incorrect. So transpose will have the higher precedence, and the symbols of transpose are given here. A transpose, either it sometimes it is written as AT, A dash, A small t, or A TR. All these are representation of transpose of a matrix, okay. It is just a operator. Now let's discuss about trace. What is a trace of a matrix? Sometimes it is called as spur. Trace is nothing but the sum of the leading diagonal elements or the principal diagonal elements. It is only valid for square matrix, okay, because in square matrix only I can properly define a diagonal. In a non-square matrix I cannot define a diagonal, right? I cannot define a diagonal, okay. So trace is nothing but the sum of the diagonal elements. In this case, what is the trace? 5. 1 plus 4, 5. That is a trace. Now there are few properties of trace, right? Few properties of trace. Trace of sum of two matrices will be individual trace plus minus, okay. Then trace of again 3 matrix, I can individually find out the trace and then add. Trace of k times a, if I am multiplying a scalar value. So what does k times a means? So k times a, right, 1 2 3 4, and if I am multiplying a scalar, let's say 2, what does it mean? It basically means multiply 2 with all the elements. So this will be 2 4 6 8. 2 4 6 8, okay. So it basically means I will multiply 2 with all the elements, okay. That is what a trace means. That is what a trace means. Okay. No, so that is not what a trace means. That is what multiplying by k means. Okay, so if I am multiplying by k, all the elements will be multiplied by k. So if I am multiplying by k, right, what does it mean? That means the diagonal, all the diagonal elements are also multiplied by k. So basically, if previously the trace of a was trace of a, basically, what will be the new trace of a? It will be k times trace of a. Why? You see, right? Previously, what was the trace? 5. Now, what is the trace? 10. Simply, it is getting multiplied by k. So that's why trace of k into a will be k into trace of a. That's it. Where k is the scalar value. Okay. And trace of ab will be same as trace of ba. Now, this is a very important property, and this can be used everywhere. Although we know that ab may or may not be equals to BA, that we have already discussed, right, and we have proven it can or cannot be equal, right, it can or cannot be equal. But definitely if AB is possible, right, if multiplication of AB and BA both are possible, right, first of all both have to be possible. If both of them are possible, then this property will always be valid. This is a very important property, and for exam this kind of property can be asked. Okay, another property of trace is that if I am taking the transpose and then finding out the trace, or just finding out the trace of that matrix, both of them will be same, because ultimately in while taking the transpose, your diagonal elements do not get changed, right, only the off diagonal elements, the elements other than the principal diagonal, get changed. So that's why this property also will be totally like very important and valid. Okay, so yeah, now let's discuss about inverse of matrix. So let's discuss about invertible matrix. What are invertible matrix and what is inverse of a matrix? So basically inverse is nothing but inverse. So we know that what is the inverse of 3? What is the inverse of 3? Just give me 1 second. Yeah, inverse of 3 will be 1 by 3. How do I know? Because if I multiply the inverse with a number itself, I will get 1. That is the definition of inverse for a decimal number system. So in matrix, somewhat similar thing happens. If I multiply two matrices and the product comes out to be inverse, sorry, product comes out to be the identity matrix, then it is called as a invertible. Then the other matrix is called as the inverse of the previous matrix. And remember that both multiplication must be identity. That is, a into b must be I and b into a also must be I. Then only the other matrix will be inverse of the current matrix, right? So this is also called as b equals to a inverse, right? So property of a times a inverse is not a times a inverse, or a inverse times a is identity, right? I have just replaced my b with a inverse, that's it. Okay, like something similar I have explained over here itself also. So now this was the property of inverse, and inverse is actually very useful to us. It will be used everywhere. So how can I calculate the inverse? To calculate the inverse, first of all you need to understand that inverse will only exist for square matrix, because to calculate the inverse of a matrix you will need to find out the determinant of that matrix, and the determinant is only valid for square matrix. That's why it is inverse is also only valid for square matrices. A has to be a non-singular matrix for inverse to exist. Non-singular meaning the determinant of A must not be equal to 0. Why? Because I have told you, right, if determinant of A is 0, that means it is a singular matrix. That's what we call a singular matrix. A singular matrix is a matrix whose determinant is 0. A non-singular matrix will be a matrix whose determinant will be non-zero, right? Because the formula for inverse of a matrix is adjoint of the matrix A upon the determinant of A. So this, if this goes to 0, then definitely inverse will not exist, right? Because this is in the denominator. Now how do I know how to compute determinant of A, but how do I compute adjoint of A, right? We will see. So basically if your if ever your determinant of A is equal to 0, then inverse will not exist. Inverse does not exist. If your determinant of A is equals to 0, then the inverse of that particular matrix will never exist. Okay, so we know how to calculate the determinant, but I don't know how to calculate the adjoint. So what is adjoint? Adjoint is nothing but matrix of cofactors. What is cofactor? So cofactor, right, is this value. Don't worry about these things. Okay, I will explain what is it. So it is transpose of matrix of cofactor. Don't worry, I will explain how to calculate adjoint for a 2 cross 2 matrix, and then we will discuss for a 3 cross 3 matrix how do I calculate the adjoint. Okay, so let's say if I have a simple 2 cross 2 matrix, right? For a simple 2 cross 2 matrix, actually you never need to remember how to calculate adjoint. You can easily calculate determinant with a shortcut, but I will still tell you the basic general method to calculate adjoint for a 2 cross 2 matrix. So let's say I have a 2 cross 2 matrix A, B, C, D here. How will I calculate the adjoint? So what you do is first you write the signs plus minus plus minus. Okay, then you calculate the cofactors. What are the cofactors? Cofactors are nothing but the, let's say the cofactor of the first element, right, will be D, because after I cross this particular column, I cross this particular row, only that is left is D. D will be the cofactor. Don't worry, for a 3 cross 3 matrix I will explain what will be the cofactor. For a 2 cross 2 matrix it is pretty simple. So cofactor, right, of A, cofactor of matrix A will be D for the first element. For the second element it will be C. For the third element it will be A. For the this element, not third, sorry, this was the fourth element actually. For this third element it is B. Now make sure to put the signs. So this is plus, this is minus, so I'll put here minus, right? I'll put here minus. This is plus, this is minus, so I'll put here minus. So this is the cofactor matrix, but my adjoint of A, right, is actually not equal to matrix of cofactors. It is a transpose of the matrix of cofactors, so I have to take the transpose of this. That will be my adjoint of A. So adjoint of A will be matrix of cofactors whole transpose. Okay, so this will become, if I transpose this, this will be D minus B minus okay, C A. Okay, so this is my adjoint of A. Now what is that inverse of A? It will be adjoint of A upon determinant of A. That is what? That is simply equals to, this is my adjoint matrix, right? And what is the determinant for a 2 cross 2 matrix? Very simple, it is A into D minus B into C divided by AD minus BC. So I will divide this by all the elements. So this will be basically my inverse, right? Simply this will come at the numerator. This will come at the numerator. Okay, so yeah, that's how you calculate the inverse, as I have shown you here as well, right? So there is a few shortcut to calculate the inverse of a 2 cross 2 matrix. The simple shortcut is you don't need to calculate the adjoint, right? You don't need to calculate the adjoint. Directly what you can do is, directly if you have to calculate the inverse of a 2 cross 2 matrix ABCD, you will swap the main diagonal elements and change the sign of the off diagonal elements, and then divide by the determinant of that particular matrix, this particular matrix, right, of matrix A. This will be your inverse. Directly you can see the answer is matching. So this is a shortcut, and you will say, sir, do I have to remember it? It will automatically be in your brain, because you will calculate the inverse of like thousands of 2 cross 2 matrix. Automatically this will be installed in your brain, don't worry. Okay, so that's how you calculate the inverse of a 2 cross 2 matrix. We will also discuss how can you calculate the inverse of a 3 cross 2 matrix. Before that, let us discuss about pre-multiplication and post-multiplication. So what do I mean by pre and post-multiplication, right? So pre-multiplication is nothing, let's say A and B is equals to I. So what does mean pre-multiplying? Pre-multiplying means I'm multiplying at the start, because of course in multiplication, because multiplication is not a commutative operation, So whether I'm multiplying here or here, it actually matters. It will change the answer. It will change the answer. So pre-multiplying means I'm multiplying at the start. Pre-multiplying by A inverse is, that means I'm multiplying at the start. Okay. What does post-multiplying means? Post-multiplying means I'm multiplying at the end. You see, I'm multiplying at the end. So these are few like terms that you must keep in mind, because this can be asked, this can be written in the question, right? This can be written in the question. So you must be clear what does pre-multiplication means, and pre means early, so that's why early, starting. Post means later, post, that's why later. Simple terms, right? Now we will discuss regarding how to calculate the adjoint for a 3 cross 3 matrix. What is the normal method and what is the shortcut? Okay, shortcut, you can remember the shortcut, but generally they will not ask you to calculate the 3 cross 3 adjoint, but still. Okay, let's take example. Let's say I have this matrix, right? I have this matrix, and how do I calculate the adjoint of this matrix? Because I want to calculate the inverse. To calculate the inverse, I need the information about the adjoint of this 3 cross 3 matrix. Maximum what will happen, they will never ask you to calculate the inverse of a 4 cross 4 matrix, because the calculation will be huge. Most cases they will ask you to calculate the inverse of a 3 cross 3 matrix, like not even calculate, maybe you will find it out in some other way. We will see how can you find it out. So for this, I know how to calculate determinant. How do I calculate determinant? Determinant is pretty easy, right? Determinant will be, I will break this determinant down. Determinant of A will be, first this will be plus, this will be minus, this will be, let me, plus minus plus. So this will be 1 times this matrix, right? Determinant of this matrix, that is 3 minus 3 minus 16 minus 0 minus 20. So this is already minus 2 and inside I have minus 20, right? Because this is 0 minus 20. So yeah, 0 minus 20. Then plus this is 0 minus 15. So plus 0 minus 15. Okay, so yeah, that is the case over here. Now what we can do is, what will be determinant of A? What will be determinant of A? Determinant of A will be, this will be minus 19 plus 40 minus 60. It's not 60, even minus 90, right? So minus 50 minus minus 19. So minus 50 minus 69. Okay. So this will be the determinant of A, minus 69. Now what about the adjoint of A? What about the adjoint of A? So the adjoint of A, right? General method is, yeah, this is again correct, right? But I have to do this for all the elements. So this will be plus minus plus minus plus minus plus minus plus. Okay. So what will be the, like, first of all it will be the matrix of cofactors whole transposed, right? So I'll find out the matrix of cofactors. What will be my matrix of cofactors? Matrix of cofactors will be equals to, what is the cofactor of this element, first element, right? In the row 1 and row column 1, this will be the determinant of this matrix, right? And of course you have to include the sign. So what is the determinant? Already you have calculated it, right? This is 19, minus 19 actually. So minus 3 minus 16. So this is minus 19. Then what is the cofactor of this element? 0 minus 20, as we have already calculated. But remember, there is a negative sign. So I have to provide the negative sign over here, right? So this will become, already this is minus 20 minus, and this is already minus. So minus minus will be plus 20. Okay. Then what about here? Here what is the determinant? It is minus 15 and it is plus sign, right? Plus into minus is minus only, so this will be minus 15. Okay. Similarly, you can calculate the uh, cofactor of this element. What is the cofactor of this element? It will be 2 times minus 1 minus 6 times 4. So minus 2 minus 24 minus 26. And what is the sign of this element? Minus. So minus minus will become plus. Minus minus, just hold on a second. This is 2 times minus 1 and minus 24. Yes, correct. Yeah, 2 times minus 1 and minus 24. So this will become, hold on a second. This is already minus. So 2 times minus 1 and yeah, minus 24. So minus 26, this will become plus. Already, like, see, it is minus 26 and negative sign is there, right? So this will become plus. Okay, this will become plus. And then what you can do, again, simply you can complete this matrix. Okay, you can complete this matrix and you will get your adjoint of A, right? I will not do it, you can complete it. And then, so not, this will be cofactors, this will be the matrix of cofactors. Your matrix A inverse will be adjoint of A upon the determinant of A. You will take the transverse of this, right? Then you will get your inverse by dividing the determinant of A. Now there is a shortcut actually, but I don't think you will be able to remember the shortcut. This is the better way, understanding the general method, how to solve it. You will do some mess up in the examination. So I think let's leave the shortcut for full course itself. Okay. So I think because you will make some mess up, but generally the matrix that they will give you, right, to calculate the inverse will be on the easier side, just like a diagonal matrix. If I have a diagonal matrix, the inverse is very simple. It is simply the inverse of individual elements. So we can calculate the adjoint of A. You will see that adjoint is coming out to BC, AC, AB, and then of course you have to divide by the determinant. If I divide by the determinant, what is the determinant? ABC. It will be 1. So this element will be 1 by A, this element will be 1 by B, this element will be 1 by C. So that is what my inverse of A becomes. That is what my inverse of A becomes, right? Simply, if let's say I have a diagonal matrix here, what will be the inverse? Very easy, very simple to calculate. Just take the inverse of the individual diagonal elements. Only this is only valid for a diagonal matrix. Okay, only valid for a diagonal matrix, right? Okay, already discussed that if a matrix is singular, inverse will not exist. It is not singular, inverse will exist. But adjoint of a square matrix will always exist, right? Because adjoint does not depend on whether it is a whether the determinant is 0 or not. It does not have any condition for it to exist, right? But inverse has a condition that for the inverse to exist, the determinant must be equals to must not be equal to 0. Basically, the matrix must be non-singular in nature. Now let's discuss few properties of adjoint. Let me drink bit of water. So I know my A inverse is adjoint of A by determinant of A, and this is also a matrix. This is just a scalar number. So I can cross multiply by determinant of A on both sides. If I cross multiply, I get the formula for adjoint of A actually. If I know the inverse, I can find the adjoint of that particular matrix. So adjoint of A will be simply determinant of A into A inverse. That's it. That is the first property of adjoint of A. And remember, n is the order of the matrix. Order, like, remember all these, whatever we are discussing for a square matrix. So inverse, adjoint, all of them will exist for square matrix only. Inverse, adjoint, all of them will exist for a square matrix only. Because why? Because determinant only exists for a square matrix. That's why. Okay. Okay. So from this, right, if I now pre-multiply by a on both sides, I get another property that a, I'm pre-multiplying because this is just a constant number, right? I'm pre-multiplying by a on both sides. So a into adjoint of a will be determinant of a into I, because a inverse into a is I. So we get this beautiful property that a into adjoint of a will be equals to my identity matrix into, obviously, determinant of a is there. Determinant of a is there. Okay. Now, what will be the adjoint of a null matrix? Adjoint of a null matrix will always be 0, right? Because all the elements are 0, right? So simply your if I show you a null matrix, so what will be adjoint? So you will first cross out this one, you will write this one, you will cross out this one, you will write this one. So all the elements are 0. So adjoint of a null matrix will be 0. Adjoint of an identity matrix will be the identity matrix itself. How? So simply you can put here a is equals to I, right? You put here a equals to I, or you put here a equals to 0. So from this property also you can derive it, right? If I put here null matrix, a equals to null matrix, what will happen? So if a equals to null matrix, this will be null, right? This will be null. Okay, so no, I could not put it over here, because if I put null, right, if I put null matrix, I know that inverse will not exist, so I cannot do all this. Simply null matrix, for finding out the adjoint of a null matrix, you can take help of here. But if I put a equals to I identity matrix, if I put a equals to identity matrix, what will happen? This will be I, this will be I, right? So I into any matrix is that matrix itself, I into C is C itself. So on the left hand side I will have adjoint of I. On the right hand side, this will be, what is the determinant of I? It is 1, right? So this is anyways 1 into I. So that's why the adjoint of identity matrix is identity matrix itself. So why am I showing you this? Why am I explaining you the proof? Because in the GATE exam, they will not give you this property. They will not ask you what is the adjoint of I. No. In the GATE exam, you have to use this property, right, to solve some other question. So you should know how am I deriving it, because this only will help you in the actual exam. If you just remember this property, this will not help you, because you have to solve in the exam, right? So maybe you have forgotten this, but if you know how to prove it, you will be able to solve that particular question. You will be able to solve that particular question. Okay. Now, one more property is there. If I am multiplying a scalar number lambda times a and taking the adjoint of it, the adjoint, then what it comes is, this adjoint is lambda n minus 1 raised to power minus 1 into adjoint of a. Okay. Why? How does it happen? How does it become lambda into n minus 1? So we can again use it over here, use this property, right? Have I proven it? No. Let me prove it. So adjoint into lambda times a, right? What will be this equals to? So we know that a into adjoint of a equals to determinant of a into I, right? Identity matrix of order and whatever is the order of my matrix. Now let's say I replace my a with lambda a, right? Replace my a with lambda a. So this will be lambda times a into adjoint of lambda a equals to determinant of lambda. I am replacing my a with lambda a, right, into I, and this equation will still be valid. Basically, I am writing C, some other matrix b equals to lambda into a, and I am replacing my b with lambda, right? So now what will happen is that if what I can do, what is the determinant of lambda into a? Do you remember this property? If a has an order of n, right, a is a n cross n matrix, and if I am multiplying some k scalar with a and then I am taking the determinant, it comes out to be k raised to power n into determinant of a. I hope you remember this property. So this will come out to be lambda raised to power n into determinant of a I of n. Okay, and here I have this lambda into a by into adjoint of lambda A, right? Now what I can do, lambda is just a scalar, so I can divide by lambda on both sides. So this will come out to be A adjoint of A adjoint of lambda A equals to lambda raised to power n minus 1. Now I can pre-multiply A inverse on both sides. I can do that, right? I can multiply A inverse on both sides. So if I multiply A inverse on both sides, what will I get? This will be adjoint of lambda A equals to lambda raised to power n minus 1 determinant of A into A inverse into I. What is this? To remember what is determinant of A into, like this is determinant of A into A inverse. Anything multiplied by a matrix, right? Identity matrix is that matrix itself. So I can neglect the identity matrix. So it is simply 1, right? So do you remember something like this? Determinant of A into A inverse. What is it? It is simply adjoint of A. Determinant of A into A inverse is simply adjoint of A. So this is actually adjoint of A, right? So this will become lambda into n minus 1 into adjoint of A. So that's how you prove this property. So it's not like you will remember everything in your brain, right? You may not remember this. So I've proven it to you. You may not remember this thing. But even if you don't remember, right, now you know how can you prove it. Okay. So in the exam hall, just you need to remember this one. This is the most important one. This one also, if you forget, like you at least you will remember this one, right? If you remember this one, you can get back to this. And from this, you will simply derive every other property that is there for adjoint of A. And trust me, questions do come from this topic. Questions do come from this topic. Okay. Okay. The next property is this one. Determinant of adjoint of A is equal to determinant of A n minus 1. So again, I can apply the same property. I have to find out determinant of adjoint of A. So what is adjoint of A? Adjoint of A is determinant of adjoint of A. How does A into adjoint of A comes out? Oh, okay. So what we are doing is to prove this property, right? We are directly taking the determinant in this equation. If I take the determinant on both sides, so I have two matrices and I'm taking the determinant, right? If I take the determinant, let's say this is a matrix some B, right? AB. So determinant of matrix AB will be determinant of A into determinant of B, right? That is determinant of adjoint of A, right? Equals to, now here it is interesting actually. Determinant of A, right? Remember, this is just a scalar value. Determinant of A is just a scalar value. I is the identity matrix, right? So it will come out to be determinant of A raised to power n, because I has an order of n, into determinant of I, which is simply 1, right? So now if I divide by determinant of A on both sides, because determinant of A is just a scalar number, it will come out to be determinant of adjoint of A comes out to be determinant of n minus 1. Determinant of adjoint of A comes out to be determinant of n minus 1. So that is what my determinant of n minus 1 equals to. Okay, I hope it is clear. So yeah, these are few properties. So one more property is there, that if I am taking the adjoint of A transpose, right? Adjoint of A transpose, it is same as calculating the adjoint of A and then taking the transpose. The proof is given over here, you can see the proof, but both are same. So it does not matter that whether you take the transpose of that matrix first, then find out the adjoint, or you first find out the adjoint and then take the transpose. Your order of application does not matter. One more property is there, that adjoint of EB will be equals to adjoint of B into adjoint of A. It is similar to taking transpose, right? So if you remember, EB whole transpose we discussed was equals to B transpose into A transpose, something similar. So how can I derive this? So what is adjoint of B into adjoint of A? What is adjoint of B? Adjoint of B will be determinant of B into B inverse matrix, right? Into B inverse into determinant of A into A inverse. Okay, that is what my that is what this adjoint of B into adjoint of A is. Now this, right, I can write determinant of A into determinant of B. These are just scalar numbers into B inverse into A inverse. Now another interesting fact is there that AB inverse, right, this property I think if we have discussed previously, will be equals to B inverse into A inverse. This is the property. So B inverse into A inverse will be equals to AB inverse. So I can replace this B inverse into A inverse with AB inverse. So this will be determinant of A into determinant of B. So I can actually include both of them. Determinant of A into determinant of B will be determinant of A into B together, right? I can do that because from here I can come back to here. So this will be now BA inverse. Okay, sorry, AB inverse. Okay, AB determinant will be equals to AB inverse. Okay, so yeah, that is the case over here. So now what I can say is that what is this? Is this something familiar? AB determinant is equals to AB inverse. Is this something familiar? Yes, it is something familiar. What is it? What is it? It is simply nothing but adjoint of AB, right? It is similar to A determinant of A into A inverse. And what is it equals to? I can keep a I here, right? I can keep I. It does not matter if I keep a I or not. So it is nothing but adjoint of that matrix, right? Adjoint of AB. Adjoint of A is A determinant of A into A inverse. So here I have determinant of AB into AB inverse, right? So it will be nothing but adjoint of AB. So hence proved adjoint of AB will be adjoint of B into adjoint of A. Okay, that's how you can remember this form, remember this property. So similarly, you can prove that adjoint of ABC will just be sequential. So adjoint of C into adjoint of B, adjoint of A. So you will move in this direction. Okay. There are a few other properties like this one, right? Adjoint of A will be determinant of A into n minus determinant of A raised to power n minus 2 into E. Again, you can apply the same formula here. Like what I will do, I have to find out adjoint of A. So I can replace my A with adjoint of A. What I will do, I'll replace my, like this equation I already know, right? This is the basic equation, standard equation. So I'll replace my A over here with adjoint of A. So I'll replace my A with adjoint of A. So this will become adjoint of A because I want to get this expression adjoint of A, right? And I will replace my A to adjoint of A. So this will be A into adjoint of A, right? Equals to determinant of A. Now A has been replaced to adjoint of A. And what is determinant of adjoint of A? Determinant of adjoint of A we have derived. It is determinant of A raised to power n minus 1. N is the order. So this will be determinant of adjoint of A, that is determinant of A into n minus 1. Okay. So this will become yes, so this will become, now what is adjoint of A? What is adjoint of A? Adjoint of A is A inverse into determinant of A, right? Adjoint of A is A inverse determinant of A into A inverse, right? This is also we know, into adjoint of A equals to determinant of A raised to power n minus 1. Now I can again divide by determinant of A on both sides. Determinant of A is just a scalar number. So this will be determinant of A raised to power n minus 2, then I can pre-multiply by A on both sides. If I pre-multiply, this will be A into A inverse, that is simply I, identity matrix, and I into any other matrix is that matrix itself. So it will be just adjoint of A. What about the right hand side? So I am pre-multiplying by A, right? So A will come here. So it does not matter, it is just a scalar number. If I write it at the starting or ending, it does not make any difference. So I can safely write here that my adjoint of A equals to determinant of A n minus 2 into A. Okay, isn't that what we have written over here? Yeah. So you can prove it actually. So few things you can remember actually, that if you find out the determinant of this, right, now what will happen, this will be n minus 1 whole square. Okay, now similarly if you find out the determinant, like how do you remember? So the determinant of adjoint of A was coming out to be determinant of A raised to power n minus 1. Determinant, so this is just a operator, right? Determinant of adjoint of A is coming out to be determinant of A raised to power n minus 1 whole square. Okay, n minus 1 whole square. Determinant of now determinant of adjoint of A will be n minus 1 whole cube. So this is like a pattern. So you can remember it like a pattern. Similarly, adjoint of A is determinant of A into A, right? Am I correct? So adjoint of A is determinant of A into A inverse. Okay, into A inverse. Your adjoint of A is determinant of A raised to power n minus 2 into A. So this, remembering this is a bit difficult. So you can derive it. Okay, you need to derive it, and this will not be asked. Trust me, this will not be asked. If this is asked, then you need to derive. Like remember, this is a bit difficult. So because it is not following any pattern, but this is definitely following a pattern, right? So at least you can remember the determinant of the adjoint, and in most cases you will see this has been asked in the examination because it follows a simple pattern. Okay, so that's how you remember what is your n is the order of the matrix. If it's a 3 cross 3 matrix, n will be 3. If it's a 2 cross 2 matrix, n will be 2. If it's a 4 cross 4 matrix, n will be 4. Okay, so these are few properties of adjoint of A. Now another few properties of the inverse is basically ABCD inverse will be D inverse, C inverse, B inverse, A inverse. That is the inverse property. Like because I have not proven it to you how this comes, I can actually show you, right? So let's say I have AB whole inverse. What will be this equals to? So I know this, right? I need to find out AB whole inverse, right? I will calculate AB whole inverse. So I know that AB inverse into AB will yield me I, because what I am doing, I am just multiplying the inverse of the matrix, right? So it will yield me I. Now what I can do, I can post multiply by B inverse on both sides. So if I post multiply by B inverse on both sides, this will be A into B inverse. This will be I into B inverse. So I into any other matrix will be the other matrix, and here B into B inverse will be I. Okay, so this will be AB inverse into A equals to B inverse. Now if I multiply by A inverse on both sides, post multiply by A inverse on both sides, what will I get? This will be AB inverse equals to B inverse into A inverse. So now I hope it is proven that AB inverse will be B inverse into A inverse. because if I multiply A inverse on both sides, this will be A into A inverse, that is simply I, and B inverse into A inverse is simply B inverse into A inverse, right? So that's how AB inverse is equals to B inverse into A inverse. That's how we get the proof. Okay, I hope it is clear, right? So there are a few other properties like K into A inverse will be 1 by K into A inverse, because like it is just a scalar. K is just a scalar, and what is the inverse power of a scalar? It is 1 by K, right? I hope that is understood by you. So that's why it comes out to be 1 by K into A inverse. And again, if I am taking the transpose then taking the inverse, or first I am taking the inverse and then taking the transpose, order does not matter. Okay, and remember here K cannot be equal to 0. Okay, if K is 0, this is not valid. Okay, because I cannot do 1 by 0, right? And again, some other property, that if I am taking the power of A, right, let's say I am doing A is a matrix 1 0 1 2 3. What do I mean by A square? A square basically means I am multiplying A twice, so it is 0 1 2 3 and then again 0 1 2 3, right? I am multiplying it twice. Now the simple property is, if I want to find out this value, right, A square inverse, this value will be same as this value, A inverse, then I take the square. Both of them are perfectly valid. Order does not matter over here. And again, determinant of A inverse, right, will be 1 by determinant of A. Okay, determinant of A inverse will be 1 by determinant of A. These are few properties. Again, determinant of K into A inverse. Now this, right, this is different. Here I am taking the inverse whole, but here the inverse is with the matrix. So it will be determinant of, what is the order of A inverse? N. So that's why when I will take this K outside the determinant, it will come out as K raised to power N, right? This is a property of determinant. And so, and what is the determinant of A inverse? Determinant of A inverse is 1 by determinant of A. That's why this comes out to be K raised to power N divided by determinant of A. Okay, and what about what about this one? If I am taking the inverse of K into A and then taking the determinant, so now the inverse is whole with respect to everything, right? So first I will solve this one. What is Ka whole inverse? Ka whole inverse, I have explained you, it is 1 by K A inverse. So this comes out to be 1 by K A inverse, and then I am taking the determinant. Again, this is just a constant number. What is the order? N cross N. So if I take this outside determinant, the power should be N. So that's why once I take it outside, it comes out 1 by K raised to power N, and the determinant of A inverse is simply 1 by determinant of A. Okay. So yeah, these are few properties. This will be very helpful in calculating inverse and determinant, right? Now let's come to a very good question actually. Like we want to prove few things. I am expecting someday GATE will ask a question from this particular property. I'm expecting. I think they have also asked something like this, right? So if I know the product of two matrices is a null matrix, if the product of two matrices is a null matrix, then what can I conclude from that? So the product of two matrices is a null matrix. So the first conclusion, like first case that can happen, right, is that either A or B both are null matrix. If A and B both are null matrix, then the product will be also null matrix. So I anyways know multiplication of anything with null matrix is 0. But if both are null matrix, then also this is a possible case, right? This is a possible case. If both are null matrix, A and B both are null matrix, then this is absolutely possible, like not possible, like this will be always true. This will be always true, right? Now if let's say only A is null and B is not null, then is this equation valid? Or only B is null matrix and A is not null matrix, then also it is valid, right? So because if I'm multiplying, let's assume B is null matrix. So if I'm multiplying anything with a null matrix, it will come out to be a null matrix only, right? Or if let's assume A is a null matrix and B is not a null matrix, then also the result will be null matrix. Now the third case, that is the most interesting case. That is the most interesting case. So in this case, right, first of all, your A and B both are not invertible in the case 1. A and B not invertible. Why? Because null matrix is not invertible. Why? Because the determinant of null matrix is 0. It is a non-singular matrix, so it will never be invertible. Okay. Now, what about this case? In this case, B is invertible because B is not a null matrix, right? Its determinant will be non-zero, maybe non-zero, maybe non-zero, maybe not zero. We don't know, but like we can surely say that A is not invertible. I can surely say, like, because if B is not a null matrix, right? B can be this matrix as well, 1 1 1 1. Now here B is not a null matrix, but still the determinant of B is 0. So I cannot comment about the determinant of B, nature of the determinant of B, right? Whether the inverse will exist or not, but I can definitely comment on the nature of A. A definitely will not be a invertible matrix because it is simply a null matrix. In this case as well, your B definitely will be a non-invertible matrix because it's a null matrix, right? I cannot comment about A. Now let's come to the third case. If in third case both A and B are not null matrix, okay, A and B both are not null matrix, you are saying A and B both are non-null matrix, can the product still be 0? Is that a possibility? Is that a possibility? That is a possibility. There is a possibility. Like I can take an example. Okay, let me take 1 2 2 4. Okay, I think the matrix, okay, example is not here, 1 2 2 4 and 2 2 minus 1 minus 1. Okay, so what do you do? If you do multiply these two matrices, right, here both of them are not null matrices, but still the product will come out to be 0. So this will be 1 into 2, so that is 2, 2 into minus 2, that is 2 minus 2, 1 into 2 minus 2, 4 minus 4, 4 minus 4. So this comes out to be 0 0 0 0. So it is a null matrix. So the product multiplication comes out to be a null matrix. Correct? Multiplication comes out to be a null matrix. Okay. So now what we can do is we can. So what is the conclusion? The conclusion is either A or B, one of them has to be a singular matrix. Then only this actually will be valid. How? How can I conclude it? So simply let's do this, right? Let's assume both A and B are invertible. That is, they are not singular matrix. Both A and B are invertible. So if I assume both A and B are invertible, right? So A into B is null matrix, and assuming both A and B are invertible, that is their inverse exists. So if I can multiply by A inverse on both sides, I can multiply by A, let's assume I can multiply by A inverse on both sides. If I multiply by A inverse on both sides, what am I getting? So it will be A inverse into A equals to this into 0. Okay, so this will be B equals to 0. But I just said that both have to be like both are non-null matrix, right? I just told you both are non-null matrix. That was my initial condition here, right? Both are not null matrix. But if I say that A is invertible, then B becomes null matrix. If I say A is invertible, then B becomes null matrix. This is not contradiction, right? Contradiction from our initial assumption. I told you that both A and B has to be not null matrix, right? So, but B is coming out to be null matrix if I assume that A is invertible. Okay. Similarly, if I assume if I do the same thing, right? If you multiply by B inverse now, you will see that A is coming out to be null matrix. So actually inverse cannot exist. So basically I cannot multiply by inverse. So if you multiply by B inverse in this equation, right? If you multiply by B inverse, what will you get? It will be A will be B into B inverse, that is I, and here whatever I multiply with B null matrix, right? It is null. So this will be null. Okay. this will be null matrix basically. So A is a null matrix. So but it is contradicting, right? Our assumption was A is not a null matrix. We have already taken the case where A is null matrix. That is already done. So the thing is, if I assume that both of them are not null matrix, and here I have also shown you that it is possible, even though both are not null matrix, I can still find out the like the multiplication to be 0, but one condition needs to be satisfied, that is determinant of each matrix must be equals to 0. Determinant of each matrix must be equal to 0. How? So AB is null, right? So if I take the determinant of both sides, this will be determinant of A into determinant of B equals to 0. Basically determinant of null matrix is 0. So already I have told you A is not a null matrix, B is not a null matrix. So either A can have non-zero determinant and B can have non-zero determinant. If both of them are invertible, that means this equation will not be valid, right? A and B both cannot be invertible. One has to be at least non-invertible, then only this determinant will come out to be 0, because one has to be at least singular matrix, at least 1 into 0 will be 0 or 0 into 1 will be 0, okay? But 1 into 1 will never be 0, right? So both of them cannot be invertible, at least one has to be not invertible. But in this particular case, right, when both of my matrices are not null, both have to be not invertible, because we will simply contradict our assumption. I have shown you, I have proven it to you, we will contradict our assumption. So here if you see, the special thing about these two matrices, the determinant of these two matrices was 0. The determinant of these two matrices was 0. It is 2, 4 minus 4, 0. It is minus 2 plus 2, 0. So that is a speciality. So if I have two matrices which are not null and I am multiplying them and I am getting a null matrix, that means individually the determinants must be 0, otherwise this condition will not be satisfied. Okay. But if you say one of the matrices is null matrix, then B can be any matrix, no problem. Okay. So that is the conclusion I want to like say. So you can slowly repeat this portion again, you will understand it better. Okay. So yeah, I hope that part is clear. I have taken the examples as well, right? So let's now move on to the next portion. Again, we will see few types of matrices. Let me drink a bit of water. So the first type of matrix is symmetric matrix. Symmetric matrix. So here symmetric matrix is nothing but a square matrix whose elements are symmetric about its principal diagonal. Or mathematically I can say that if I take the transpose of a symmetric matrix, it will be the same matrix. We can take few examples. Let's say 1, 2, 3 and 3. So if I take the transpose of this matrix, right, what will I get? It will be diagonal elements will be same, off diagonal elements will be swapped. So again it is the same matrix. So A transpose is equals to A itself. So it is a symmetric matrix. Okay. But let's take another example. 1, 2, 1, 0. Is this matrix symmetric? No. If I take the mirror image about the main diagonal, I see these elements are different. Whenever the mirror image about the main diagonal is not are not identical, that means it is not a symmetrical matrix. If I take the mirror image here, right, I see the elements are identical. For a 3 cross 3 matrix also, 1, 2, 3, okay, you will take the mirror image about the diagonal elements and you will see whether these elements, give me 1 second, whether these elements and these elements are same. If these elements are same, then definitely the matrix will be symmetric. And there are few good properties about a symmetric matrix. Okay, so A will be equals to A transpose, or if I take this A transpose on the left hand side, so my A minus A transpose will be equals to 0. A minus A transpose will be equals to 0. Okay, so there are few properties of symmetric matrix. If A is a symmetric matrix, then A raised to power k, A inverse A transpose adjoint of A plus A transpose, all will be symmetrical. Okay, if A is symmetrical. How? So if I calculate, if A is symmetrical, that means A is equals to A transpose, correct? So what is A raised to power k transpose? So I have told you, right, if I take the transpose first then take the power, it does not make any difference, correct? So this will be A transpose raised to power k. And what is A transpose? Equals to A. So this will be A raised to power k. So I see A raised to power k transpose is A raised to power k. So it is again symmetric. Similarly, you can prove it for all the others. So what is A transpose? So if A is symmetrical, right, A transpose also will be symmetrical. It is like the same thing only, right? So A transpose, if I take the transpose of this, what will it be? A transpose itself is A, and then again I am taking the transpose, and A is a symmetric matrix, so A transpose will be A. So this will be again A. Or simple words, in simpler words, if I take the transpose and then again I take the transpose, right, we get back the same matrix, because first I am swapping the off diagonal elements, again I am swapping the off diagonal elements, so I will get back the same matrix. So this is another property of transpose. I think I forgot to tell you during that point of time, but if I am taking the transpose twice, I will get back my same matrix as it was before. Okay. So one more very important property about symmetric matrix is that its eigenvalues will always be real and positive for a symmetric matrix, right? So we will discuss what are eigenvalues. I think positive I don't remember, but it will always be real. Okay. So we will come to eigenvalues once this topic is done. We will come to eigenvalues. Okay. Now there is another matrix known as skew symmetric matrix. Skew symmetric matrix is similar to symmetric matrix, but it has another property that this time my A transpose is not exactly equals to A, it is equals to minus of A. Previously in symmetric, A transpose was equals to E. So this time what will happen is the mirror image about your main diagonal elements will be negative. So let's say this is 1 2, this is minus 1 minus 1, sorry, minus 1 plus 1. Okay, so the mirror image must be negative. What do I see? Okay, sorry, for a skew symmetric matrix, right, also the diagonal elements must be 0, main diagonal elements must be 0. Okay, for a matrix to be skew symmetric. So I see the image about the main diagonal, this is minus 1, this is plus 1, right? So this will be A transpose minus so okay, give me 1 second now. Just give me 1 second. So if I take the transpose of this matrix, right, this will be 0 1 minus 1 0, 0 1 minus 1 0. So what is it? It is nothing but, if I take the minus sign common, right, if I take the minus sign common, this will be 0 minus 1 1 0. It is nothing but A. This matrix is nothing but A. So this will be minus of A. So that's how a symmetric matrix is formed basically. So first of all, your diagonal elements all must be 0, and your off diagonal elements all must be negative of each other. Here you see this is negative of this one, right? So these two properties they have to follow for a matrix to be skew symmetric. Again, this time if I take this on the left hand side, this will become A plus A transpose will be equals to null matrix. So this is again a property of a skew symmetric matrix numerically. So which is not a skew symmetric matrix. Whenever you have a non-zero diagonal, right, it will never be a skew symmetric matrix. If you ever have a non-zero diagonal 1 0 minus 1 1, it will never be a skew symmetric, because if you are taking the transpose and then making the negative sign, this will become minus, right? This will become minus. If this becomes minus, right, just hold on, if I swap the diagonal elements, this will be 1 0 1 minus 1. Okay, yeah, if I take negative common here, this will become minus 1 minus 1 1 0. So is this matrix A? No, because here I had 1, here I had a minus 1. So the diagonal elements actually changes. The diagonal elements actually changes. That is a problem if the diagonal element is non-zero. So that's why all diagonal elements must be 0, and off diagonal elements must be negative of each other about the main diagonal. Okay. So yeah, that is all what we have told you. So if a matrix is skew symmetric, right, then a raised to power 2n will be a symmetric matrix and a raised to power 2n plus 1 will be a skew symmetric matrix. How? So can I prove it? Remember, n is a positive integer. So if a matrix is skew symmetric, so a matrix is skew symmetric, A transpose equals to minus of A. So let's take example of this matrix itself, right? This one. This matrix is skew symmetric. So if I multiply by A again, if I multiply by A square again, so this will be 0 minus 1 1 0, and this will be A into A, right? So this will be 0 minus 1 1 0. So this will become 0 plus 1, that is 1. This will be 0 0, this will be 1 0, this will be 1 1 into minus 1. Yes. So this matrix is nothing but symmetric, right? A transpose will be equals to A. If you take the transpose, it will be same. If I again multiply, if I do A cube, like of course I will not be able to prove it formally here, it will take me some time. Okay, but if I, let's say I again cube it, if I cube it, what will happen? If I cube it, this will become again, this is my A square, right? So A cube will be A square into A. So A square is already calculated. Again I will multiply A. So if I multiply A over here, right, this will be okay, I can actually also prove it. I can also prove it actually. So let me show it actually. So first this will be 1 0 0 minus 1. A square is 1 0 0 minus 1, and your A is 0 minus 1 1 0, right? So if I multiply these two values, this will be 1 into 0 1 into 0. This will be minus 1 0. This will be 0 minus 1. This will be 0 0. Okay, 0 minus 1 minus 1 0. Okay, so that is what my A cube is. And is it skew symmetric? This should be skew symmetric. I'm making some mess up, right? Hold on a second. 0, this is minus 1, yes, then this is, oh, this, how is this? Just give me 1 second now. This is okay, this is symmetric, this should be skew symmetric. Messing up something. 0 minus 1 1 0. So 0 into 0 minus, oh sorry, really sorry, this will be minus 1 actually. I'm extremely sorry, this will be minus 1, yeah. And this will be 0 0, this will be 0 0, this will be minus 1, yeah, sorry, this will be minus 1 actually. So this will be minus 1 here. So this will be minus 1 into 0 0, minus 1 into minus 1, this will be plus 1, yeah, plus 1. So this, now I hope you can see like this. If I take the transpose of this, right, this will be negative of A, correct? Negative of A cube basically. So I can prove it formally here. So let's say I want to calculate A square, correct? So how will I calculate A square? It will be A into A. Now if I want to take the transpose of this, right, so A square is A into A. So what is A square whole transpose? A square whole transpose will be A into A whole transpose, or I can individually break the transpose. This will be A transpose into A transpose. Now A is a skew symmetric matrix. So if A is a skew symmetric matrix, I know A transpose will be minus A, correct? So I can break this, write this A transpose as minus A. So this will be minus of A into minus of A. So minus minus will be plus, plus A square. So A square whole transpose becomes A square. So this is nothing. If I assume that A square is some matrix B, So the equation that is written over here, that is B is equals to B transpose equals to B. B transpose is equals to B. So it is nothing but property of a symmetric matrix, right? And similarly, again if I do A cube will be A square into A, correct? A square into A. So what I can do, I can take the transpose of this. So A cube whole transpose, right, will be equals to A square whole transpose, that will be equals to A transpose into A square whole transpose. Now already I know this A square whole transpose value. What is it? It is simply A square. So this value is already A square, correct? Because it is a symmetric matrix. A square is a symmetric matrix. This will be A square. What is A transpose? A transpose is minus of A. So this will be minus of A cube. Minus of A cube. Okay. And so my A cube transpose is minus of A cube. That basically means it is a property of a skew symmetric matrix. It is a property of a skew symmetric matrix. Okay, so that's why odd power will always be skew symmetric matrix and even power will always be a symmetric matrix if my the power is even. If the power is even, then it becomes even symmetric. If it is odd, it becomes skew symmetric. Very good property to remember. Okay. Okay. If A is skew symmetric matrix, we can also comment about the determinant. If A is a skew symmetric matrix, we can also comment about the determinant. What will be the determinant? Determinant will be a if n is even, determinant will be a perfect square. If n is odd, determinant will be 0. Odd meaning, let's say I have a skew symmetric matrix here, A transpose equals to negative of A, right? And A is a 2 cross 2 matrix, A, B, C, D. Okay, A, B, C, D, 2 cross 2 matrix. And if it is skew symmetric, right, that means your A and D will be 0 and your B, this will be negative of each other. So what is the determinant over here? Determinant over here will be B square, which is a perfect square, right? Which is a perfect square. Similarly, if I have x, y, 0, 0, z, so this will be minus of z, so this will be minus of z, this will be minus of y, this will be minus of x. Okay. Now if you find out the determinant, right, it will come out to be 0. I can show you. So the first element, if I break the determinant with respect to the first element, it will be 0. So if I calculate the determinant right here, let me calculate the determinant. This will be, this will be 0 into 0, 0 minus z square. So this is 0 only. So I don't actually need to do it. X into, so if I am calculating this one, right, 0 into minus of zy, so this will become plus zy, and plus y into, again this will be plus xz and minus of 0, right, 0 into y, so this is 0, so xz. So the determinant comes out to be 0. So for a skew symmetric matrix of even order, the determinant will of odd order will the determinant will always be 0. That's why if it is odd, determinant is 0. If it is even, determinant will always be a perfect square. Determinant will always be a perfect square no matter what. Okay, so a question is there, so you have to find out the determinant of A. So directly I can say this is a skew symmetric matrix, so directly I can say it will be a perfect square. What will be the perfect square value? It will be 3 square, that is 9. Okay, determinant of this will be 9. You can calculate, you will get 9. Okay, so that is one property of skew symmetric matrix. Yeah, what about any other? So what is find out A square? So as it is a skew symmetric matrix, right, I know A square will be also what? A square will be simply a symmetric matrix and AQ will be a skew symmetric matrix. If they would have asked you what kind of matrix will be A square, it will be a symmetric, because if I multiply, like if the power is even, right, if the power is even, it becomes symmetric matrix. If A is a skew symmetric matrix, and if power is odd, like here, it will be a skew symmetric matrix. So this can be asked in exam. This can be asked in exam. Now let's come to the next one, that is orthogonal matrices. What are my orthogonal matrices? Okay, so an orthogonal matrix is a square matrix A if and only if its transpose is same as its inverse. If and only if its transpose is same as inverse. Okay, so A transpose will be equals to A inverse, or A transpose A will be equals to A into A transpose equals to identity matrix In. Okay, so yeah, that is the case over here. So basically the property of an orthogonal matrix is that if you multiply the transpose with the matrix, right, the resultant will be identity matrix. So order does not matter. First, if I multiply A into A transpose or A transpose into A, the result should be a identity matrix, then only the matrix is called to be a orthogonal matrix. So from this, right, from this equation I can actually get back to this one. So simply I know my A transpose into A is equals to I. So I can cross multiply by A inverse on both sides. If I cross multiply by A inverse on both sides, what will I get? This will be A transpose, A inverse, right? This will be A inverse. So basically from this we get that our transpose of the matrix will be inverse. The transpose of the matrix will be inverse for a orthogonal matrix. Okay, same you can derive from here as well. Okay, so this, right, this thing is valid only for a square matrix, because inverse exists only for a square matrix. But also orthogonality can be also for a non-square matrix. If A and B are non-square matrix, and then if they follow this equation, right, then if they follow this relation, then also A is called as orthogonal, but it is called as semi-orthogonal matrix. It is called as semi-orthogonal matrix. Then A is a semi-orthogonal matrix. Okay. Yeah. So in other words, how can I say orthogonal vectorically? Like how did this orthogonal came into picture? Why is this the name orthogonal? So if you remember one thing, that if I have two vectors, right, A, or let me name this as I plus j and I minus j. Are these two vectors orthogonal? How we used to find the orthogonality? We used to take the dot product. If I take the dot product, what will happen? So let me assume this vector as A vector and this is B vector. So if I take the dot product of this vector A dot B, it comes out to be 1 minus 1, right? I hope you know how to take the dot product. This is 0. So actually the vectors are orthogonal with each other. Why? Why? Because what is A dot B? A dot B is magnitude of A into magnitude of B into cos of theta, right? And whenever the angle between the two vectors is 90, then it is called to be an orthogonal matrix, orthogonal vector. Then those two set of vectors are called as orthogonal vectors. So here determinant of A is non-zero, sorry, magnitude of A is non-zero, magnitude of B is also non-zero, right, root 2, but dot product is coming out to be 0, so that means theta has to be 90 or odd multiple of 90, right? Then only the dot product will be 0. Graphically, how can I show it? So where is my I plus j point? I plus j vector? I plus j vector will be somewhere around here, I plus j, right? This is my I, this is my j, like this is my real and this is my imaginary part, ij. Okay, and where is my I minus j? Where is my I minus j? So I minus j is here. Okay. So this is my I minus j. So you see that the angle between these two vectors is 90. Angle between these two vectors is 90. So these two vectors are orthogonal with each other. These two vectors are orthogonal with each other. I hope this part is clear. This part is clear. Okay. So like if I take the dot product, it comes out to be 0, right? So that is the actual meaning of orthogonality. So in matrix format, what we do is we actually, let's say, write if I have a 2 cross 2 matrix, then I write row 1 and row 2. If the two rows, right, in I cap j cap format, so this is a I cap, like this will be my I cap and this will be my j cap component, right? So a1 I cap, b1 j cap, a2 I cap, b2 j cap. So if the dot product is 0, comes out to be 0, then we say that matrix is orthogonal. If the dot product is 0, then we say the matrix is orthogonal. Okay. So basically this, if I take the dot product of two rows, it must come out to be 0. That is also another property of a orthogonal matrix. Okay. So that is written over here. That also one more thing, so that is written over here, the dot product of any two rows or columns of an orthogonal matrix is always 0. If you take the dot product of either columns or either rows, the dot product will always come out to be 0 for an orthogonal matrix. Okay. What are other properties? Other properties is the determinant of an orthogonal matrix will be either 1 or -1. How? So I can see that my A transpose is A inverse. So if I take the determinant on both sides here, right, this will be determinant of A transpose, determinant of A inverse. So what is the determinant of A transpose? It is nothing but determinant of A, right? Determinant of A transpose and determinant of A are both are same. Determinant of A inverse will be 1 by determinant of A. So this will be determinant of A square equals to 1. So from this I can do determinant of A square minus 1 equal to 0. So I have two factors of A, determinant of A minus 1 and determinant of A plus 1 equal to 0. Okay. So yeah, that is what my like orthogonal property says. Determinant of A is equals to plus minus 1. Okay. So from here I can get the two solutions, either it will be 1 or -1. So that is another property of an orthogonal matrix. So all these are actually very important conclusions. From somewhere, from some point they can ask. Okay. So the dot product of two rows or two columns will be 0 for an orthogonal matrix. The determinant will be 1 or -1 for an orthogonal matrix. For an orthogonal matrix, but the transpose will be equals to inverse. Okay. And this is the actual definition of an orthogonal matrix. Okay. Now every orthogonal matrix, right, every row or column of an orthogonal matrix will always be an unit vector. Will always be an unit vector. So if you see, what do we mean by unit vector? Basically the magnitude of row 1, right, always will be equals to 1. The magnitude of row 2 will always be equals to 1. I hope you know how to calculate the magnitude of a vector, right? So what is magnitude of a vector? This will be a1 square plus b1 square. For a matrix to be orthogonal, the row or column must always be equals to 1 magnitude. So as I have shown you, that is what a unit vector is. Okay. So yeah. So if they ask you, right, if you have 4 options, and if they ask you if you have 4 matrices given and they ask you which out of this which one are orthogonal, you can eliminate few options by checking the magnitude of the rows or columns. Simply if one of the magnitude comes out, one of the rows of one of the matrix magnitude comes out to be not equals to 1, right, then that matrix will not be an orthogonal matrix. So that's how you can eliminate the options. So these conditions are actually pretty important. Now let's come to the other matrix, that is known as nilpotent matrix. We have already discussed what is null matrix. Okay. But what is a nilpotent matrix? Nilpotent matrix again is a square matrix such that the product of the matrix itself is equals to null matrix. So what does it mean? So basically, right, there is an example here. The matrix itself is not null matrix, but if I multiply twice, if I take the A square, right, it becomes a null matrix. So this matrix A is not a null matrix, but this has a special property. So how can I define that property? I say that this matrix is a nilpotent matrix of order 2. this matrix is a nilpotent matrix of order index or exponent 2. So because if I take the square, I get a null matrix, right? That's why this will be a nilpotent matrix of index or exponent 2. Okay, that as I have written it over here. The property, what is the property of a nilpotent matrix? If I take the determinant on both sides, right, this will be determinant of a raised to power k or determinant of a null matrix. Determinant of a null matrix is 0. Determinant of a raised to power k is determinant of a raised to power k. Okay, I can take the power later. This will be 0. So, and I know that determinant will be a scalar value, right? If a is real, determinant will be a scalar value. So basically determinant of a has to be equal to 0. Determinant of a has to be equal to 0, correct? If determinant of a is belongs to a real value. Otherwise I cannot multiply two numbers and not get a 0, right? That is not possible, because it is what? It is determinant of a into determinant of a into determinant of a. So at least one of the values has to be 0, right? Here at least one of the values has to be 0. Even if one of the values is not 0, then not real actually, any for any value. Even if none, like all of them are same values and they equate to 0, so of course it has to be 0. So the property of a nilpotent matrix is the determinant will always come out to be 0. If you see, the determinant here comes out to be 0. So the nilpotent matrix is a square matrix of order n cross n. Okay, the index of a nilpotent matrix having an order n cross n is either n or value less than n. Okay, and determinant will always be, so okay, one more thing is there. If it's a 2 cross 2 matrix, right, if it is a nilpotent matrix, then the index must be equals to or less than the order, that is 2. It cannot go beyond, it will not go beyond it. Okay, so that is another property. All the eigenvalues of nilpotent matrix are 0. What do I mean by eigenvalues? We'll come to it, but for now understand, like remember this property, all the eigenvalues of an nilpotent matrix will be 0. The determinant is 0, we have already discussed. The trace also will be always 0. You see, the trace of a nilpotent matrix will also be 0. So this is how you can eliminate the options of a nilpotent matrix. Just remembering one thing is enough. Okay, and nilpotent matrix of course will be non-zero because the determinant is 0. It is a non-singular matrix, correct? Let's come to the next type of matrix, that is idempotent matrix. What is an idempotent matrix? So an idempotent matrix is a square matrix which when multiplied by itself gives back the same matrix. So if I do a square, right, I will get back a. That is what my idempotent matrix is. This matrix is an idempotent matrix of order or index 2. Okay, so one or not index 2, sorry, I didn't, like there is no index here. Simply what is idempotent matrix? If I multiply the matrix by itself again, I will get back the same matrix. So there are few properties of idempotent matrix. So if I take the determinant of both sides, right, this will be determinant of a square equals to determinant of a, or if I take this determinant on the left hand side, this will be determinant of a into determinant of a minus 1 equal to 0. So either your determinant of a, determinant of an idempotent matrix will be either 0 or 1. If the determinant of an idempotent matrix is 1, that means it is a identity matrix, right? If it is 1, that means it is basically a identity matrix. Am I correct? Otherwise the determinant will never be, can it be 1? I'm just thinking of something. No, it can be 1 as well, right? But it will not follow that property. We have to check. Here I have shown you actually. Okay, yeah, ignore this part. Just understand that the determinant of an idempotent matrix will be either 0 or 1. Okay, just remember this thing. So okay, it will be a square matrix. Again, idempotent matrix will be a square matrix. The eigenvalues will be of the matrix will be 0 or 1. I have not explained you what is eigenvalues. We will come to that. The trace of an idempotent matrix is equal to rank of a matrix. The trace of an, so trace, right? Okay. Okay, we also don't know what is rank, so ignore all these points. Yeah, let's ignore these points. These are not important. We will discuss about this once we will discuss about rank and eigenvalues. Okay, now what is an involuntary matrix? Involuntary matrix involuntary matrix is a special kind of matrix. It satisfies the self inverse, that is A will be equals to A inverse. A will be equals to A inverse. So if I multiply by A on both sides, this will be A square will be equals to I. So that is the definition of a involuntary matrix. Okay. So what are the eigenvalues? What are the determinant of A? It will be plus minus 1. So if I take the determinant, it will become again same equation plus minus 1. So same like orthogonal matrix. Okay. So yeah. So these are few properties written. Just go through this ones. I mean, not super important, but you can go like have a read and try to prove it by yourself. Okay. So now, if A is an involuntary matrix, what can I comment about A raised to power n? What can I comment about A raised to power n? So let's break it down. If A is an involuntary matrix, that means what? A square will be equals to I, or basically my the property is A inverse is A, right? Or I can say A square is I. A square is I. Correct? So let's say what is my E raised to power 3. So A raised to power 3, if I multiply A on both sides, this will be A cube will be equals to A. So A raised to power 3 will be simply A. What will be my A raised to power 4? A raised to power 4 will be, if I again multiply A on both sides, this will be A raised to power 4 equals to A square, and A square is I, so this becomes I. So A raised to power 4 is I, A cube is A. Again if I multiply A, this will be A raised to power 5, and A raised to power 5 will be equals to A again, right, because I am multiplying by A on both sides. So the conclusion is that for even multiplication, right, for even power, it is coming out to be I. So if A is involuntary matrix, for even power it will come out to be I, for odd power it will come out to be A. For odd power it will come out to be A, for even power it will come out to be I. That's it. Okay, that is what my involuntary matrix is equals to. Okay. What is a periodic matrix? A periodic matrix is a square matrix where the number of rows and the number of columns are equal and satisfies a relation. Okay. So it is a square matrix where the number of rows and the number of columns are equal and satisfies a relation. So basically what will happen is that E raised to power k plus 1 will be equals to A. So or I can say E raised to power, it is not exactly, if k is 1, right, it will be just like a idempotent matrix. In idempotent matrix, what used to happen? A square equals to A. I get back the same matrix, right, if I multiply it by itself. But in periodic matrix, I don't know, k will be the period. So A raised to power k plus 1 will be equals to A. Basically k can be 2. So that means A cube will be equals to A. So with this, right, I can use many properties, I can derive many properties, and few GATE PYQs also have came in this using this property. Conjugate. Now let's come to the important part. What is a conjugate of a matrix? Okay. So what is a conjugate of a matrix? So what is conjugate of a simple complex number? Yeah, I have shown it. If I have a complex number 1 plus 2i, what is the conjugate? Simply I will change the sign of the imaginary part. I will just change the sign of the imaginary part of the complex number. That will be the conjugate of a complex number. Correct? Similarly, what will be the conjugate of a matrix? I will just change the imaginary portion of all the elements inside the matrix. So A conjugate, right, it is shown as A bar or AC. Okay, this will be 1, this is plus, this will become minus 2i, this is 2 plus 0i, so of course this will not change its sign, this will also not change its sign, only this will change its sign. So this is 1 minus 3i, so this will become 1 plus 3i. So that is what we mean by conjugate. Okay, now we have understood what is conjugate. We will discuss what is a Hermitian matrix. Hermitian matrix is similar to a symmetric matrix. In real domain, it is similar to a symmetric matrix. Okay. So what is a basically Hermitian matrix? Hermitian matrix is a square matrix which is equal to its conjugate transpose. Conjugate transpose. So what I will do, I will first take the conjugate and then I will take the transpose. That is what conjugate transpose means. It is defined in theta. It is called as tranjugate. Tranjugate, that is transpose and conjugate, that's why tranjugate. Okay. So what does it basically mean? Let's say I have this matrix. Let me take example. I have this matrix here 1 2, this 1 minus 3i, I think this same matrix, right, and this is 1 plus 3i. Okay, and is this matrix Hermitian? So to check it, first of all I will conjugate it, right. I will first check the conjugate of this matrix, right. So conjugate will be 1 plus 3i, 1 minus 3i, 2. Okay, and then I will take the transpose. If I take the transpose, what do I get? This will be 1 2, this will be 1 minus 3i, 1 plus 3i. Okay, so is it same as the initial matrix? Yes, this is same as the initial matrix A. Okay, so this matrix is same as the initial matrix, that means this matrix will be Hermitian. So for a matrix to be Hermitian, basically it's off diagonal elements, right? The real part must be same and the imaginary part must be conjugate of each other. What did I say? For a matrix to be skew Hermitian, the real part of diagonal elements, like I don't care what is in the main diagonal element. And one more thing, its main diagonal elements must be real. I think I have mentioned over here. Yeah, its main diagonal elements, whenever I equal to j, it must be real. If it is not real, right, you'll never get a Hermitian matrix. You will never get a Hermitian matrix. Okay. And your off diagonal elements, the real part are same and its imaginary part will be conjugate of each other. Imaginary part will be conjugate of each other. Okay. One more thing is there. If A is a symmetric matrix, right, it may or may not be skew symmetric, it may or may not be Hermitian. Okay, so I can take a example. Let me take a very small example over here, like 1 3 plus I 3 plus I 2. So this matrix is actually symmetric, right? A transpose is equals to A, but A theta is not equals to A. So that means it is not a Hermitian matrix, not Hermitian. Theta sometimes is also called as the H operator, Hermitian operator. So if a matrix is symmetrical, it does not mean that it will be Hermitian. Okay, that does not necessarily mean. So there are few properties of Hermitian. The diagonal elements of a Hermitian matrix will always be real. The diagonal elements of an Hermitian matrix are all real numbers. If A is a symmetric matrix with all entries to be real numbers, then it is obviously a Hermitian matrix. Okay, so if A is a symmetric matrix, now here, right, all entries were not real, but if A is a symmetric matrix with all entries to be real, then it will definitely be a Hermitian matrix. You can check the condition because there are no imaginary parts, right? It will follow the Hermitian rule. So if A is a symmetric matrix with all real elements, then definitely it will be a Hermitian. If it has complex elements, then I have to check. Okay. The non-diagonal elements of a Hermitian matrix are complex numbers and are always complex conjugates. You see, they will be complex conjugate. I forgot to mention, they will be complex conjugate of each other. The non-diagonal elements will always be complex conjugate of each other. Okay. The sum of any two matrix, Hermitian matrix, is always a Hermitian matrix. Okay, it is same like sum of symmetric matrix. So if I have two matrices that are symmetric, right, A transpose and B transpose, both are symmetric. So A transpose equals to A and B transpose equals to B. And let's say I am adding two matrices, right? Will this be symmetric? Yes. If I take the transpose, I can take the transpose inside. This will be A transpose plus B transpose, which is A plus B. So AB whole transpose is simply AB. So A plus B. So A plus B is also a symmetric matrix. So similarly, you can also prove it that sum of two Hermitian matrix will always be a Hermitian matrix. Okay, and the determinant of a Hermitian matrix will always be real. This is actually a very important property. This I am expecting a question to be asked from this. you will calculate the determinant will always come out to be real. Why? Because you see these are complex conjugate of each other, not here, right? These are complex conjugate of each other, so automatically only the real part will remain, the imaginary part will automatically be out of the picture. Okay, that's why this property is actually pretty important, that the determinant of Hermitian matrix will always be real, and the inverse of a Hermitian matrix will also be always Hermitian. Okay, so if A is Hermitian, all of this also will be Hermitian. You can obviously prove it, but I don't have time enough to, so I won't be able to prove it. Okay, so here I have given you a few proofs. You can go through this. You can see how these are all Hermitian. Okay, so okay, we have already discussed. Now, what is a skew Hermitian matrix? It is similar to skew symmetric, right? Just like as skew symmetric is to symmetric matrix, so skew Hermitian will be similar to Hermitian. So what will happen if I take the Hermitian operator and it comes out to be negative of A, it will be a skew Hermitian matrix. Okay, if I have this Hermitian operator and if I take the negative of A, it will be a skew Hermitian matrix. It will be a skew Hermitian matrix. Okay, so yeah, now what I can do, I can show you, right? I can show you how to check skew Hermitian. So what we will do is we will first of all take the conjugate. This will be minus 3i 0 minus 1 minus 3i 1 minus 3i, and then take the transpose. This will be minus 3i 0, this will be 1 minus 3i, this will be minus 1 minus 3i. Okay, so now what is it? It is nothing but the negative of this one, right? So this is equals to minus of A, so hence the matrix is a skew Hermitian matrix. For skew Hermitian matrix, the diagonal elements must be purely imaginary or 0. Okay, that these are the properties of a skew Hermitian matrix, that all the diagonal elements must be 0 or purely imaginary. The off diagonal elements, the imaginary parts must be conjugate of each other. You see, okay, sorry, okay, no. The imaginary parts must be equal, but the real parts must be negative. That's why I have shown you here that the imaginary parts, like it is basically the negative of the conjugate. Basically, off diagonal elements, the complex numbers will be negative of the conjugate. That's why the sign will change for the real part, sign will remain same for the imaginary part. Again, there are many properties for skew Hermitian you can read. So it is similar to symmetric matrix. So you remember the skew symmetric matrix property, that if I have even power, then it is a symmetric matrix. Even is a good thing, right? So that's why symmetric matrix. So if I have even power of skew symmetric, it will always be a symmetric matrix. You can also prove it, right? It will take you hardly 5 seconds, as I have shown you the proof, right? So you prove it. If you tend to forget it, you can prove it. Again, here they will follow the same relation, that even power of skew Hermitian will be Hermitian matrix. Even power of skew Hermitian will be Hermitian. Odd power of skew Hermitian will be skew Hermitian matrix. Same property. Previously, I forgot to tell you that for a symmetric matrix, right, I can break down my matrix into this format. Where is it? Here. Have I told you? Oh, I forgot to tell you actually here. Okay. So basically, if I have A matrix, right, A can be broken down into two parts, A plus A transpose by 2 and minus of A, A plus and A minus A transpose divided by 2. Okay, so this will be a symmetric matrix and this will be a skew symmetric matrix. Like, how is it possible? So if I break it down, right, this will be what? A by 2 plus A by 2 plus A transpose by 2 minus A transpose by 2, which is simply A, right? So this part is sorted, so it is equals to A. But how is this a symmetric matrix? You calculate, you evaluate this, right? This will be a symmetric. I can prove it to you as well. So let me name this matrix B equals to A plus A transpose by 2. So if I take the B transpose, what will I get? B transpose will be equals to A transpose plus A divided by 2, which is nothing but B. So B transpose equals to B. So it is a symmetric matrix. Similarly, you can do it here as well. Let me assume another matrix C. C equals to A minus A transpose by 2. If I take the transpose of this, right, if I take C transpose, this will be A transpose minus A divided by 2. So which is nothing but negative of C, right? So this will be minus of C. Okay, so this will be minus of C. So hence it is a skew symmetric matrix. So I can break down any matrix in a format of symmetric and a skew symmetric matrix. I can break it down. Okay, so yeah, similarly for a Hermitian matrix as well, you can do the same. For a Hermitian for in case of in case of a matrix, right, you can break a matrix in terms of its Hermitian format and a skew Hermitian format. So that is also possible. Any square matrix can be broken down into these two parts. Now we have few more matrix known as unitary matrix. It is just like orthogonal, but in the complex domain. So this time your A into A theta, not A into A transpose. A into A theta will be I, or A theta into A will be I. Okay, so that is what is called a orthogonal matrix. So these are the properties of a orthogonal matrix. You can read it again. If A and A are not square matrix, then they are called as semi unitary matrix. Now let's finally come to the next topic, that is solution of linear equation. That is, this is our original topic, right? We actually had to find out the solution. How can I find out the solution of linear equations? For that we studied a bit about matrices, different types of matrices. Now ultimately we'll come to the different ways in which I can find the solution of linear equations. So the first way is using Cramer's rule. So what is Cramer's rule? I will explain, don't worry. Mainly we use the concept of determinants for finding the solution in Cramer's rule. Okay, and also we can use matrix inversion method. I will explain what is matrix inversion method as well. Okay, then we have this Gauss elimination method. This is a general solution. This is generally used for larger set of equations. For smaller set, let's say it's a 3 variable equation, right? x1, x2, x3, x, y, z. Then for smaller set of equations we can use these two methods. For larger set of equations we will use these methods. And don't worry, in this chapter we will actually not find the solutions. That is not the task. We will only find the type of solutions, whether the solutions will be infinite, unique, or no solution. Okay, this is what we will do in this whole chapter. And the fourth one is the iterative method. In this there are two methods, Jacobi and Gauss-Seidel. These are actually not exact solution, these are approximate solution. This will be much faster, much easier to calculate. I mean calculations will be on the higher side, but this will be much faster than this one actually to compute. But these are approximate, these are not exact solution. Whatever solutions I will get from here, right, this will be my exact solution. Let's say x equal to 1, y equals to 2, z equals to 3 is a solution of the set of equations. Then in iterative method, in approximate value, x can be 1.01, y can be 2.1, z can be 2.9, something like that, right? It will not come out to be exact. And these methods will be taught to you in power systems, not here. And here also Cramer's rule and these methods I will show you, but this will not be used in this chapter. These will not be used, don't worry. Maybe Gauss elimination method can be used, and just we have to find the rank of the matrix. That is our task. Our task is to find the rank of the matrix. Okay, we don't have to find the solutions, but still I will tell you how to find the solutions. Let's say I have an equation like this, a11 x1, this equation, right? Let's say x plus y plus z equals to 3, x minus y plus z equals to 2, then 2x plus 3y plus z equals to 5. Okay, these kind of equation I have. So this can again be written in the matrix format like ax into b. What is x? X is a column matrix of the variables, column matrix with variables. What is a? A is the coefficient matrix. It will always be a square matrix. You see here, it contains all the coefficients of x, y and z. So in the first row I have 1 1 1. So here there will be 1 1 1. In this case it is e11 because these are my coefficients. In the second row I will have these coefficients. In the third row I will have these coefficients. Okay, and the final matrix B is also a column matrix. It will be a column matrix of constants. So here on the right hand side, whatever constant values are there, this will be present. The B matrix will be this. Now how will you calculate the solution using Cramer's rule? So this is how we calculate the solution using Cramer's rule. Is we find out the determinant dx1. This matrix is actually called as dx1 matrix. Why is it called dx1? So basically what we do is whatever elements were there in the x1, that is in the first column, we change it. We replace it with what? We replace it with the constant matrix b1, b2, b3. So I will replace it over here and that will give me my dx1 matrix. I will find out the determinant of the matrix and then divide by the determinant of matrix A, and that will simply be the solution of x1. That will be the exact value of x1. Now it seems very easy, right? That it is very easy. So basically just find out the determinant of these two matrices and my solution, I have got my value of x1. Very easy. But this is easy for smaller matrices, right? Calculating determinant actually takes a huge amount of computation power. For smaller matrices, it is very easy. When the size of the matrix will be increased, let's say a 5 cross 5 matrix, 7 cross 7 matrix, then calculating this determinant will be a difficult task. It will not be that simple. Okay, not that easy actually. Okay, so you can verify. In this case, what is our? I can take example. In this case, what is my A matrix? So let me take the example here. What is my A matrix? My A matrix in this example, whatever I have taken, I have just taken a random example, is 1 1 1, 1 minus 1 1, okay, 2 3 5, 2 3 5, sorry, not 5, sorry, 2 3 1. Sorry, this is all, sorry, this is also 2 3 1. Yeah, 2 3 1. Now this is my A matrix. What is my X matrix? X matrix is X Y Z. What is my B matrix? B matrix is the constant, right? So 3 2 5. B matrix is 3 2 5. So now what will be my x value? X value will be simply, okay, just give me 1 second. What is happening? I have to turn this off right here. So my x value will be equals to the determinant of this matrix. That is, I will replace my first column, right? Because it contains the x. In the first column, all the coefficients contain x. So I will replace that with my constant matrix. So this will be 3 2 5. This will be 1. Everything else will remain same, 1 1 1. Actually, I should have taken a smaller example. That would have been better. Okay, instead of taking a larger example, let me take a smaller example. Let me take 2 variable. Okay, I know you will be easily able to find out 2 variable, but let me take a smaller example. Otherwise, this will be a bit lengthier, right? So my coefficient matrix will be A matrix will be this. xy, this will be 3 2. Okay, so now we'll just replace this, right, and then divide by the determinant of A matrix. What is the determinant of A matrix? So determinant of A matrix, right, it is minus 1 minus 1 minus 2. So what is the determinant of this one? It is minus 3 minus 2, so minus 5 by minus 2, that is 2.5. Okay, what about y? So y will be, now I will replace wherever y contains. So y contains in the second column, right? So I will replace this column with my constant matrix. So y will be this. This will be 1 1 3 2 divided by determinant of A, that will be same. This will not change, denominator will not change, minus 2. So this will be 2 minus 3, that is minus 1 by 2. So that is minus 0.5. So is it satisfying? Of course it is, right? So 0.5 plus, sorry, not minus, sorry, this will be plus 0.5. 0.5 plus 2.5 will be 3. 0.5 minus 2, 0.5, sorry, 2.5 minus 0.5 will be 2. Okay, so yeah, we are able to solve using Cramer's rule. You will say, sir, this is so easy, why not use it? As I told you, right, as the order of the matrix will increase, the complexity will increase. Now there are few important conclusions from the Cramer's rule. There are few important conclusions from the Cramer's rule. If for some reason the determinant of A becomes 0, will any solution exist? I cannot comment. I cannot say whether any solution will exist or not. If for some reason determinant of A is equal to 0. So if for some reason determinant of A is equal to 0 and this determinant of x1, right, this matrix, determinant of this matrix, or determinant of x2 is not equal to 0, right, these are not equal to 0, then that means basically there will be no solutions. Why there will be no solutions? Simply because you cannot, like here I have dx1, right, then divided by d0. I cannot divide by 0 from a finite number, from a non-zero number. I cannot divide by 0. Okay, if all of them are non-zero, right, then there will be no solutions. But if either of them, right, if either dx1 or dx2 or any other determinant, right, at the top becomes 0, then it becomes a 0 by 0 format. If it becomes a 0 by 0 format, then you will have infinite solutions. Okay, if either your dx1 dx2 is equals to 0, right, and your determinant is also equals to 0, both are 0, it becomes a 0 by 0 format, so you will get infinite solution. It is same as saying the two lines are parallel with each other. Okay, this condition is same as saying two lines are parallel with each other. So that is what I have written over here. If either dx1 dx2 dx3 and obviously your determinant d is also equal to 0, that means you will have infinite solutions. Now if all of them are not equal to 0, if determinant of A is also not equal to 0 and all the other determinants are also, it does not matter actually, if these are equal to 0 or not 0, I don't care. Okay, ultimately this can be anything actually, yeah, sorry, this can be anything, right, this, if it is 0 or not 0, I don't care, this can be anything. That point I missed the point. This can be anything. If the denominator is not 0, right, then for sure I will get a unique solution. If the denominator is not 0, I will get a unique solution, basically only a single solution, single set of solution. If both either of dx1 and dx2 is 0, then I will get infinite solutions. How? I can show you an example. Let's take this example that I have x plus y equals to 3 and 2x minus 2x minus 2y equals to minus 6. So if either of the like you will see that you will find dx1, that will also come out to be 0 and your determinant also will come out to be 0, d. So if both are 0, then you will get infinite solution. If d is not 0, right, if determinant is not 0, then for sure you will get unique solution. Okay, that is what is written over here. So this solution, right, ax equal to b, this can have two cases. One is if determinant d is not equal to 0. If determinant d is not equal to 0, you will get unique solutions. If d is 0, that is the denominator, the determinant of the coefficient matrix is 0, then you have to check the condition that if none of the numerator determinant is 0, then you will get no solution. If all of the numerator determinant are non-zero, then you will get no solution. If at least one of the numerator is 0, then you will get infinite solutions. That is the conclusion of Cramer's rule. So what you will do, first of all, you will check the determinant of the coefficient matrix, because they will ask you the nature of the solutions, whether you will have unique solution, whether you will have no solution or infinitely many solutions. Okay. So you will check the nature of the, how can you check the nature? By checking the determinant. If the determinant comes out to be non-zero, then for sure you will say it has a unique solution. But if it comes out 0, then you check further. You check the individual determinants dx1, dx2, dx3. If at least one of the numerator determinants comes out to be 0, then you will have infinitely many solution, otherwise you will have no solution. Okay. So that is the conclusion from Cramer's rule. Now, yeah, that was about it. One more is there about trivial solutions. What do I mean by trivial solutions? Trivial solution means that all my solutions will be 0. Trivial means 0 solutions. Now 0 solution means, does not mean that I don't have any solution. No, it simply means I have 0 as a solution. It simply means I have 0 as a solution. Okay. How? So if I have this equation, right, x minus y equal to 0 and 3x plus 2y equal to 0, what is the solution? You will say, once you will find out the determinant of the coefficient matrix, it is not equal to 0, right? You will see determinant of the coefficient matrix is not equal to 0. But if you individually find out d of x1, right, you will see it is 0. Why? Because once you will replace this 0 with this one, so all of the column is 0. If the column of any matrix is all zeros, right, then for sure the determinant also will be 0. So dx1 will be 0. Similarly, your dx2 also will be simply equals to 0. So what are the solutions? So x will be equals to dx1, that is 0 upon determinant of a, that is 0. Y also will be equals to dx2, that is 0 upon determinant of a, that is some non-zero value, it is equal to 0. So when all my solutions are 0, then it is called as trivial set of equations or trivial solutions, because it is boring. All my solutions are 0 because it is boring, that's why it is called trivial solutions. I have trivial solutions, all solutions are my 0. Why? Because if you put any other value here, right, x and y, let's say I put x equal to 3, y equal to 3, it will satisfy this equation, but it will never satisfy this one. It will never satisfy this one. Okay. So that's why, like you will see, right, only x equal to 0 and y equal to 0 will satisfy both the equations. So you have a trivial solution at x equal to 0 and y equal to 0. Do I have any other solution? So if I multiply by 3 here, right, if I multiply by 3 and if I eliminate this will be 5y equal to 0. So y has to be equal to 0. Now if y equals to 0, x also has to be equal to 0. So you have trivial solutions. So just be careful regarding this particular thing, that if the constant matrix is all zeros, if the constant matrix is all zeros, right, constant matrix, where did it go? This, if it is all zeros, that means you will get trivial solution. If and only if your determinant of a is not 0. If determinant of a is also not 0, then, so if determinant of a is also 0, then you will get infinite solutions. How? Let me show you this. Minus x plus y equal to 0. Can you tell me what are the solutions? If I add these two equations, right, it will be 0 equal to 0, which is always valid. So for any values of x, right, and y, not for any, so for infinite values of x and y, these two set of equations will be valid. It is nothing but the negative of this one, right? So here my determinant of a is also 0 and my determinant of dx1, dx2, those things are also 0. Okay. So I hope this part is clear by you. What do I mean by trivial solutions? Now what do I mean by non-trivial solutions? Non-trivial solutions basically means that 0 is not a solution. X equal to y equal to z equal to 0 is not a solution. That is what non-trivial means. Okay. Now let's discuss few valid operations in rows and columns, because now we will discuss about Gauss elimination method. So we have to discuss what are few valid operations in rows and columns. So basically, if I make this matrix, right, from the equation set of equations, I am making this matrix. So I can write this equation first and this equation second. Is that valid? Yeah, no problem. You can write this one first, then you can write this one. So that's why I can also interchange the rows over here. If I interchange the rows, make sure you are also interchanging the rows over here in the coefficient matrix. Then everything will be valid. So interchanging of ith row and jth column will be totally valid. So basically what do I mean? Yeah, let me take a small example. Let's take x minus y equals to 3 and 2x plus y equals to 1. And if I form the coefficient matrix, this will be 1 minus 1 to 1. Okay, to 1, and this will be b will be equals to 3 1. Okay, so this is my coefficient matrix, and yeah, this is my coefficient matrix. Just give me 1 second. Yeah, and this is my constant matrix, and my x matrix is x comma y, right? So a x equals to b, this will satisfy. Now what I can do, I can interchange these, right? I can write 2y plus x equals to 1 and x minus y equals to 3. Will it change the solution of x and y? No, right? I can write this one first. So I can actually interchange the rows, but if you are interchanging the rows, right, make sure you are also interchanging the rows of the matrix B. I can interchange the rows of matrix A, but make sure you are also interchanging the rows of matrix B, because here, right, if I am swapping, if I am writing this one first, that means this also is written first. So don't mess it up. So if I interchange the rows, this will be 2 1 1 minus 1, B will now become 1 3, and x, will I interchange x and y? No. Still in the first column I have x, and the second column I have y. So x and y will not be interchanged. X and y will remain same, and still you will get back to your same equation. Okay. So yeah, this part is clear, that row operations are valid. Also, multiplying ith row by a non-zero number is also totally valid. That is what we do, right, during elimination. How we used to eliminate? So we used to multiply by 2 here, right, and then I used to subtract. So similarly in a matrix also I can multiply by 2, but if you are multiplying by 2 or any non-zero value, make sure you are also multiplying this matrix B, not only matrix A. Then it will not change the solution. Basically, valid row operations will be those row operations or column operations where the solutions remain same. Solutions will not change. That is our purpose. So addition of lambda times jth row plus ith, this is also valid operation. So what do I mean by it? So I'm multiplying this, then I'm subtracting this, right? That is like a addition. Subtraction is also another form of addition only. So this is a valid operation. Similarly here also it is a valid operation. So what I can do is I can multiply the first row by 2, right? This will be 2 minus 2, 2 1, and this will become 6. Don't forget, as you have multiplied by 2, this element also will be scaled. Okay, now I can subtract this row from the second row. So this will become 2 minus 2 0 3, and this will be 6 minus 5. Okay, so these are all valid, but this is not valid. This thing is not valid. So what you are doing is you are multiplying this row, right, jth row, by some value and then subtracting the k. So actually don't do this simultaneously, do step by step. First you multiply by k into j. Basically what I am doing is I am not telling you to do this simultaneously, like multiplying this row and then subtracting here, right? That is not like recommended. What am I telling? So here, right, let's say it is 2 minus 2, okay, or what was the matrix? Yeah, 1 minus 1, 2 1, 3 1. So what am I doing is I'm simultaneously multiplying this by 2, okay, and this also multiplying this by 3 or some 4 value, multiplying this row by 4, this row by 2, and then subtracting these two. You will say there is nothing wrong. Yes, there is nothing wrong, but what I will say is first do this multiplication, or first do this multiplication then subtract. Don't do them simultaneously. Something will be messed up in the constant matrix, right? Don't do this simultaneously. That is what I'm telling. Okay. Now, what are equal matrices? We have discussed what is an equal matrix. Equal matrices are those kind of matrices that when the elements, each elements in the matrix are same, that is called as a equal matrix. Now, what is a equivalent matrix? Equivalent matrix are those matrix where the number of rows and the number of columns are same. Corresponding entries can be made same using elementary transformation. So let me take an example. So 1 2 0 3, and this is 1, this is my A matrix, and this is my B matrix, 1 2 0 3. Okay, so A matrix are like this. A and B are equal matrix. A and B are equal matrix. Okay, I don't have space. Now, what about this matrix, right? So let me take example over here. A is equals to same, C is 1 2 1 5. Now, is A and C equal matrix? No, A and C are not equal matrices, but definitely what I can say is A and C are equivalent matrix because their number of rows and columns are same, and I can get my C, right, by doing some transformation. That is, I can add with row 2 row 1. If I do this transformation, I can add the 2 rows, then I will get my C. So these are actually called equivalent matrix. So knowing these terms is important. Okay, now we will solve, we will find the solution of set of equations using Gauss elimination method. With this we will understand the concept of rank. Okay, so I have to find the solution of these 3 equations using Gauss elimination method. Okay, so my A matrix will be equals to 1 minus 3 2 3 1 minus 2 1 1 1. Okay, this is my coefficient matrix, and we actually integrate this matrix, integrate coefficient matrix with the constant matrix. So we write the constant matrix in a same matrix. This is not actually called as a matrix, this is called as a augmented matrix because I'm augmenting 2 different matrices, because actually we don't because matrix contains similar objects, but here these are all coefficients of x, y and z, but this is just a constant term, this is not a coefficient, right? That's why I cannot directly write this in a matrix format, but this is called as an augmented matrix, and this will be helpful everywhere to find out the nature of solutions, whether my solutions will be real, infinite, or no solution. So now I have written this augmented matrix. Now we will eliminate elements in the augmented matrix in a systematic method. what will I do? I will simply first of all try to make I will try to eliminate this and this to 0. I will try to make, sorry, I will try to make this one and this one to be a 0, right? Basically, I will try to, my aim will be to make a upper triangular matrix. This is a matrix, so I will try to make my A matrix into a upper triangular matrix. That will be my target. Why? I will explain why. So to do that, first of all, I have to make these two elements equals to this element equal to 0, right? These two elements equal to 0 because it has to be upper triangular matrix. So all the non-zero elements can stay here. All these elements has to be 0. So how can I make this one 0? Or let us, first of all, we will try to make this one 0, okay? How can I make, or let me make this one 0. How can I make this one 0? Simply if I subtract this, right, I can make it 0. So what I can do, what row operation can I do? I can do row 3 can be changed to row 3 minus row 1, okay? So this will become, all other things will be same. So 3, 1 minus 2, this will be 0, this will be 4, this will be minus 1, okay? Of course, I am subtracting, right? So this also will be subtracted. So this will be 6 minus 4, that is 2. Don't forget. Okay. Now, what will be our next target? Next target will be to make this element 0. How can I make it 0? So what I can do? Okay. How can I make it 0? Okay. Actually, what I should have done? Okay. Now I will make this element 0. Okay. That will be my next target. Why, I will explain in a second. So how can I make it 0? If I multiply 3 and then subtract, right, from row 1. So row 2 can be changed to row 2 minus 3 row 1, okay? One minus 3, 2, 4. So if I multiply 3, right, this will be 0. This will be multiplying 3 and then subtracting. So this will be 10. This will multiplying 3 and then subtracting. This will be minus of 8. Multiplying 3 and then subtracting, minus of 10. This will be 0, 4, minus 1 and 2. Okay. So now what will happen is that now I will try to make this one 0, because now I can use these two rows, because these two elements are already 0, so they will not interfere with each other whatever I do, right? That's why the purpose was to make this 0, so that now I can make this element 0 using row 2. So what shall I multiply with row 2 so that this one will be 0? That is 4 by 10. So what I can do is R3 can be changed to R3 minus 4 by 10 into R1. Okay. So this will be one minus 3, 0, minus it. Okay, and if I do 4 by 10, right, this will be this will be 0. If I do 4 by 10, so what will this become? This will be 4 by 10, right? If I do 4 by 10, this will be 0.8 into 0.8 into, sorry, 4 by 10 0.4 into 8, 0.4 into 8 is 3.2. So I'm subtracting, so I'm adding 3.2 minus 1, so it is 2.2 basically. This will be 2.2 and this will be 4 by 10, so minus 4, so this will again become 6. This will be minus 10, this will be 4. Now this will be much simpler to solve. Now this has been converted into the upper triangular format in which we are actually trying to go this matrix, right? Upper triangular format. Now it is much simpler. Now what I can say, now I can come back to my original equation. So what is the original equation? That is, this will be multiplied with x, this will be multiplied with y, this will be multiplied with z, will be equals to this. So 0 into x, that is 0, 0 into y, that is 0, plus z into 2.2 equals to 6. So from here I will get the value of 6, z, that is 2.2 divided by 6 divided by 2.2, and I will replace it in this equation. So 0 into x, that is 0, 10 into y minus 8z. I know the value of z, I will put the value of z over here, that will be equals to minus 10, and I will get my value of y. Similarly, now finally I have x, y and z, so I can easily get the value of x. I know value of y and z, right? So I can easily get the value of x. Okay, I hope that part is clear, right? So yeah, so that is the case over here basically. Yes, that is the case. So this is basically nothing but the Gauss elimination method. It is called elimination because we are eliminating unknowns, right? We only, in the final row we only had z as unknown. So this format is sometimes also called as a row echelon format. I have converted this into upper triangular matrix. This is also sometimes called as row echelon format. Okay, I hope that part is clear. What is called as a row echelon format. So in Gauss elimination method, first we form the augmented matrix. Okay, first the augmented matrix is formed. Actually this can stay here itself, right? I don't need all these things. Just give me 1 second. Yes. So first we form the augmented matrix, then we convert the augmented matrix into row echelon format, and then we use back substitution to find out the value. Like we back substituted this equation and we found the value of z, then we found the value of y, then we found the value of x. So basically, right, this kind of format is called as this kind of format is called as row echelon format. Okay, so you don't need to go into the details of row echelon format, just understand this. We will calculate the rank of my augmented matrix while it is in this row echelon format, or in your head you can assume this to be the minimized format. Can I minimize it further? No. Can I make this coefficient 0? Can I make this 0? Not possible. Whatever you do, right, whatever row transformations or column transformations you do, you will not be able to make this element go to 0. So this element cannot go to 0. If this element is not able to go to 0, that means I cannot minimize it further. So this is the minimized format, and we will calculate the rank of this minimized format. If the rank is a certain number, we will discuss about that number. Then we directly, by understanding that number, right, we can directly say whether it will have unique solution, infinite solution, or no solution. Okay, so yeah, rank of A is known as this symbol, row of A. It is the number of non-zero rows in the row echelon format. In this row echelon format, how many non-zero rows I have? How many non-zero rows I have? 3. Right. After the minimized format, how many non-zero row I have? Non-zero meaning where all the elements are not zero. At least one element is non-zero. Here this element is non-zero. Here 2 elements are non-zero. Here 3 elements are non-zero. So the rank of this matrix will be 3. Rank of this matrix will be 3. Okay. Now what is nullity? Nullity is known as the total number of variables minus the rank of A. What are my total number of variables here? 3. 3 are my total number of variables, x, y and z. X, y and z, 3 are my total number of variables. Okay. 3 are my total number of variables, x, y and z. Okay. So Yeah. Now total number of variables 3 minus rank. 3 minus rank of A. So okay, 3. So what is the rank in this case? In this case it is 3, right? Because I don't have any all my rows are non-zero, so rank is 3. So 3 minus 3 is 0. Nullity is 0 in this case. What does it actually mean? It means I will get a unique solution. Whenever nullity is 0, that means I will get a unique solution. I will not get a null solution. Okay, so are we getting unique solution? Yes, z will be some unique value, y will be some unique value, and x will be some unique value. So this set of x, y and z are unique. I will not get any other set as a solution. Only I will have one solution. Okay, so it is also called as number of free variables. Why is it called number of free variables? I will discuss about that. Okay, or also it is called as dimension of the null space. What is null space? I will discuss about that. So what is rank? Rank is the rank of a matrix is equal to the number of linearly independent rows or columns, or in other words, basically the smallest minor whose determinant is non-zero. So basically what we will do to find out the rank of this matrix, right, 3 cross 3 matrix, what I will do, I will calculate the determinant of this matrix. If this determinant comes out to be 0, then rank is not 3, because whenever determinant is 0, right, if determinant is 0, determinant of a matrix is 0, that means that either the rows and columns are linearly dependent. I have told you, right, while explaining determinant, that rows or columns are linearly dependent. So if determinant is 0, that means rows and columns are dependent on each other, and if rows and columns are linearly dependent of each other, then definitely rank cannot be 3, because it is a 3. I have 3 rows and 3 columns. Rank cannot be 3 because out of the 3 rows, maybe 2 rows are dependent on each other. Rank is the number of rows or columns which are independent of each other. That's why rank cannot be 3, rank has to be lower than 3, right? In our case, we were lucky that our determinant was not equal to 0. That means all the rows are linearly independent. You cannot actually write one row in terms of the other row. You cannot do it. So that's why your determinant will come out to be non-zero. But if it comes out to be 0, then you have to identify which rows are dependent. Are all my rows dependent? So this, right, here I can take an example. 1, 2, 3, 2, 4, 6, 4, 8, 12. So here, right, these 2 rows are linearly dependent on the first row. So 2 times this gives me row 2, and 4 times row 1 gives me row 3. 4 times row 1 gives me row 3. Okay, 4 times row 1 gives me row 3. Okay, so yeah, that is the case. Over here, that is the case over here. Okay, so what is the rank? Rank will be actually in this matrix, it will be 1. How many linearly independent rows I have? Only 1, right? The other 2 are dependent on this row, right? Or I can write this row as well. So I can say this row is independent and these 2 are dependent on this row. Anything is okay, but we have only a single row that is independent. If I would have changed this to 5, right, then I would have had 3 rows that are independent. How can you check it? You can find out the determinant. If the determinant is coming out to be 0, non-zero, that means all the 3 rows will be independent of each other, linearly independent of each other. If it is coming out to be 0, then that means there is some relation. What is the relation? These 2 rows are dependent on each other, right? So rank cannot be 3, because these 2 rows are dependent on each other. So rank will be 2 in our case. For this matrix, the rank will be 2, because I have 2 rows that are independent. This row is dependent on this one, or in other words, you can say these 2 rows are independent and these 2 rows are dependent on each other. Whichever way you like, you can choose this one or this one. That's your wish. But ultimately they are the same, right? It is just 2 times. This is just 2 times this one, right? So sorry, this row is just 2 times the row 1. Correct? So I hope this part is clear, whatever I was trying to explain here. So rank, so I will tell you the shortcut to calculate rank. So here, right, if I have this matrix, how can you calculate the rank? simply first of all you calculate the determinant. You calculate the determinant. If you calculate the determinant, it is coming out to be 0. If it is coming out to be 0, that means few rows or columns are dependent on each other. So for sure, rank will not be 3. Rank will be less than 3. Because rank tells me the number of independent rows or columns. But as this determinant is coming out to be 0, then that means there has to be some row or column that are dependent on each other. So rank will be less than 3. Rank cannot be equals to 3. Okay, rank has to be less than 3. Rank cannot be equals to 3. Right? Now what next do I need to do? Next, how can I verify? Now you need to choose individual 2 cross 2 matrix. So you will choose this matrix. You will choose this matrix. You will choose this matrix. You will choose this matrix and check whether all these are non-zero or not. If any one of them becomes 0, that means rank also will not be 2. Rank also will not be 2. So here I have done the same thing, right? I check the determinant. This is non-zero. If any one of them comes out to be non-zero, then rank will be 2. You will stop there. Whenever your determinant will come non-zero, you will directly stop at that point. If your determinant ever comes non-zero, you will directly stop at that point of time. Let me take another example. Okay. Let me take I've written it, so I will take another example. So let me take this example, right? So here if I have this matrix 1 2 3, this will be -2 5 6, and this will be 0, this will be 9, this will be 12. Okay, so this is my matrix A, and now I want to find the determinant. So now if I want to find the rank of this matrix, so if you calculate the determinant, you will see you are getting 0. Okay, because I have chosen the numbers as such, there is some dependency, right? Now I will find out the rank of the 2 cross 2 determinant of the 2 cross 2 matrix. So is this 0? This is non-zero. This is coming out to be non-zero, right? 5 plus 9 comes out to be 5 plus 4 comes out to be 9. So which is non-zero. So rank will be 2. So there will be 2 rows that are independent of each other. How? So my row 3, right? Row 3 is basically combination of row 1 and row 2. So row 3 is linearly dependent on row 1 and row 2. Also you can also say row 1 is linearly dependent on some constant C1 into R3 and some constant C2 into R2, whichever way you like, but at least there is a dependency on a row that is dependent on the other 2 rows, and these 2 rows are totally linearly independent. You cannot actually you cannot write row 1 in terms of as a function of only row 2. That is not possible. Sorry, I'm cutting the screen. Yeah, you cannot write row 1 as a function of only row 2. That is not possible, right? So they are independent. So what are the independent number of rows or columns in this matrix? 2. That's why the rank will be 2. So that is what I've told here. Find the determinant of A if A is a square matrix. Actually rank is defined for a non-square matrix as well. So if I have a matrix like this, right? 0 1. What is the rank of this? The rank of this is simply 1. Why? Because can I write this? This is column 1, this is column 2. Can I write column 2 as a function of only column 1? Yes. Column 2 is 0 times column 1. Right? That is smart, right? So column 2 is 0 times column 1. So yes, I can write column 2 in terms of column 1. Definitely then the rank will be 1, because then I will have only a single element left, right? Single element left, that is 1. Right? Okay. So this rank will be 1. Now what about if I have here 0 0? What is the rank? In this case the rank will be actually 0. So previous case, right, what you will do is you will first of all check which is lower, like what is the dimension of this matrix? 1 cross 2, right? And I can write my column 2 in terms of column 1. by doing 0 times 1. Then I will check the determinant of individual elements, right? So if I check the determinant of this element, what is the determinant of a single element? 1. This is 0. So a element has a non-zero determinant, so the rank will be 1. Okay, because I am checking the determinant of single elements. But if this was 0, then what is the determinant? What is the determinant of this element? 0. This element also 0, right? So I don't have a single element whose determinant is non-zero. That means rank equals to 1 also is gone, right? It will be somewhat lower than 1. Minimum value of rank can be 0. So rank is 0. So there are no elements that are linearly independent because it is a null matrix, right? It is completely a null matrix. So the rank of a null matrix will always be 0. Okay. Similarly, I can choose this one. Let's say I have 1 2 1 5 3 4. Okay. What will be the rank of this matrix? I have 2 rows and 3 columns. What will be the rank of this matrix? Okay. So you will say, sir, can I write my column 3 in terms of column 2 and column 1? You will always be able to write it. You will always be able to do it actually. So here how can I do it? Basically? Okay. So basically what do I need to do? 1 2 into C1 some constant plus C2 into 1 5 must be equals to 3 4. So this will be C1 plus C2 equals to 3 and your 2C2 plus 5C1 will be equals to 4. You will solve this, you will get the value of C1 and C2. So bottom line is you can always define the third column as a function of the previous 2 columns because you will get this unique solution equation. Okay. So whenever you have a rectangular matrix, the rank will be lower than the small rank will be, the maximum value of the rank can be the lowest value of the size. What is the lowest value of the size? That is 2, either row or column, whichever one is lower. So in this case number of rows is lower, so rank has to be less than or equals to 2. It cannot be more than 2. Okay. So you can simply eliminate this column. You can only check for this particular matrix. Now you check your determinant method, that is 5 minus 2, that comes out to be non-zero. So definitely the rank will be 2. So that's how you basically solve for rank. So the steps I have told you, that you just go on till you get a non-zero determinant. As soon as you will get a non-zero determinant, you will stop there. That will be my value of rank. So the size of that non-zero determinant matrix will be my rank basically. Okay. So I hope that part is clear. Yeah, here. So minor also I have explained. I don't think we have to explain minor much. So let's do this example. Let us find out the rank of this matrix. Okay, what will be the rank of this matrix? So first of all I will find out the determinant of A. So before doing the determinant of A, right, you try to make as many zeros as possible. You try to make as many zeros as possible for your easier computation. So what I can see is I can actually, if I multiply 3, right, and then subtract, this will be all 0. If I multiply 3 and subtract this one, this also will be all zeros. So not 3. If I multiply 2 and subtract, this will be also all zeros. I think we have done this already. So this will be 1 2 4 0 0 0 0 0 0. So determinant of A will be 0. So definitely rank will not be equals to my 3. Rank will be something lower than 3. Okay, rank will be lower than 3, right? Now I will go and reduce this matrix, right? If I find out the determinant, this also is coming out to be 0, this also is coming out to be 0, all these are 0 anyways. So again for 2 cross 2 matrix as well, the determinants are coming out to be 0. So rank of A cannot be equal to 2, rank of A has to be less than 2. So now if I what is the possible values of less than 2? 1 or 0. So I will check the determinant of 1 cross 1 matrix, that is each element. So if I check the determinant of this, what is the determinant? 1. If I check the determinant of this, what is the determinant? 2. If I check the determinant of this, what is the determinant? 4. So I am getting non-zero determinant. So definitely, whenever, as soon as I will get a non-zero determinant, right, I will say the rank of A will be that size of the non-zero determinant, that is 1 cross 1, that is 1. Okay. So rank of A will be 1 in this case. Can I say it in a textual format? What does rank of A 1 means? That means there is only single row or column that is independent. Is it true? Yes. This row is independent, right? This row is independent. All these two rows are dependent on the first row. Correct? That's why the rank is 1. Okay. So these are the properties of rank. Elementary operations, like proper elementary operations, do not change the rank of a matrix. Rank of row matrix will always be equals to 0 or 1. What do I mean by row matrix? Row matrix means I have only a single row. So this is a 1 cross 4 matrix, right? So I can write all these elements in terms of my first column element. So this will be 0, 0, 0. So what is the rank? Rank is 1, right? Rank is 1. So that's why rank of row matrix is 1. Similarly, rank of a column matrix will be 1. Rank of identity matrix will be n, because if you see, all my rows are independent. If I multiply 2 and then subtract or add, I will not be able to make a row of zeros. So my main purpose to check dependency between the rows is to make row of zeros or column of zeros. Can I make a row of 0 here? No. So definitely all the rows are independent of each other, linearly independent of each other. Then the rank will be simply the size of the identity matrix, in this case 3. Okay. The rank of a scalar matrix also will be n. Scalar matrix meaning something like this, right? So 3 0 0 3 0 0 0 0 3. So this also will have rank of 3 only, because all these rows are independent of each other. The rank of a n cross n non-singular matrix will be always n. What does a non-singular matrix mean? Non-singular matrix means whose determinant is not equal to 0, and if its determinant is not equal to 0, it is called as a full rank matrix. That is, the rank is equals to size of the matrix. So if A is a 3 cross 3 matrix, rank will be 3. If A is a n cross n matrix, rank will be n. Okay. So from this property also we can say that rank of A will be equals to rank of A inverse, because if inverse exists, that means determinant of A is not 0. That means it is a full rank matrix. That means A and A inverse both will be same, rank will be same, and rank of adjoint of A also will be same. Okay. All these properties are found from the conclusion that determinant of A is not equal to 0. If determinant of A is not 0, it is a full rank matrix. Okay. Now, if all the elements of a matrix are equal and not equal to 0, then the rank of the matrix is 1. Okay. Here. So if all the elements in a matrix, right, are equal, so let's say this is 1 1 1 1 1 1 1 1 1, then the rank of the matrix will be 1. How? So this will be basically, I can subtract this row and this row, right? So this will be 1 1 1 0 0 0 0 0 0. So here all these two rows are gone. So these two rows actually were linearly dependent on the first row, or you can say row 2 was linearly dependent on these two rows, or whatever you want to say, right? Ultimately, I have only a single row that is totally independent, right, which is non-zero. These two rows are totally 0. So what is the rank? Rank is 1. So whenever all the elements of a matrix is equal, rank will always be equals to 1. If all the elements of a matrix are 0, then the rank will be 0. It is simply a null matrix. For a null matrix, the rank will be 0. If a matrix with all the rows or all the columns are proportional, then the rank is 1. What does it mean? What do you mean by proportional? So basically it means that this is 1 1 1 2 2 2 4 4 4. So all these elements, right, are proportional to row 1. These elements also are proportional to row 1. So what is the rank? Rank is 1. Only one row I have which is independent. Okay. So a matrix is a full rank matrix if the rows and columns are linearly independent. Otherwise it is a rank deficient. Full rank meaning that all the rows or columns are independent, that is determinant of A will not be equals to 0. If determinant of A is not equal to 0, it is a full rank matrix. Okay. The rank of a skew symmetric matrix cannot be equals to 1. This is a kind of a property. No need to remember it. Okay. You can verify it. So if I have a rectangular matrix, right, of m cross n, the rank of A will always be less than or equals to minimum of whichever, either number of rows or number of columns. Whichever one is minimum, it will be that. I have already proven it to you, right? Also, one more property, rank of A into B and rank of B into A is always equal, and this is a very important property. Questions have been asked from this property, right? Rank of A into A and B into A are equal if AB and BA both exist. Okay. Also, rank of A will be same as A transpose, A into A transpose, right? Because this determinant also will be somewhat similar, and if I take the Hermitian, if I multiply A into A theta, all these ranks will be same. Okay, all these ranks will be same. I can use this property, simply use this property, right? Rank of AB will be equals to rank of BA. So this is actually a very important property. Make sure you remember this property. Okay. Okay, this has already been discussed. Also, one more thing, if A and B are row and column matrix respectively, then rank of AB will be less than or equals to 1. What do I mean? So if I have a row matrix here, right, any random value x, y, z, a, b, c, this is a 1 cross 3, or let me write this one last. Three cross 1 and 1 cross 3 matrix. So it will become a 3 cross 3 matrix, right? But actually its rank, right, will be always 1, or like less than equal to 1. It can be 0 as well. How? Because what is the rank of this? Rank of this matrix, right? This is a column matrix, it is 1. What is the rank of this? Rank of this matrix is also equals to 1, right? Pardon my handwriting, like I'm just doing in a hurry. So rank of this matrix is also 1, rank of this matrix is also 1, and we know the rank of if I am actually just hold on a second, we know this thing, right? Okay, if I'm multiplying A into B, I'm getting a 3 cross 3 matrix. This is my A, this is my B, and we know rank of AB is same as rank of BA. So now if I multiply B into A, what will be the size? So I'm doing 1 cross 3, that is row first, then a column, right? What is the size of the column? It is 3 cross 1, right? 3 rows 1. So what is the size of the resultant matrix BA? It is number of rows, number of columns, that is 1 cross 1. So it is only a single element. And what is the rank of BA? It is the minimum of minimum of rows and columns. Maximum value of this rank can be 1, right? So rank of BA has to be less than or equals to 1. That is, it has to be less than or equals to size of the matrix, right? So, and we know rank of BA is same as rank of AB as discussed from this property. So I can say that rank of AB also has to be less than or equals to 1. So that's how you can prove that rank of AB will be less than or equals to 1, even though you are saying that we will get a 3 cross 3 matrix, but without even doing any computation, I can directly say the rank of AB will be less than or equals to 1. Okay, so this property is actually very important. Please make a note of it. There are a few more properties. Rank of A plus B. The rank of A plus B will be less than or equals to, I cannot say exactly, less than or equals to rank of A plus rank of B individually. Again, now this is another property, rank of A minus B. Rank of A minus B will be greater than or equals to rank of A minus rank of B. So not that important, this property is not that important. Okay, this is an important property. And again, this one is also a very important property. Rank of A into B will be less than, like rank of A into B is same as rank of B into A. Okay, also it is less than or equals to minimum of rank of A and rank of B, right? So whichever one is minimum here, right? Rank of A into B will be minimum of rank of A into rank of B. So what is rank of A? 1, right? It is like a row matrix. So it is a column matrix, and rank of B is also 1. It is a row matrix. So that's why rank of AB also will be minimum of rank of A, rank of B. This is also very important property. This can be asked in questions. Okay. So yeah, already discussed the rank of, if rank of A and rank of adjoint of A are equal. So if rank of A is n, rank of adjoint of A will be n. Okay. Now there are few properties. If rank of A is n minus 1, then rank of adjoint of A is 1. So we can actually derive it. How can you derive? So what you can do, if rank of A is n minus 1, right, what does it mean basically? Rank of A n minus 1 basically means that my determinant of A is 0. Correct? And what is my adjoint of A? Okay, adjoint of A will exist actually. Adjoint of A will exist. But currently I don't have the proof. Like there are few proofs. So like you can go and prove this. We don't have the time for proof because we are already exceeding our time. So if you find out, right, you will see that all the other rows or columns are linearly dependent on one of the rows or columns. Okay. So if ever your rank of A, like let's say I have a 3 cross 3 matrix, right? A 3 cross 3 matrix, and its determinant is 0, that means its inverse does not exist. If its inverse does not exist, right, then your rank of the adjoint matrix, right, rank of the adjoint matrix will always be less than or equals to n minus 1, that is size minus 1, that is 3 minus 1. Okay, that is 2. Rank of adjoint of A is 2. Okay, so let's do few examples. So let's find out the rank of this matrix and this matrix, right? So first of all, what I will do, I will find out the minimum number out of the rows and columns. What is minimum? 2. So I will only consider 2 columns. I will neglect the other column. Correct? So rank will be, first of all, I got this information, the rank will be less than or equals to 2. It cannot be more than 2. Now I will find out the determinant of this 2 cross 2 matrix. I see it is non-zero. So rank will be 2. That's how easy it is to find out the rank. Okay. Again here, right, here what is the size? Size is 3 cross 2. So again rank will be less than, rank of A will be less than or equals to 2. Okay, rank of A will be less than or equals to 2. Okay, so what about the yeah, let's check the determinant. So if I check this determinant, again it is coming out to be non-zero, right? So again this matrix also will have rank of 2 because one of the smaller 2 cross 2 matrix has a determinant not equal to 0, so rank will be 2. Okay, you can check, you can cross verify, it will be 2. So how can you cross verify? You check the 2 columns, right? The 2 columns are actually linearly independent of each other. Here also if you see, the 2 rows are linearly independent. I cannot write row 2 as a scalar multiple of row 1, not possible. You will not be able to do it. Here also you will not be able to write your column 1 as a scalar multiple of column 2. You will just simply not be able to do it, right? So that's why the rank will be 2. Directly you can say, or using our method also you can say. Okay, whichever one is suitable by you. That's how you find out the rank. Now rank is actually pretty important to find out the nature of the solution of equations. So we will discuss about that only. So now we have understood how to find out the rank. Now we will discuss the solution of linear equation. So there are actually 2 kinds of system of linear equation. One is the homogeneous equation, another one is the non-homogeneous. In homogeneous, basically the constant term, right, on the right hand side are all zeros. You can see this is a homogeneous set of equations. This is a non-homogeneous set of equations because all the constant term are not 0. Even if one of the constant term is non-zero, then it becomes a non-homogeneous set of equations. Homogeneous meaning same, non-homogeneous meaning not same. They are not all 0. That's why. Okay. So that is what my homogeneous, that is the difference between homogeneous and non-homogeneous equation. And also remember this thing, that our system of linear equation can have 3 outcomes: no solution, infinite solution, unique solution. If I have no solution, then the set of equations are called as inconsistent set of equation. Why am I giving this much emphasis on the names? Because in the question they will play a game with the names itself. You will not, in linear algebra, you will not be able to understand what are they talking about. What are they talking about? So you must know, you must understand what does each word means. So whenever the set of linear equations will have no solutions, that means those set of equations are inconsistent because they don't give out any solution to me, right? If I have either infinite solution or unique solution, then those set of equations are called as consistent set of equations, because at least I'm getting some solutions. Even though those are not unique, but I'm getting many solutions, but at least I'm getting some solutions. That's why these are called as consistent set of linear equations. Okay, already matrix mapping is already taught to you. This is how I do the matrix mapping. I think all this have been already discussed. Okay, so now actually let's come to the conclusion. I think the conclusion is here itself. Yeah, the conclusion is here itself. So the matrix that I will form, right, A is a coefficient matrix and A colon B is called as a augmented matrix. The matrix that includes both the constant matrix and the augmented matrix. Okay, now if the rank of A matrix and A colon B, the augmented matrix, right, both are not equal to each other, then we will have inconsistent set of solutions. And whenever we have inconsistent set of solutions, that means basically our solution, like we will not have any solution, no solution. So basically what do I mean? Let's say I have two variables, right, x minus y equals to 2 and x plus y equals to 3, and what is the coefficient matrix A? Coefficient matrix A will be 1 minus 1 1 1. And what is my matrix B? My matrix B is simply 2 3. Now what we will do is we will first of all check the rank of A matrix, right? In our case it is not it is basically 2, right, because determinant is not equal to 0, so rank of A is 2. Then I will check the rank of A colon B. What is it coming? What is A colon B? 1 minus 1 1 1, and this is 2 3, right? How do I check the rank? Simply you can check, I have two rows, right? So what is the size of this matrix? 2 cross 3. So rank, maximum value of rank can be 2. Are these two rows independent? Yes, they are. These two rows are independent of each other. You can see these two rows are independent. So rank of A colon B is also equals to 2. That means my solutions will be consistent, either infinite or unique, but we will not have inconsistent set of equations, right? When will that happen? That might happen, let's say, when this is, let's say, 3 x minus y equal to 3. Now this becomes also minus 1 and this becomes 3. So in this example, what is the rank? Rank of A is actually 1, right, because this determinant is 0 and I have a 1 cross 1 element that is non-zero, so that's why rank of A will be 1. Now what about rank of A colon B? Rank of A colon B, this is negative, right? Are these two rows independent? Again, these two rows are independent, because if you do this operation that row 2 equals to row 2 minus row 1, right, that will make these two elements 0, but this will still be non-zero. So if I have a non-zero element in a row, right, then that is also considered as a independent row. So two rows will be independent. So still the rank of A colon B will be 2. Rank of A colon B is 2, rank of A is 1. That means these are not equal. That means we don't have any solution, as can be seen from here itself, right? If you try to solve it by method of elimination, what you will get? You will get 0 equals to 1 or 0 equals to minus 1, right? If I subtract this equation, right? If I subtract this equation, you will get 0 equals to minus 1, which is not possible, correct? So whenever your rank of A and rank of AB are not equal, you will get no solution. Your set of equations are inconsistent set of equation. If this condition is not there, if rank of A and rank of A colon B are equal, then you have two options, right? Then you have two outcomes. Then you can have two outcomes. One is unique solution, another one is infinite solution. How to check that? So now, if the rank of A and A colon B are equal, and if it is equals to the number of unknown variables, right? In this case, what was my rank of A? 2. Rank of A colon B, like if I now remove this negative sign, rank of A colon B is also 2. Rank of A is also 2. Now both of them are equal. If both of them are equal, I will get a unique solution. And what is it equals to? It is equals to the total number of variables. How many variables I have? I have 2 variables, right? Here I have 2 variables. So if it is equals to the number of variables, that basically means I will have unique set of solutions. Unique solutions. Okay? Unique solutions. Now what is this trivial solution? I will explain, don't worry. What is this trivial solution? I will explain that. Trivial solution will come later. We will discuss about that. I will have unique solution, and if rank of A is equals to rank of AB, but it is less than number of variables. How can it happen? So I can give you an example. Yeah, if I do this -1, so then what does my rank of A becomes? Rank of A again becomes 1, right? And I have to do this -2 as well. This will be -2. This will be -2. Again, are these two rows independent of each other? No. If I just simply multiply a -1, I will get my row 2. So these two rows are dependent. So rank of A colon B also becomes 1. So now, even though rank of A and rank of B both are equal, right? Rank of A and rank of A colon B both are equal, but it is less than the number of variables. I have 2 variables, it is less than that. So I will have infinite solutions. So if you try to solve this equation, right, you will get simply 0 equal to 0, like infinitely many overlapping solutions. So that's why this case is considered as the infinite solution. How can you verify? Whenever your determinant of A will be equal to 0, then as soon as your determinant of A is 0, right, you will check the rank of A colon B. If the rank of A colon B is also coming out to be same, then we will have infinite solutions. If the rank of A colon B is not coming out to be same, if it is a full rank matrix, then definitely you have no solutions. Okay. Now let's come to the fact about trivial and non-trivial solutions. What do I mean by trivial and non-trivial solutions? Okay. Trivial solution means if whatever we discussed, these are all for non-homogeneous equation. If I have homogeneous set of equation, right? So in homogeneous set of equation, my B, right, B matrix is simply 0. In homogeneous set of equation, my B matrix is simply 0. So if B matrix is simply 0, right, that column is always 0. So it will not add anything with the rank. So what do I mean? So let's take a very basic example, right? So let me take this example: x minus y equal to 0, x minus y equal to 0, x plus 3y equal to 0. So what will be the coefficient? 1 minus 1 3. What will be the B matrix? 0 0. Okay. Now what is the this is my A matrix. What is A colon B? A colon B will be basically 1 minus 1 1 3 0 0. Now will this ever add anything with the rank? No. Right? This will never add, because this element is always like same as this element, right? This will not change anything. So ultimately, like what you will see, what you will observe is you are getting a column of zeros, right? So it will not change anything to the rank of my matrix A. So rank of A colon B will be same as rank of A. This will always be valid for a homogeneous set of equation. Rank of A colon B will always be equal to rank of A. So from this conclusion, right, the conclusion is, if we have homogeneous set of equation, if I have homogeneous set of equation, then there is no possibility to get no solution. You will never get no solution. That is the beauty. So because this condition will never come, because your rank will always be equal. You see, right, this column of zeros will not make any change, right, to the rank. Only I will check the rank using these two columns. So it does not make any change to the rank. That's why we say for homogeneous set of equations, my solutions will be either infinite or unique solution. I don't have any chance to get no solution. There is no possible way to get no solution. That is not a possibility. Now you will get infinite solution if the rank of a colon b is less than the number of variables, or rank of a is less than the number of variables, right? In this case, no, it is not. If I find out the determinant, it is not 0, so we will get unique solution. And what is the solution? The solution is simply 0, 0. So if you are getting in a homogeneous equation, right, if you are getting unique solution, that is the determinant is not 0, then always the solution will be 0, 0. X equal to 0, y equal to 0. You see, x equal to 0, y equal to 0 will be solution. So for any homogeneous equation, x equal to 0, y equal to 0, z equal to 0 will always be a solution, because the right hand side is always 0. So if all the elements on the left hand side is also 0, then 0 will be equal to 0. So this, right, x equal to y equal to 0 is called what? I have told you in the starting, right? This is called as a trivial solution. Trivial solution, boring solution, right? X equal to 0, y equal to 0. This is boring. So if I have unique solution in homogeneous set of equation, that means the solution is trivial. The solution is trivial. So that's why we call it trivial solution. This is only for homogeneous equation, because only x equal to 0, y equal to 0, z equal to 0 will be a solution. That's why it is called as trivial solution. If we have infinite solution, how can I have infinite solution? If I can make this something like this, right, then you will see you will have infinite solution for any value, like not for any value. Whenever my x equals to y, like x equals to 0, 0 is solution, that is totally fine. X equals to 1, y equals to 1 also will be a solution. You see, x equal to 1, y equal to 1 also will satisfy these two equations. But previously, right, if you try to do that, previously what was the equation? I think this was minus 3y or something, right? Sorry, plus 3y. Now if you try to put x equal to 1, y equal to 1, it will satisfy this equation. But will I satisfy this equation? No, it will be 4 equals to 0. It will not satisfy. So if the determinant is 0 for a homogeneous set of equation, then the solution will be non-trivial. That is, I will get infinite solution. Non-trivial meaning non-zero solutions. Zero solutions will also be there. Like this is a trivial solution, right? X equal to 0, y equal to 0 is a trivial, is a boring solution. I already know for every homogeneous equation, x equal to 0, y equal to 0, z equal to 0 will always be a solution. I already know that. You are not saying me anything new. You are saying the trivial thing, right? But if this determinant is 0, that means other solutions are present. That means we have non-trivial solutions. Okay, that means we have infinite solutions. So please, this slide is the most important one of this whole chapter. This slide is the most important one. If you did not understand, go back and rewatch it again. Okay, repeat and rewatch it again. Okay, I hope that is clear. So same thing I have written it over here. So another conclusion is there. If determinant is not equal to 0, right, for a if determinant is not equal to 0, right, we will have only unique solution. That is the only possibility. If determinant is not equal to 0, because you see, out of these three cases, right, only on this case we have determinant not equal to 0. For the other two cases, if determinant is equal to 0, then I need to check whether I have infinite solutions or no solutions. Okay, these three things we have to check. So let's do a very basic example. Pause the video and try out this question. Let's solve this. So here, what is my coefficient matrix? It is like a 5 variable. So calculating determinant for a 5 variable matrix will be very difficult for us. So we will actually solve it using a different way, using the rank method, right? So what is my coefficient matrix? My coefficient matrix, this will be 1, 2, minus 2, minus 1, 1. Okay, 1. Then 2, 4, minus 4, 3. Okay, one thing is 0 over here. What is 0? X4. The coefficient of x4 is 0. So this will be 0. And this will be 2 obviously. This will be 3. This will be beta. Now this is -1, -2, 3, 3, 4. This is 3, 6, -7, 1, 1. Okay, this is the this is the augmented. This was the A matrix. Okay, and this is the B matrix, basically the constant matrix. Sorry. Okay. So this is my B matrix. Now, what do I need to do? I need to convert this into row echelon format. How? Try to make as many zeros as possible. Try to eliminate totally this row, right? How can I totally eliminate this row? So let me make all these elements 0. I can make it all these elements 0. So what I can do is I can do this operation. Row 2 will be equals to row 2 minus 2 row 1. Row 3 will be equals to row 3 minus or row 3 plus row 1, and row 4 will be equals to row 4 will be equals to uh, row 4 minus 3 row 1. Okay, row 4 will be equals to row 4 minus 3 row 1. Okay, so if I do all this, right, this will be same, this will not change, right? This will become 0, this will be 2, I am doing 2 times this will also become 0, this will be also 0, this will be 2, this will be 1, this will be also 0. Okay, conveniently all the elements here are 0. This will be also 0, this will also be 0, this will be 1, this will be 2, this will be 5 because I'm adding the 2 rows, and this will be 4. Okay, and I am subtracting this one 3 times this one, right? So this will be 0, 3 times this also will be 0, 3 times this will be -1, this will be 4, this will be 3 times this -2. Okay, 3 times this is -2, and this will be beta minus 3. Okay, so yeah, we got this. Like, what is our aim? Our aim is to make as many zeros as possible in this last row, right? So what I can do, I can see I have 3 zeros over here. I can swap these 2 rows for my own convenience. I can swap these 2 rows, or you can also make zeros over here as well. That is also totally fine. Okay, let me do one thing. Okay, no, I can swap these 2 rows. That will be better for me. So I will just swap these 2 rows because I want the last row should have the maximum number of zeros, right, to convert it into row echelon format. So these 2 rows I will swap, and there is no harm in swapping the rows. Swapping of rows is allowed. Okay, swapping the rows is allowed. So this will be now what I can do is I can add these 2 elements to make this is 0. Okay, I can add I can. So what did I do here? I interchange my row 2 and row 4, and now in the next operation I am changing my row 3 to row 3 plus row 2. So this will be 0, this will be 6, this will be 3, this will be beta minus 1, but should I do it? That is the question. Okay, let's keep it as it is. Now what I will do is okay, if I multiply 3 here, right, and then subtract here, this will be all zeros. So I can multiply 3 and subtract this one, correct? Yes, I can do that. So if I multiply, I can change my row 3 to row 3 minus 3 times row 4, right? So this will be basically, this will become all zeros. So this will be all zeros. Sorry, not this. And this will remain same because this is 0 anyways. So now what I can do, I can actually do one more thing. I can again subtract this row, right? I can again subtract this row because okay, one more thing also. Yeah, let me subtract these two rows because I want to have beta only in a single row. I don't want it to have two rows because I will get confused, right? So again what I will do, I will perform this operation. I will change my row 2 to row 2 minus row 3. If I do it, right, only the final last column will change, rest everything will be same. So let me keep it at the side. Let me, okay, we have so much space but I'm not utilizing it properly. Keep it here, let me keep it here, let me keep it here, let me keep it here. Yes, so this, right, this will, what will happen, this will be 0 basically, this will change and this will be I'm adding 1, so this will become minus 2. Okay, that is what will happen, this will become minus 2. Now again what I can do, I can perform again another operation to make change row 2 to row 2 minus 2 row 4, so that these two elements are also gone, correct? These elements are also gone. So I can perform that. This will be this will be 1. Okay, let me copy this thing. Just give me 1 second. Okay, so this goes away. Okay, so this also may okay, can I, oh no, this is not, okay, I can do it actually, but all the elements will not be 0 actually. Okay, only I will be able to make this one 0, this one will go to 0, but this one will still be there, right? This will become minus 4. Okay, no problem. So okay, now how many what do I need? They're asking me what is the condition, find the value of beta such that I can have unique solution, no solution, or infinite solution. So what is the what is the condition to for us to get a unique solution? What is the condition for us to get a unique solution? So how many unknowns I have? 5. Will I ever get a unique solution? 1 2 3 4. I will never get a unique solution, right? Because the number of equations is less than number of variables, and from here itself we can see that what is the rank of A? Rank of A will be this much, right? What is this size of the matrix? It is 4 cross 5. So rank of A is 4, which is less than the number of variables. How many variables I have? 5. So of course there is no possibility of unique solution. That is gone. Not possible. Unique solution not possible. So for any value of beta, you will never get a unique solution. That is anyways gone, right? Now let's come to the next part, that is getting an infinite solution. Okay, or no solution. Let's come to the easier one, no solution. So for what value of beta I will get no solution? If beta is equals to 1, then I get a row of 0, right? If beta is not equal to 1, what will be the rank? If beta is not equal to 1, how many non-zero rows I will have? Like how many independent rows I will have? This will be one independent row, this is one, this is another independent row, this is another independent row, this is another independent row. So rank will be 4, right? Rank of A augmented matrix A colon B will be 4. But what is the rank of A? What is the rank of this matrix? It is actually 3, because I have 3 independent rows. This is totally 0, right? So rank of A is 3. For which condition? When my beta is not equal to 0. If beta becomes equals to, sorry, beta is not equals to 1. If beta becomes equals to 1, then my rank can be, okay, just give me 1 second. I messed up something. 1 second, because it seems like I might have messed up somewhere. What am I doing? Interchanging row 3 and row 4. Okay. And then I'm doing row 3 plus row 3 plus row 2. So this becomes changing row 3 to row 3 plus row 2. Adding this to, oh sorry, I made a mess. Row 3 has been changed. Row 3 has been changed to row 3 plus row 2, right? If I'm adding these two, this will be plus 1. Sorry, this will be beta plus 1, right? Not minus 1. That's why I was messing it up. This will be beta plus 1. Sorry about that. Beta plus 1. This will be beta plus 1. Now here I'm doing something, right? So I'm subtracting from row 2. That's why you should always write this cleanly, what operation you're doing. Otherwise, if you'll mess it up, right, you'll do some mistake. Row 2 minus row 3. So row 2 minus row 3. So if I'm subtracting this, right, this is plus 1. So this will become minus 3 basically. This will be minus 3. Okay. Yeah, this will be minus. Now this is correct. Yeah. Now, yeah, what do I see? That if beta is not equals to minus 1. So if beta is equals to minus 1, right, then this row will be completely 0. Then both the ranks of the augmented matrix and rank of coefficient matrix will be same. But if it is not equal to 0, then the ranks will be different. And if rank is different, that means definitely I will have no solution. So if for the condition beta not equals to 1 minus 1, I will get no solutions, because your rank of A will be 3. Because you can always check a smaller 3 cross 3 matrix, right? If I check a smaller 3 cross 3 matrix, this determinant, what is the determinant of this? This is 0. Is this, yeah, this is 0. This will be again 0. Okay, this is also 0, right? Let me check any other matrix. This one, yes, this one seems fine. No, this is also 0. Oh, let me check this one. This one is all zeros. Let me check this. Yeah, this one is fine, right? Yeah, this one you can check. So if you check this one, right, the determinant of this one will be, you can break this determinant down. This will be 0. This will also be 0. What about if I break it about this one? Okay, all the hell. Okay, this is also coming out of 0. Oh, okay. Let me just give me 1 second now. If I check this determinant, 0, because I have rows of zeros. This will be 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 rows of zeros. Okay, this is anyways gone. This will be, okay, this is anyways gone. This again rows of zeros. This also is row. Okay, this is anyways gone, right? So rank of this will be always less. Okay, yeah. This rank is 2. Yes. Okay, yeah. So what is rank of A? Rank of A is actually 2, right? Because if I choose a small, yeah, if I choose a small 2 cross 2 element, it is non-zero. So that is definitely there. But I have to check all these, right? All these are 0, right? This is 0. 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 Right? Okay, this is also 0. So yeah. Yeah, this and this also, this element is always 0, right? If I check these two, yeah, this actually can form a non-zero minor. Yeah, these elements, yes. But can I use a submatrix like this? Yes, we can. Always we can. Yes, we can. So here, right, if I choose these two rows and this row, third row, so -2, -1, 1, -1, 0, -4, and 0, 2, 1. Okay, so I think this one, the determinant is not 0. So if I check the determinant here, this will be something +8 plus 1, and this one will be some 0 plus 1. Yeah, this will be non-zero determinant. So rank of A will be 3. Okay, so at least, like, you will say, sir, you did not check the minor like this. How can you check? How can I take row 1 and row 2 and row 4 directly? I can, right? I can swap these two rows. If you are having problems, what you do, you swap. That's why always this whole row of 0, right, always should be at the bottom. That's the proper way. Otherwise, you will not be able to properly analyze the determinants. So I made a mistake here. First of all, I should have converted this into the row echelon format. So what I will do, I will swap my row 3 and row 4. Then it will be easier. So if I swap my row 3 and row 4, what will happen? Okay, row 3 and row 4 are swapped. Now it is fine. Now if you check the determinant of this matrix, right, you will say that it is non-zero. So definitely rank of A will be 3. Now if rank of A is 3 and rank of A colon B is 4, then I will have no solutions if beta is not equal to -1. If beta is equals to -1, then this also totally goes away. Then definitely rank of A colon B and rank of A are same. So for what is the condition for infinitely many solutions? The condition is beta equals to 1. So for infinite solutions, what is the condition? For infinite solutions, right, condition is beta has to be equals to 1. If beta is equals to 1, then you will get infinitely many solutions. Okay, I hope you have understood exactly how to find out the rank and the conditions for infinite many solutions, unique solution, and no solution. So like the conclusion is, I think I have written the conclusion over here, that if the number of equations is less than number of variables, that means surely there will not be any possibility of unique solution. There can be two cases, either no solution, infinite solution. Okay, because your rank will not be equal to number of variables. That means your determinant will be always less than 0. Sorry, equal to 0. Determinant always will be equals to 0. So there is no possibility of unique solution. Now if your number of equations is greater than or equals to number of variables, then there is some possibility of unique solution. There are 3 possible outcomes. Okay, for homogeneous equation, as I have already told you, the system of equations will always be consistent. That is, either I can have unique solution, that is x equal to 0, y equal to 0, z equal to 0, trivial solution, null matrix as a solution, that is a unique solution, trivial solution. All these are saying the same things for a homogeneous equation. Okay, or I will have infinitely many solutions. Those are called as non-trivial solutions. So if you have a homogeneous equation, you directly check the determinant. If the determinant comes out to be non-zero, then you say that we have trivial solutions, unique solutions. If the determinant comes out to be 0, then we have non-trivial solutions, infinite solutions. So how will the question come? Question will come that I have this set of equations. They will not say whether it is homogeneous or non-homogeneous. You will identify. You will see these are homogeneous equations. And after you see it is a homogeneous equation, you will directly calculate the determinant of A. If you calculate the determinant of that coefficient matrix, you will see if it is coming out to be 0, then you will say that I have non-trivial solutions or infinite solutions. Okay. If it is not coming out to be 0, then you will say I have trivial solutions, that is x equal to 0 as a solution. So I only have a single solution, that's why it is a unique solution. That is the conclusion. Okay. Please don't mess this up. Remember this. Okay. That was about it. Now this I will come to later. Number of linearly dependent solutions, what are my number of variables, null space, all these things I will come to later. Okay. Now one more thing is there known as LU decomposition. One more thing I want to say, this right, number of linearly dependent solutions like is equals to n minus rank of A. So let's say if the number of unknown variables is 4 and rank of A is 3, that means you have 3 linearly independent rows. That means you will have one dependent solution, or null space, right, null space of my matrix n will or n of A, right, n of A will be, this is also called as null space, that is equals to number of unknown variables, that is n, minus the rank of A. In this case it will be 4 minus 3. Okay. What do I mean by null space? Basically one solution will be always dependent on the other ones. I will discuss about this later on. For now, just understand that what do I mean by dependent solutions. Number of linearly dependent solutions will always be equals to n, that is the size of the coefficient matrix minus the rank of A. Okay. I hope that part is clear. That is the number of linearly dependent solutions. Okay. Now what is LU decomposition? What do I mean by LU decomposition? It is nothing but you break your matrix. Let's say I have a matrix, right, A, into a lower triangular matrix and a upper triangular matrix. Simply this is the format of lower triangular and upper triangular, and it will be given to you in the question. Just maybe what you have to do, you maybe have to find out this element. I hope you can do the matrix operation and find out these elements. So what you will do, you will multiply these two elements, these two matrix, and then equate with the element 1 with this multiplication, right? You will equate each elements and you will find out the values of this L and U elements. That's it. Simple, equating the right hand side with the left hand side. That's it. Nothing else. That is what LU decomposition is for EC, IN, W aspirants. In CSIT, they teach this in bit depth. Okay, they go into the a bit depth, but for us this much is more than enough because we have other things to cover as well, right? So now we will cover about eigenvectors. Again, this is the very important topic, right? Linear dependence, all those things, solutions, that is a very important topic. This again is a very important topic. The questions will mainly come from eigenvector, eigenvalues, or this solutions, homogeneous solution, rank. That is where mostly the question comes from. Sometimes they ask determinant properties also, but mostly the question comes from this two topics. So what is eigenvector? So the physical meaning of eigenvector is nothing. Let's first say that I have a vector here 3i 4j. If I plot it in the graph, this will be my 3i 4j. Okay, and if I show it in the vector format, this will be 3, 4, or in row format 3, 4. If I scale it, right, make it 3 times the vector, it will be 9, 12. So I am scaling it. The direction is same. I am just scaling the vector, right? So I am multiplying a scalar with the vector to get 9, 9, 12j. Direction will be same, angle will be same with respect to the x-axis, just it will be scaled. The length of the vector will be changed. Okay, so eigenvector is something similar. Eigenvectors are those kind of vectors, is if I multiply, where is the equation? Yeah, are those kind of vectors if I multiply this with the element. So let's say I have a matrix A, and for this matrix V is my eigenvector. The size of the vector, eigenvector is either a row vector or column vector. Generally we represent it in a column vector, so it is n cross 1. The size of A will be n cross 1. So eigenvector whose size will be n cross 1, which is a column vector basically, which is a column matrix basically. So if I multiply, if V is a eigenvector of A, and if I multiply these two matrices, then I will get the same matrix, that is V, but in a scaled fashion, that is lambda. Lambda is the scaling factor. Lambda is called as a scaling factor. This will not be equal to 0. This will be a non-zero. Sorry, this can be equal to 0 as well. No problem. Eigenvector must be non-zero. Eigenvector must be non-zero. Okay. So in linear algebra, the eigenvector of a square matrix are non-zero vectors which, when multiplied by the square matrix itself, would result in just the scalar multiple of the eigenvector. Basically, what am I doing? I am just scaling the vector. I am just scaling the vector. That's it. Okay. That is A into V equals to lambda into V for some scalar lambda. I am getting the same matrix scalar. So the word eigen means own, characteristics, proper, typical. So it is originated from the German language. So you don't have to get into that actually. Just understand this, that what is my eigenvector. Now I hope it is clear what is my eigenvector. Eigenvector is a vector in which if I multiply its own eigenvector, right, I will get back the eigenvector itself with a scaled. So one more thing I want to say, like what does scaling mean? Scaling basically means that the length of the matrix will be same. Now I can scale it in the opposite direction as well, right? Then also the angle will be same. This theta angle will again be same, right? So how can I scale it? If I multiply -2, -1, something like this, then this vector can be scaled. So lambda can be any value, that is that can be 0 as well. Okay, negative, positive, any real value. Okay, so I can scale it in this direction, in this direction. That is what scaling means. Okay, so direction can be in either in the same or exactly in the opposite direction. It cannot be in any other direction. Direction has to be either in the same direction along the initial vector or exactly in the opposite direction. It cannot be in this direction, in this direction. No, that is not possible. That is what my scaling means. Okay. So yeah, let us now discuss one more point about orthogonal vectors. How do I check if two vectors are orthogonal with each other or not? Okay, so to check if two vectors are orthogonal with each other or not, we have to, they must satisfy these three conditions. First one is x1 transpose dot x2 must be equal to 0. So basically what does orthogonal means in vector format? In vector format, if I have two vectors a, b, if they're orthogonal, then we know their dot product must be equal to 0. But in matrix, how do I like form it, right? So in matrix format, what do we do? We have two vectors. Those will be generally in the column vector format. So what I will do is, first of all, I will take the transpose of the first vector and take the dot product with the other vector without transpose, and if that comes out to be 0, null matrix, then we say it is a orthogonal, it is an orthogonal set of mutually orthogonal vectors. Okay, also their dot product, right, x1 transpose dot x1 must not be null matrix. This is actually called as the inner dot product and this is called as the outer dot product. Okay, so because we are doing the taking the dot product with itself, we're taking the dot product with the matrix itself, that's why it is called inner dot product, and these are called as outer dot product. Let us take few examples, from there we will understand. So we have this example over here, right, this example we have. So what do I need to do? I need to do x1 transpose multiplied by x2. x1 transpose multiplied by x2. So this will be what? I'm taking the transpose of transpose, right? So this will be 1 0 only. So I'm doing the transpose of transpose, this will be 1 0, but this is already in transpose, I'm not doing anything. So this will be converted into your column matrix. Okay, we write it like this for our own convenience. Generally vector is represented in column format. So this will be 0 1. So this will be like, what is the size? Size of this matrix is 1 cross 2 and 2 cross 1. So what will be the final size? It will be 1 cross 1, right? So this is simply 1 into 0, that is 0 itself, plus this first row into first column, right? That is again 0. So it is null. So definitely it will be a orthogonal matrix, but I have to check first of all inner dot product. So what is x1 transpose into x1? So this will be 1 comma 0 into 1 comma 0. Is this equal to 0? No, this is not equal to 0. This is equals to 1. So this is not equal to 0. So definitely inner dot product should not be equal to 0. So this is satisfying. I have to check the inner dot product for the other matrix as well, right? x2 transpose into x2. What will be this equals to? So x2 is 0 1 transpose, correct? So this will be 0 1 and 0 1. Again this is not equal to 0. This is equals to 1, right? This is which is not equal to 0. So hence x1 and x2 are set of, these two are set of mutually orthogonal vectors. Okay. Also you can also calculate this value as well, x2 transpose x1. This is also totally valid. Both are totally valid, right? You can check both of them. So here if I check x2 transpose into x1, so this will be x2 transpose, right? So this will be 0 1 into 1 0. Again you will see that it is coming out to be 0, right? So yeah, so then I can say that this is a set of mutually orthogonal vectors. Here as well, again you will apply the same condition, you will see that you are getting set of mutually orthogonal vectors of x1 and x2. Okay, you can check it. Now basically for two vectors to be orthogonal, their inner dot product must be null and their sorry what I told you opposite, their outer dot product, right? That is when I is not equal to j, outer dot product must be equals to null, and their inner dot product whenever I is equals to j, that must not be equals to 0. That must not be equals to 0. Okay, so that is what my set of mutually orthogonal vectors are. And what are my set of mutually orthonormal vectors? Orthonormal vectors are those vectors where the outer product is 0, that is done, right? The inner product is also 1. Here inner product can be anything except 0, but here I am specifying that inner product must be 1, then it will be orthonormal. Basically the magnitude will be 1. So in this case what is the inner product? The inner product is 1. So this is a set of orthonormal vectors. These two, in the first case, these are set of orthonormal vectors. For the second case if I solve, right, for the second one if I solve, here if I take the outer product first, this will be x1 transpose will be 1 1, and this will be minus 1 1. So this will be minus 1 0, right? This will be 0 simply. So if I do the inner product now, x1 transpose into x1, so this will be 1 1 and 1 1. So here you are seeing that this is not equals to actually 1, this is equals to 2. And if you do same thing, x2 transpose into x2, right, I think you will get, let us calculate, this will be minus 1 1 into minus 1 1, 1 plus 1, so 2 again, which is not equals to 1, which is not equals to 1. So these are the set of linearly mutually orthogonal vectors, not orthonormal. Orthonormal will be the case when the inner product is exactly equals to 1 and outer product is equals to 0. Okay, so yeah, actually we should know what is orthogonal and orthonormal because it will be used later on. Okay, so what are eigenvalues? Eigenvalues, now what are eigenvalues? Eigenvector I have told you, right? What are eigenvalues? The eigenvalues of a matrix are scalars by which some vector eigenvector change when the matrix transformation is applied. So basically, I have a matrix and I multiply this vector, right, eigenvector, and it is transformed into the same vector but scaled. So the scaling factor is simply called as the eigenvalue. The scaling value is called as the eigenvalue, that is it. So let's understand what is eigenvalue and eigenvector by a simple example. So A, let's take a matrix A equals to 3 0 0 3. Okay, and let's assume that my eigenvector, right, is 3 comma 4 3 4. So if I multiply these two matrices together, like I'm basically transforming this matrix, right? So this will be 3 0 0 3. This will be 3 4. Okay, that will be equals to, this will be equals to uh, uh, so I can take this 3 common, right, 3 outside, because it is just a identity matrix, right? So this will be same. So this 3 will be simply multiplied. If I multiply I into any matrix, right, I get back the same matrix. You can confirm this. I'll get back the same matrix. So basically what am I doing? I'm multiplying A into X and I'm getting some lambda into X. Same X, right? This X is same. What is lambda? What is the eigenvector? So what is the eigenvalue? Eigenvalue is 3. Lambda is 3 and eigenvector is 3 comma 4. So like the conclusion, like I hope now you have understood like what is eigenvector and eigenvalue. The conclusion is that if my A is a scalar matrix or a identity matrix, then any vector will work as eigenvector. What did I say? I think it is not, okay, it is not written over here. So if my matrix A matrix is a scalar matrix or a identity matrix, right, or a scalar multiple of identity matrix, then any vector will work as eigenvector. You can confirm. You can choose here your X to be 3 comma 5. Then also it will work as an eigenvector. How? Because here, right, A is I, A is some k times I, and I into any vector, right, is always that vector itself with the scaling factor present over here, correct? So that is the conclusion basically. If A is identity matrix, then any vector will work as eigenvector. Now, why is it so important? Why is it so important? So what I can say is, is that now let us come back to our original equation. What is my original equation? My original equation is A into X equals to lambda into X. So if I take this X on the left hand side, this will be A into X minus lambda into X equals to 0. If I take this X common, right, then this will become A minus lambda. Will this be only lambda? This is a matrix. Can this be only lambda? No, this will be I of order n into X. Like if you ever tend to get confused with this line, right, you come back to this line. So if I multiply X into A, this will be AX, correct? If I multiply X into identity matrix, it will be X matrix, right? I cannot leave my lambda alone. I have to write a matrix format because this is a matrix format. I cannot simply subtract a scalar and a matrix, right? That's why I have to read here I. I have to write here I. That's why I is here, right? Now what I can do, is this something familiar? It is something familiar, right? This is my unknown variable matrix. This is some matrix, I don't care, and the constant matrix is 0. So this is nothing but homogeneous equation. This is nothing but homogeneous equation, right? Where this I have this special matrix, that is E, that is A minus lambda I. Okay, And in a homogeneous equation, for us to get infinite solution, what needs to happen? The determinant must go to 0. Determinant E must go to 0. That is what we have discussed just in the previous slides, right? So determinant of E must be equal to 0. That is A minus lambda I must be equal to 0, right, for infinite solutions. Okay. Basically, we know for a homogeneous equation, either there are two cases. Either I have a trivial solution or non-trivial solution. Trivial solution is not possible, right, because I have already told you that eigenvector cannot be 0. So x vector cannot be 0. So trivial solution is gone out of the picture. What is the other possibility? Infinite solution. If I need to have a solution of this equation, I have to go for the infinite solution case. And when does infinite solution occur? When my determinant of the matrix is 0. Then we get infinite solution. That's why we will make this determinant equal to 0. A minus lambda I determinant will be 0. And I hope you have seen this equation everywhere else. This is called as the characteristics equation. Okay. So we will derive the characteristics equation, don't worry. So the solution vector that we get in this eigenvector will be my eigenvector basically. The solution that we will get, right, from solving these values, right, we will get our eigenvector basically. How do I get my eigenvector? I will show you, don't worry. So basically you can let me take a very basic matrix. Okay, let me take this matrix 0 2 0 1 3. Okay, so what are my how do I find my eigenvectors basically? So what you will do, this is my A matrix. I will do A minus lambda into I. Okay, so A minus lambda into I, determinant equal to 0. So this will be 2 0 1 3 minus lambda into I, that is 1 0 0 1, determinant equal to 0. So this will be 2 minus lambda, 3 minus lambda, this will be 1, this will be 0. Okay, and this determinant I will make it 0. So this will be 2 minus lambda into 3 minus lambda equal to 0. So from here I get two values of lambda. Lambda equals to 2 and lambda equals to 3. Now you will say, how sir I will solve it? I get two distinct values. How will I solve it? So this is how you will solve basically. So you will put this in the equation. So what was the equation? A into x was equals to lambda into x, correct? So what was my A? A is this value, that is 2 0 2 0 1 3. X is some x1 x2, right? X1 x2. I have to find out the eigenvector, so that is how we will solve. X1 x2, this will be lambda, so I can choose one value of lambda at a time. So 2 into x1 x2. So from this I will get a equation. So 2x1 is equals to 2x1, which is always 2. So I don't get any new information. 2x1 equals to 2x1. x1 can take any value. X1 any value, right? There is no boundation in x1. What about this equation? Second equation. So here x1 plus 3x2, I am just equating in the rows. x1 plus 3x2 equals to 2x2. Okay. So from here I can say that x1 will be equals to minus of x2. So I get one relation. X1 is minus of x2, right? So if I have here x1, this will be minus of x2, and x1 can take any value because the first row is telling me 2x1 equals to 2x1, that is always valid, right? So x1 can take any value. 2x1 equals to 2x1 is always valid. So x1 can take any value basically. Okay, so this I can write, I can take x1 common, equals to 1 minus 1. Okay, so you try yourself. 1 minus 1 will be an eigenvector, 2 minus 1, 2 minus 2 will be an eigenvector, 3 minus 3 will be an eigenvector. Basically minus 3 will be an eigenvector. Anything you choose where the other term is the negative of the first term, then it will be an eigenvector. You can verify it. Okay, that will be eigenvector. So basically what is it telling me? I have infinite solutions, right? You are seeing I have infinite solutions. That is what we expected. We must have infinite solutions. So we are getting infinite solutions. We are getting infinite solutions, right? That is what we have solved for, right? Otherwise only x equal to 0 would be one of the solution, previous solution, right? So we are getting infinite solutions. And for uh, the other value of lambda, for the other value of lambda equals to 3, if I solve for lambda equals to 3, what will happen? This will be 2 0 1 3 equals to x1 x2 equals to 3 into x1 x2. Okay, equals to 3 into x1 x2, right? So if I solve for this, right, this will be 2x1 equals to 3x1. So can infinite values of x1 take? No. Here, right, what is the solution? I can, don't cancel out, don't cancel these things out, don't do it. Okay, you take this to the other side. If I take this to the other side, this will be 3x1 minus 2x1 equal to 0. So your x1 equals to 0. Don't cancel out, you cannot cancel out things, right? Why you cannot cancel? Because whenever we cancel, right, we assume that x1 is not 0, then only we can cancel. That is our assumption, but you don't know, because no one has told you this, right? So don't just cancel it blindly. Whenever you are cancelling, you are assuming that x1 is not equal to 0. How do we cancel? So simply what we do is we divide by x1 on both sides, and whenever I am dividing by some number, make sure the number must not be equal to 0. Otherwise you are making a blunder, right? So from this equation I get x1 equal to 0. So x1 equal to 0, I got one equation, and in the other equation x1 plus 3x2 in the other row equals to 3x2. So now 3x2 equals, because x1 is 0, right? So 3x2 equals to 3x2 is always valid. So x2 can take any value. Basically the other solution will be 0 3 x2. So basically x2 can take any value. I can show you a few examples, you can verify. Here 0 3 will be one solution, 0 6 will be one solution, 0 x2 can be any real value, 0 7 also can be a solution. Like here 1.2 minus 1.2 is also a solution. It's not like it will be always integer, no. Again I will get infinite solution, because that's what we solved for. But I got two linearly independent solutions. These two are linearly independent vectors, right? These two vectors are linearly independent. I cannot write this vector, so I have got two solutions. As my lambda, my eigenvalues were distinct, I got two independent vectors. V1 vector, what is V1 vector? That is, let's say alpha 1 into 1 minus 1. So alpha can take any real value. Okay, and V2 is alpha 2 into zero 3, right? So it can be anything. I can place it 1 over here also, because it does not matter. It can be like I can take 3x2 common, right? I can take 3x2 common. So it can be anything. So are these two vectors linearly independent? Yes. How can I say? Because I will never be able to write v1 into some k times v2. You'll never be able to do it. Try it. You'll never be able to do it where k is some scalar. So whenever my eigenvalues are distinct, you will get linearly independent eigenvectors. Okay, so that is what that is one conclusion. So what is the steps to compute eigenvector and eigenvalues? First you will compute the eigenvalues by this equation. Okay, assuming x is not equal to 0, then you will put those lambda values in the equation itself, original equation, and then you will find out the solution. Okay, each eigenvalue will correspond to its own eigenvector. Now each eigenvalue will correspond to its own eigenvector. If I have 2 cross 2 matrix, I will get 2 eigenvalues. If I have 3 cross 3 matrix, right, I will get 3 eigenvalues. Why? Because this is a polynomial. Here, if you remember, this becomes a polynomial. What is the order of the polynomial? Polynomial 2, because it was a 2 cross 2 matrix, because the determinant was 2 cross 2. If it was 3 cross 3, the order of the polynomial would have been 3. So simply, I will get n number of solutions if the order is n cross n. Now, if two eigenvalues are same or repeated, if I have repeated eigenvalues, then their corresponding eigenvectors also will be same, right? If eigenvalues are repeated, because ultimately we are putting this x value, right, lambda value, if they are repeated, then their eigenvectors will be dependent, they will be same, they will not be unique. Here I was getting two linearly independent eigenvector, right? Infinite solutions, all of them has infinite solutions, but here I was getting two linearly independent eigenvectors. So that is the conclusion basically. So this thing is called as the characteristics matrix E, A minus lambda I. This thing is called as the characteristics polynomial A minus lambda I determinant. This this, if I equate this equal to 0, this is called as the characteristics equation, and roots of this characteristics equation are called as eigenvalues or characteristics roots or latent roots. So these are just terminologies, okay, nothing else, these are just names. So let us try to find the characteristics equation of this particular matrix, and there is a shortcut as well. I will discuss about the shortcut as well. So what is the long cut? Long cut is very simple, right? Simply you do A minus lambda I of n, in our case it will be 3, determinant equals to 0. That will be your characteristics equation. So this will be 2 minus lambda equal to 0, 0, 3 minus lambda, 4, 0, 0, 4 minus lambda, okay, equals to 0. So this will be equals to 2 minus lambda into 3 minus lambda into 4 minus lambda. Although here it was very simple, right? Then again I have to simplify this further, right? I have to simplify this further. So if I simplify this, this will be 6 minus 5 lambda plus lambda square plus 4 minus lambda equal to 0. Now this will be 24 minus 6 lambda, 24 minus 6 lambda, and yeah, minus 20 lambda plus 5 lambda whole square plus 4 lambda square and minus lambda cube equal to 0. So this is my characteristic equation. You can further simplify it, right? This will be 24 minus 26 lambda plus 9 lambda whole square minus lambda q equal to 0. Okay, so this will be lambda cube minus 9 lambda square plus 26 lambda minus 24 equal to 0. Okay, that is my characteristics equation. What is the shortcut? Shortcut is this one. For a 3 cross 3 matrix, the characteristics equation will be lambda cube minus trace of into lambda square. That's why we have learned trace, because we will use trace. So what is trace? Trace is the sum of the leading diagonal elements. So 2 plus 3 plus 4, that is 9. So it will be minus 9 lambda square, exactly whatever we have got over here. Now this one is actually a bit difficult. It is the minor along the diagonal. So plus the sum of minors along the diagonal. So basically I will calculate the minor of this. What is the minor of this? So the minor of this is simply this matrix, right? Determinant of this matrix. 3 times 4 minus 0, so 12. So 12 plus minor of the other diagonal element, this one. 2 times 4 minus 0, that is 8. Plus the minor of this element. What is the minor of this element? 6, right? 6. Minor of this element is 6. Okay, this into lambda minus determinant of A. So this is equals to what? This is 12 plus 2, so this becomes actually 26, exactly whatever we have calculated over here, right? Okay, and make sure the signs also keep on changing, right? Here you see the signs are changing, so you have to remember the sign. So this is a shortcut, but you have to remember the format. Okay, minus determinant of A. What is determinant of A? Determinant of this matrix is simply 2 into 3 into 4. So 6 into 4, that is 24. So this will be minus of 24, exactly matching over here. So the constant term always will be determinant of the matrix. The lambda term always will be sum of the minors of the diagonal. The lambda square term will always be the trace, minus of negative of the trace of the matrix, and obviously this term will be, coefficient of this term will be 1. Okay, there is a shortcut for 2 cross 2 matrix as well. The shortcut for 2 cross 2 matrix is, the characteristic equation for a 2 cross 2 matrix will be lambda square minus of trace of A plus of determinant of A. This thing goes away. Okay, so always it will be plus minus plus, plus minus plus. Okay, so yeah, I hope that thing is clear, and this will be hugely help to you. So please remember this shortcut. We will use this shortcut everywhere else. Okay, now another definition of eigenvector is this one, that if I have a linear system A, and if I'm providing an input vector that is an eigenvector of this system, right, then the output will just be a scaled version of the input. That this you will study in signals and system. In signals and system also we see eigenvectors and eigenvalues, right? So same concept. Okay, I hope that part is clear. Yeah, those things are clear. Yeah, these things are done. Solution of each eigenvector. Okay, these are done. Okay, what are the properties of eigenvector? Let's discuss about the properties of eigenvalues. So a square matrix of order n has at most n distinct eigenvalues. It cannot have more than n eigenvalues because the order of the characteristics equation is n. An identity matrix has only one eigenvalue, which is 1. So if you see a identity matrix, right, 1 0 0 1, how many eigen values I will have? So I will, if I solve this matrix, right, it will be like, if I see the characteristics equation, it will be lambda square minus trace of A, that is 2 lambda, plus determinant of A, that is 1, equal to 0. So here what do I see? It is lambda minus 1 whole square equal to 0. So lambda equals to 1 equals to 1. So only lambda equals to 1 is a solution. So only I have 1 as a eigenvalue. Again, if you want to do the same for a third order matrix, you will see you are getting the same value. Okay, here this will be basically yeah, again what is the shortcut? Shortcut is lambda cube minus of trace is 3 lambda plus the determinant of the minus, right? So all the minors are 1, all the minors are 1 here, so this will be 3 lambda, this is square lambda plus, sorry, minus the determinant, plus minus plus, right? Sorry, plus minus plus minus. So what is the determinant of identity matrix? 1. Determinant of identity matrix is 1 equals to 0, right? So this will be, now this is just a cubic equation, right? So which is lambda minus 1 whole cube equal to 0. So here lambda equals to 1 equals to 1 equals to 1, I get same solution. So that's how I say that the your matrix, right, your identity matrix will always have only one eigenvalue, that is 1. The eigenvalues of triangular matrix and diagonal matrices are nothing but the principal diagonal elements. What do I mean by it here, right? If I have a matrix like this, you will observe that your eigenvalues always will be the principal diagonal elements. Or a upper triangular matrix or a lower triangular matrix, the eigenvalues always will be a principal diagonal element. You can solve it. You will see you are getting this value. Okay, the sum of the eigenvalues of a matrix is equals to the sum of its diagonal elements or trace of matrix. So sum of the eigenvalues will always be equals to sum of the diagonal elements. That can be formed from this characteristics equation, right? So what does this lambda square mean actually? What does this coefficient of lambda square means? It means it is the sum of all the solutions of lambda, right? I hope you remember the characteristic equation. Or if you want to see from here, what did it go? Yeah, this one. So if I have a equation x square plus 3x plus 1 equal to 0, do you remember what does this 3 represent? This 3 represents the sum of the roots of x, right? That is x1 plus x2 or alpha plus beta was equals to 3, if you remember during your class 8 days, right? And alpha into beta was equals to 1. So the sum of this coefficient represents the sum of the roots. So this coefficient represents the sum of the roots of lambda. So sum of the eigenvalues, that is lambda, will be equals to my trace of A, that is equals to sum of the diagonal elements. So from this we get another very important property of eigenvalues. The sum of the eigenvalues will be equals to my trace of the matrix. Okay. The product of the eigenvalues of matrix A is equals to its determinant. The product of the eigenvalues of matrix A is equals to its determinant, right? That is what the product of the eigenvalues is equals to. So here, right, what are the product? The product of the eigenvalues basically this final term, right? This final term is what? Determinant. And this actually determinant is nothing but this term is product of the roots. So product of the eigenvalues will be equals to my determinant of A. Product of my eigenvalues will be equals to my determinant of A. Okay. So that is the case. The eigenvalues of Hermitian and symmetric matrices always will be real. I have discussed about this previously, right? Now I am again restating this point. The eigenvalues of skew Hermitian and skew symmetric matrix will either be 0 or purely imaginary numbers. Please keep this in mind. These are actually important properties. Okay. Properties of eigenvalues. If any square matrix has k identical rows or columns, then k minus 1 eigenvalues will be 0. So let's say this, right? This is 2 to 2, right? This is not the one. Let me delete this actually. So let me delete this portion. So it is 2 to 2. So what are the eigenvalues of this? So you can solve the eigenvalues. This will be two minus lambda 2 2 minus lambda and if I take the determinant of this, right, so I can directly write the characteristics equation. So lambda square minus 4 lambda 0. So lambda minus 4 equal to 0. So lambda simply equals to 4 or 0, right? So one eigenvalue is 4, other eigenvalue is simply 0, and this will always happen. This will always happen. Simply, how can you solve it? So if I have a 3 cross 3 matrix, right, and I have to find out the determinant of this matrix, 2 minus lambda, this will be 2 2, this will be 2, this will be 2 minus lambda, this will be 2, this will be 2 2, 2 minus lambda. Okay, how do I find out the determinant of this? What I can do is I can simply add all the rows with the first row. If I add all the rows with the first row, what will I get? This will become 6 minus lambda. This will be 6 minus lambda. This will be 6 minus lambda. This will be 2 2 minus lambda. This will be 2. This will be 2. This will be 2. This will be 2 minus lambda. Okay. Okay, so I can take this 6 minus lambda common. I can take this common, right? So if I take this common 6 minus lambda out of a determinant, so one thing I forgot to tell you, for a matrix, right, if you are taking something in common for a matrix, then you have to take it common from all the elements. For determinant, you only have to take it common from the either a row or a column. What do I mean? So let's say I have this 1 2 2 4, right, and I want to take 2 common. So if I take 2 common out of this matrix, this will be 0.5 1 1 2. But if let's say this was determinant 1 2 2 4, to take 2 common, right, what will I do? If I take 2 common, I can either take it common from a single row or a single column. So if I want to take 2 common, this will be same as this one, 0.5 1 2 4. Okay, I have just taken it common from the first row. Why is that the case? Because I hope you remember this property, that 2 times a, right, if I find out the determinant of this is actually 2 raised to power n times determinant of a. I hope you remember this property. So how did this n came? There I explained, right? So simply it is a n cross n matrix. So this 2 is getting multiplied with all the elements. So I have to take in common n times, either from the row or the column, so that this will be 2 raised to power n. So that's why please be mindful of this. So if I am taking here 6 minus lambda as common, right, 6 minus lambda as common, this will become 1 1 1 2 2 2 minus lambda 2 2 minus lambda. Okay, now what I can do, I can subtract basically these 2 columns, right? So one solution we have already got, lambda equal to 6. Other solutions will be 0. You will see other solutions will be 0. I can show you. This will be 1 0 0. Like I'm just subtracting my column 1 from column 2 and column 3. So this will be minus lambda. This will be 0. This will be 2 0. This will be minus lambda. So this will be equals to lambda square, and simply the determinant is lambda square. So 6 minus lambda into lambda square equal to 0. So 2 solutions are 0 and the other solution is simply non-zero. So whenever you will have k identical rows or columns, k minus 1 eigenvalues will be 0 and the only one eigenvalue will be non-zero. That is basically the value, not the value actually, this can be anything. It will be basically the sum of the rows or column. Here what was the sum of the rows and column or column? 4. Here what was the sum? 6, because I was able to take this lambda minus 6 common. Okay, I hope this part is clear. This is one of the very good properties of eigenvalues. So I already have been discussed what is sum of eigenvalues, product of eigenvalues, Very, very important. These are very, very important. Okay. If A is a singular matrix, if A is a singular matrix, that means the determinant of the matrix is 0. That means the product of the eigenvalues will be 0. That means at least one eigenvalue has to be 0, because if determinant is 0, product of eigenvalues is 0, and if product of eigenvalues is 0, this lambda 1, lambda 2, lambda 1, lambda 2, lambda 3, all these are 0. That means at least one element will be 0, equal to 0, right? If all these are 0, that means at least one element is 0. It has to be like at least either lambda 3, lambda 2, lambda 1, at least one of them has to be 0. Okay. Now, if rank of A, the A matrix, right, is less than n, then also at least one of the eigenvalue has to be 0, because if rank of A is less than the number of variables, that means determinant of A is 0, and if determinant of A is 0, that means your one of the eigenvalue will be 0. So all these, whatever I am telling you, right, these are all conclusions. Examiner will ask you something from this point, so please listen to it very carefully and try to at least understand it conceptually. No need to remember, but understand it conceptually. So if I tell you that if one of the eigenvalues of the matrix is 0, what can you conclude? You can conclude that it will be a singular matrix, because the determinant has to be 0 if one of the elements, one of the eigenvalues is 0. The rank of the matrix A has to be less than n, the order of the matrix. So these two things you can conclude. Also you can conclude about the solutions, right? Here it is a homogeneous equation. So if it is less, right, you will get okay, yeah, if it is less, yeah, that is what you will conclude basically. These two things you will conclude. Okay. Now if all the elements of A are real and alpha plus I beta and having alpha plus I beta as an eigenvalue, then the other eigenvalue will be alpha minus I beta. Okay, the short proof is here. You can see the proof using the characteristics equation for a 2 cross 2 matrix. Okay, if all the elements are real and if alpha plus I beta is a eigenvalue, that is solution, then of course the other solution has to be alpha minus I beta, right? I hope you remember that the complex roots always come in complex conjugate format if all the coefficients of the polynomial are real. If all the coefficients of my polynomial are real, then my roots will come as complex conjugate format. Okay. Also, if my roots are in this format, alpha plus under root beta, right, inserts, then the other root will be alpha minus under root beta. So I think for that also I have proven here, right? For that also I have proven here alpha plus minus beta. Okay, that is also what I have proven here. So yeah, these are key points that you must understand conceptually and keep in your mind. Okay, now if A has a eigenvalue lambda, then A square will have a eigenvalue lambda square. How is it possible? So A has a eigenvalue lambda, so A x will be equals to lambda into x if A has a eigenvalue lambda. So what I will do, I'll pre-multiply by A on both sides. So if I pre-multiply by A on both sides, this will be A into x equals to lambda into A into x. Now what is A into x? What is A into x? A into x is nothing but lambda into x, because lambda is just a scalar, right? I can take it outside. Lambda is just a scalar. So A into x is nothing but lambda into x. Sorry, yeah, lambda into x. So I'll replace my A into x with lambda into x, and already a lambda is there, and this becomes A square into x. So A square into x equals to lambda square into x. I can write this as b equals to A square, and I can write lambda square equals to beta. So b into x equals to beta into x. It is nothing but same equation as my eigenvector equation, but this time the actual matrix is A square and the eigenvalue is beta, that is lambda square. So that's why the eigenvalue of A square will be lambda square, as you can see from here. Similarly, A raised to power m will be lambda raised to power m. A inverse will be lambda inverse. This will be valid if the inverse exists, obviously. K into A will have eigenvalue as k into lambda. Again, if I have Ax, right, what will be the eigenvalue of k into A? Simply multiply by k on both sides. This will be k into lambda, right? Very simple. This is the most important one. What will be the eigenvalue of adjoint of A? Sometimes they have asked question from this, right? Sometimes they have actually asked questions. So eigenvalues of adjoint of A will be what? It will be determinant of A upon lambda. How? So do you remember what was my adjoint of A? So adjoint of A was basically A inverse into I, and also there was a determinant of, sorry, not I actually, yeah, determinant of A into A inverse, right? That is what my adjoint of A is equals to. Right, so I have to find out the eigenvalues of this matrix. So basically I have to find out the eigenvalue of this matrix. How will I find it out? If I know the eigenvalue of my A matrix, right? So I know my eigenvalues of my A matrix. So how will I find it out? So what I will do is, I am doing A into X into lambda into X, right? So now what I will do is, okay, so I multiply by this factor on both sides. If I multiply by this factor on both sides, what will I get? So first of all, what is my A inverse? So one thing I can do, I can multiply by, okay, I cannot multiply by X inverse actually on both sides. What is my A inverse? What is my A inverse? I don't know what is my A inverse. Okay, so if I multiply by magnitude of A into A inverse on both sides, what will I get? A inverse into A into X and this will be determinant of A into lambda is also scalar. This will be A inverse into X. Okay, so what will be my eigenvalues basically? Okay, this will be simply I, right? Okay, okay, so this becomes I. So A inverse into A is I, right? Identity matrix. So this will be magnitude of determinant of A into X equals to lambda into, so I can divide by this determinant, this okay, this let me keep it actually, A inverse into X. Okay, so now what I will do is, I will divide by lambda on both sides, and let me name this matrix as B, adjoint of A. So if I divide by lambda on both sides, this will be determinant of A upon lambda into X will be equals to this determinant of A into A inverse, which is equals to my B matrix, right? B into X. And let me write this determinant of A by lambda as beta. So this will be beta. So basically B into X equals to again beta into X, right? So finally this is my eigenvalue for this matrix B. What is matrix B? Matrix B is nothing but adjoint of A. What is eigenvalue? Eigenvalue is determinant of A upon lambda, that is written over here. So why am I deriving? Because of course you will not be able to remember these many things, right? So you should be smart enough to derive in the exam hall. So that's why I am showing how can I derive it in the exam hall itself. So if you are enjoying this, make sure to hit the like button and comment down below if you are still watching till this point. Okay, so yeah, that's how basically you will derive this. So basically the eigenvalues of adjoint of A will be the product of all the eigenvalues, because determinant of A is nothing but product of all the eigenvalues of A. Product of all the eigenvalues of A divided by the particular eigenvalue. So basically, how many eigenvalues will the adjoint of A have? So let's say it's a 3 cross 3 matrix and I have lambda 1, lambda 2, lambda 3 as eigenvalues of matrix A. So what will be the eigenvalues of adjoint of A? It will be product of all the eigenvalues lambda 1, lambda 2, lambda 3 divided by the one of the eigenvalue lambda 1. So one of the eigenvalues will be lambda 2 into lambda 3. The other eigenvalue will be again product, then divided by the other lambda 2. So this will be lambda 1 into lambda 3 and the other one will be lambda 1 into lambda 2. Okay, so these three will be my eigenvalues of my adjoint of A. Okay, I hope that part is clear. Okay, if I have a matrix that is A plus minus ki, then the eigenvalues will be lambda plus minus k. Again, you can prove it. Okay, that is the homework for you. Please prove it. How can I prove it? Using the same equation, this equation only, A into x equals to lambda into x. Use this equation, you will be able to prove this. And if it is raised to the power of m, then this also will be raised to the power of m. Just keep in mind, if this is raised to the power of m, this also will be raised to the power of m. And here, if I have inverse, so what will be the eigenvalues of 1 by k a plus minus k im? It will be 1 by lambda a plus minus k im. So whatever you will do with a, right, you can do with lambda. That's it. So what you have to keep in mind, just replace your a with lambda. This is known as the inverse Cayley-Hamilton theorem. Replace your a with lambda. That's it. And of course, you will replace I with 1 because it is a scalar value, right? You will replace your a with lambda. Replace a with lambda. Replace a with lambda. Replace a with lambda. Okay, that is the shortcut. You will just simply replace your a with lambda. And if you tend to forget it, then of course you have to derive it. So all these properties are only valid if the eigen vectors are independent. Okay, and they are always valid for distinct eigenvalues. If for some case the eigenvalue comes out to be same, then these properties will not be valid. Okay, so few more properties. A matrix and its transpose will have same eigenvalues, that is A and A transpose will have same eigenvalues, no problem. If A and B are two square matrices of same order, then AB and BA will again have same eigenvalues if they are of same order and they are square matrices, because eigenvalues will only exist for square matrices, so their eigenvalues also will be same. AB and BA will have same eigenvalues. The eigenvalues of an orthogonal matrix will always be plus minus 1. Why? Because what was the equation for orthogonal matrix? A into A transpose equals to I. So if I convert this into my normal format, right, in scalar format, what will be the characteristic equation? So I can replace A transpose with lambda because the eigenvalue of A transpose is also lambda. I can replace my A with lambda. This equals to, I can replace my I with 1. So lambda square equals to 1. So lambda minus 1 into lambda plus 1 equals to 0. Okay, that is what my eigenvalues are equals to. Now, according to Cayley-Hamilton theorem, a square matrix will satisfy. So that is what we have discussed. So a square matrix will satisfy its own characteristics equation. So this is actually the actual Cayley-Hamilton theorem. Here I am using the reverse Cayley-Hamilton theorem. So what I am doing, I am replacing my square matrix with lambda. But actually the Cayley-Hamilton theorem states that if I have this characteristic equation, right, if I change my characteristic equation with A, this will be valid. Basically, what do I mean? So let's say I have this 3 cross 3 matrix A, right? And for this 3 cross 3 matrix, this is my or let me write a 2 cross 2 matrix. This is my characteristics equation. So Cayley-Hamilton theorem states that if I replace my lambda with A, this equation will be still valid. That is, this will be A square. Now this is a matrix, right? So if you are replacing matrix, if I have some constant term, make sure to write I. So once I come from this domain, matrix domain to scalar domain, I always replace my I with 1. So if you want to come back from scalar domain to matrix domain, always remember your 1 should be replaced with I if it is by alone. Okay, so here this will be A square, this will be minus 2A, and your 1 will be replaced with I equal to 0. Let's say if this was 2, so then this would have been 2I, because here this is 2 times 1, so 1 will be replaced with I. These are already matrix, so I don't need to write I, because I into A square is A square, I into A is A. So I don't need to write I here, but here I need to write I, because all of these are matrix. This also must be a matrix, this cannot be constant, right? And this will be a null vector. So basically we can do few questions. So they can ask you, if the matrix is given, they will ask you what is A cube, what is A raised to power 4. So what you can do, you can easily calculate the characteristics equation, and from there you can calculate A raised to power 4, not directly. Directly what you have to do, you have to multiply A into A, then again you have to multiply another A, then again you have to multiply another A, then only you will get A raised to power 4. But without doing this A raised to power 4, like individually, you can solve it using the characteristics equation. That is what my Cayley-Hamilton theorem tells me. Okay, so orthogonal matrix we have already discussed. Unitary matrix also, because unitary matrix, right? The thing about unitary matrix is the eigenvalues will come out to be complex conjugate, but the this product, right, will always be equals to 1. For a unitary matrix, the lambda star into lambda will be 1. How? Basically, for a matrix to be unitary, what needs to happen? Your A transpose star, that is basically the conjugate of it, is A inverse, right? It is similar to my orthogonal, but just a star is there to include the imaginary terms. So basically this will like the eigenvalue of E transpose is lambda, eigenvalue of A inverse is 1 by lambda. So from here I get this equation that A star into lambda. What is star? Star basically means that conjugate. If lambda is A plus IB, then your A star will be A minus IB. That is what star means, right? So if I am taking the conjugate of these two, it should come out to be 1. That is the property of a eigenvalue. So, or this, right, is nothing but the magnitude of A. How? So if I multiply these two, right, if I multiply these two, this will come out to be A square plus B square. So what is magnitude of lambda? Magnitude of lambda is under root A square plus B square. So if I square it, I will get my lambda. So if I square it, this will be lambda square. Lambda square will be equals to 1. Lambda square will be equals to 1. Okay. So same, right, if you have to find out the eigenvalue of idempotent, again you remember the property of idempotent, it was A square equals to A, then you replace A with lambda. So you will get the value of eigenvalues of idempotent, same for involuntary, same for nilpotent. Okay. So this will be the locus of eigenvalues for different kind of matrix. Pretty important. If you want to make a short notes, you can make a short notes out of this and remember where will my eigenvalues lie. Okay. So yeah, as discussed regarding the Cayley-Hamilton theorem, same thing they have done here. So if I have a characteristic equation, I can use the reverse Cayley-Hamilton theorem. I can replace my lambda with A. Sorry, not reverse, sorry, this is the actual Cayley-Hamilton theorem. I can replace my lambda with A. Okay, so that's how you can solve using Cayley-Hamilton theorem. So few properties of eigen vectors we'll discuss. First of all, if the rank of A, right, the matrix for which we're actually calculating eigenvectors, what does rank of A tells me? Rank of A tells me the number of linearly independent rows. Also, it tells me number of linearly independent columns. So, rank actually tells me the number of linearly independent eigenvectors. How? So, we can see from here itself. Let's say I have a 2 cross 2 matrix. Okay. Let's take the example 1, 2, 0, 3. 1, 2, 0, 3. Okay. What are the eigenvalues? Eigenvalues are 1 and 2. Right. What is the rank of this matrix? Rank of this matrix is 2. Let me take another matrix 1, 3, 0, 0. What are my eigenvalues? 1 and 0. Correct. It's a diagonal matrix 1 and 0. Now let us find out the eigenvectors for each of them, right? Let me find out the eigenvectors for each of them. So I hope you understand that how am I calculating it directly. It is just a diagonal matrix, right? You can even solve the characteristics equation, right? 1 will lambda minus 1 into lambda minus 2. Here also you can solve the characteristics equation. It will come out to be 1 and 0. Okay. So let me find out the eigenvector for this 0, 2, x1, x2 equals to eigenvalue into x1, x2. So what is my eigen vector here? So it is x1 plus 3x2 equals to x1. So x2 has to be 0, that is fixed, right? And okay, 0 into x1 plus 2 into x2 equals to x2. Anyways, here also x2 has to be, like, it is saying the same thing, x2 is 0. So basically, right, x2 is 0, x1 can be anything. X1 can be anything. So one solution will be alpha into 1, 0, because x2 has to be 0. x1 can be anything, alpha belongs to any real value, because sorry, x1 can be anything, right? That's why this first term can be anything. Okay. What about the other solution for lambda equals to 2? For lambda equals to 2, if I solve for lambda equals to 2, let me solve for lambda equals to 2. So let me keep it here. Let me keep it here. Okay. This was my V1 eigenvector. Now I will calculate for V2 eigenvector. So 1, 3, 0, 2, x1, x2, and now my eigenvalue is 2, x1, x2. So here this will be x1 plus 3x2 equals to 2x1. Okay, 0. So this becomes basically my x1 is 3x2 and 2x2 is 2x2 itself. So x2, 2x2 equals to 2x2. Basically x2 can take any value, right? x2 can take any value. x1 will be 3x2. So basically this will be 3, this will be 1, and this will be beta, and beta belongs to any real space, right? Any real number. Beta can be any real number. So what do I observe? Are these two vectors linearly independent? Of course they are, because I will never be able to write, can I ever be able to write k into 3, 1 equals to 1 comma 0? Is there any possibility I can ever write this where k is any real number? No. So these two are linearly independent. Basically whenever my rank of matrix is 2, I will always get like basically the rank tells me the number of linearly independent rows or columns, or it tells me the number of linearly independent eigenvector. It tells me how many linear independent eigenvector I will have. Okay, that is what my rank tells me. Now what about here when it is 1, 0? When it is 1, 0, right, for this particular matrix this will be 1, 3, 0, 0, x1, x2 equals to x1, x2, 1, like when lambda is 1. So this will be basically 3x2 will be equals to 0. So x2 will be 0, right? x2 is 0 and x1 can take any value. Basically x1 can take any value. You can see from here x1 is automatically getting cancelled, and here we have no condition actually. So x1, okay, no, here also, yeah, x2 is 0. This tells me x2 is 0. So x1 can be any value. x1 can be any value. So basically the matrix will be 1, 0, alpha. Okay, this is the first eigenvector. What about the second eigenvector? Now the second eigenvector is actually null matrix, right? Why? Because this is 1, 3, 0, 0 and this is x1, x2, right? And it is lambda is 0. 0 times x1, x2 is 0 itself, right? It is a null, simple 0, 0, correct? So from here I can say that this will be x1 plus 3x2 equal to 0, or I can say x1 equals to minus 3x2, right? Okay, x1 equals to minus 3x2. Okay, so what is my eigenvector? What is my x2? x1 has to be 3x2 and this equation has to satisfy. This is 0. So if x1 and x2 both are 0, then okay, for any value this x1, okay, no, this can be actually, this is 0, this is 0. I don't have any condition, right? If I don't have any condition, this will become like minus 3, 1 into beta. So here what do I see? That here also the two eigenvectors are linearly independent. So like I explained it a bit wrong here. I will explain it more clearly now. So what do you have to check actually is not the rank of A. Like rank of A tells me just how many number of linearly independent rows or linearly independent columns I have, or n of A, that is known as the null space. Nullity of a matrix A, any matrix A, will be the total number of variables n, or the order of the matrix, minus the rank of A. That is a basic formula that tells me the number of linearly dependent rows or dependent columns. Okay. Here I will actually not check rank of A. What I will check is nullity of my A of lambda, like A minus lambda I. That is what I will check. Why? I will explain just in a second. I will explain. So what is nullity of A minus lambda I? It will be number of variables n minus rank of A minus lambda I. So this will be for different lambdas, the nullity will be different, right? So let's first of all calculate for lambda 1, when lambda equals to 1, correct? For this first case, when lambda is equals to 1. So when lambda is equals to 1, this will be n is what? N is the number of variables, that is 2, minus rank of A minus I. A is this matrix. If I subtract I, this will become 0, this will be 3, this will become 1, this will be also 0. Okay. So what is the rank of this matrix? Rank of this matrix is simply 1, right? Because one of the column is totally 0. So rank of this matrix will be 1, that is 2 minus 1, that is equals to 1. So this actually tells me the total number of free variables. What do I mean by free variables? So here, right, this x2 is fixed for this vector, for this eigenvector, x2 is fixed, x2 is 0. So we are not free to choose the value of x2, but I am free to choose any value of x1. So x1 here is a free variable. X1 here is a free variable. That is what we mean by number of like free variable. X1 is a free variable in this case. So that's why the rank, that's why the nullity is 1, right? Again, if I calculate the nullity for lambda equals to 2, right? A minus 2i, because my lambda is equals to 1 and 2, right? So if my lambda is equals to 2, then what will be my nullity? This will be equals to n, number of variables is 2, minus rank of A minus 2i, right? What is A minus 2i? A minus 2i. So this will be minus 1, this will be 0. This will be minus 1, 3, 0, 0. What is the rank of this matrix? Again it is 1, right? So this will be 2 minus 1, that is 1. Again, in the second case also I see that I have a, like, if I choose this x2, right, automatically this is fixed, because this will, x1 will always be 3 times x2. So either one of the variable will be free. I cannot choose both of the variables to be free. Okay, that is not possible from my end. I cannot choose both of the variables to be free. That is what we mean by nullity and free variable, right? Okay. So here I was wrong actually. If rank is 2, then basically I will have 2 linearly independent eigenvectors. No, that is wrong, because here also you see the rank. What is the rank of the matrix? 1. Are these 2 eigenvectors independent? Yes. These 2 eigenvectors are independent of each other, right? Even though the rank is 1, these 2 eigenvectors are independent. Let's now take another example where I have repeated eigenvalues. In this case, eigenvalues were non-repeated, correct? And okay, here also let us calculate the nullity for these kind of cases. So if I calculate the nullity, right, again for this case, that is for this matrix now, okay, let me choose it for lambda equals to 1 first. So again, if lambda equals to 1, then nullity of this matrix, right, nullity of A minus lambda I for the second case now, this will be equals to n, that is 2 minus rank of the matrix is 1 3 0 0 1 3 0 0, and I'm subtracting lambda I, that is 1, right? So this will be 0, this will also become 0, this will be minus 1. Okay, this will become 0 and this will become, yeah, minus 1 lambda I, yeah. So what is the rank? Rank is again 1. So again it is 1. Again I can see I have a free variable, right? I am free to choose the value of x1, but x2 is fixed to 0. Similarly, if I calculate the nullity of a minus 0, basically, because 0 is an eigen value here, right? So that will become nullity of a, that is 2 minus rank of a. Rank of a is 1 because it is 1300, which is 1. So again I have 1. Again I see I have like one variable I am free to choose, but the other variable I am not free to choose. If I choose this one, right, x2, then x1 will be minus 3 times x2. That is fixed, right? So that is what my nullity tells me. Nullity discusses about the number of variables that I am free to choose as my eigenvectors. Okay, but how can I discuss about the dependence and independence of eigenvectors? Are my eigenvectors will be linearly dependent or independent? How can I say about that? For that, let us take another example. Okay, let me take an example where my eigenvalues are repeated. So let me take this matrix 1 3 1 0 0. Okay, so here I know my lambda equals to 1 comma 1. I have two eigenvalues, both are 1 comma 1, right? They are repeated. So now if I find out the eigenvectors for this, so this will be like I will have a single eigenvector only, right? A minus lambda I, sorry, a into x, right? So 1301 into x1 x2 equals to lambda into x1 x2. Okay, so this will be x1 plus 3x2, okay, equals to x1. So x2 is set to 0, x2 is set to 0, and x2 equal to x2, x2 is again set to 0. So again this becomes alpha into 1 comma 0. And here what do I see? I see I have only a single eigenvector, right? Because the other eigenvector that I will get by putting lambda equals to 1 will be same. So that eigenvector is linearly dependent on this one, right? Because that eigenvector also will be same. If I put lambda equals to 1, it will be some beta into 1 0. So if I have repeated eigenvector, right, the number of times by which it is repeated, those many dependent eigenvectors I will have. Okay, what about the nullity? Again, if I calculate the nullity, right, for this particular eigenvector, eigenvalue lambda equals to 1, this will become like 2 minus rank of lambda is 1, so this will be 0 0 0. So again it is 1, so 1. So how many number of free variables I have? 1, right? I can choose a single free variable, the other variable is fixed to 0. Okay, so this particular value tells me nothing but the number of free variables. Number of free variables for the eigenvector corresponding to lambda, to eigenvalue lambda. Okay, and what is the rank of this matrix? The rank of this matrix is simply 2. So even though it is a full rank matrix, still the eigenvectors what I'm getting are like dependent, linearly dependent. So how to like know whether my eigenvectors will be linearly independent or dependent? If all my eigenvectors are distinct, that is they are not equal, then it will have a set of n linearly independent eigenvectors. Okay, here if you see, whatever eigenvectors I was getting, eigenvalues I was getting, they are not same. So eigenvectors were also not linearly independent. They are not linearly dependent, they were linearly independent. Here also, if you see, eigenvectors were distinct. So here I got my eigenvalues were distinct. So my eigenvectors were also linearly independent. Now if I have repeated eigenvalues, so repeated eigenvalues will be, if I have repeated eigenvalues, right, then the total number of linearly independent eigenvectors will be basically total number of variables minus the number of repeated eigenvalues. So here how many repeated eigenvalues I have? Like one repeated once, right? So that's why it will be 1 in this case. What is the total number of variables? 2. And how many times 1 got repeated? How many times 1 got repeated? Once. So this will be 2 minus 1, that is 1. Okay. So that's how you can calculate the number of like linearly independent eigenvectors. Okay. Yeah, that's how you will calculate. That's it basically. Yes, that's it. So free variables, number of, one more thing is there, one more thing is left out. That is one, that is, yeah. So yeah, that's it basically, that's it. So that's how you will know like how many number of linearly independent eigenvectors I have. So few properties of eigenvector are, if eigenvector of A is known, okay, then eigenvector of A square also will be same as A cube, eigenvector of A cube also will be same as A, eigenvector of A inverse will also be same as A. How can I prove it? Of course you can. So if you know that what is the equation for eigenvector A into x equals to lambda into x. So what will be equation for, sorry, A into x equals to lambda into x. What is the equation for A square? So I can pre-multiply A square, A on both sides. This will become A square into x will be equals to lambda into A into x. Okay, so A into x equals to so what is A into x equals to? A into x is nothing but lambda into x, right? So I can replace a lambda into x. So this will be A square. So I can say my A square equals to B matrix, right? So this will be B into x equals to lambda into A into x, that is, yeah, A into x is lambda into x. So this will be lambda into x, correct? So B into x equals to lambda square into x. So basically x is eigenvector of B, right? And what is the eigenvalue? Lambda square. But the eigenvector remains same. And what is B? B is A square. So eigenvector of A square is x, which was the eigenvector of x, which was the eigenvector of A. So eigenvector will not change actually. Eigenvector will remain same. This is how you can prove how eigenvector will remain same. Okay, eigenvalue changes, but eigenvector remains same. Okay, eigenvector corresponding to distinct eigenvalue forms the set of linearly independent eigenvectors. Okay, so eigenvectors corresponding to distinct different eigenvalues will form a set of linearly independent eigenvectors. Okay, that is what we have seen in the example. If A is a real symmetric matrix having distinct eigenvalues, then eigenvectors corresponding to them forms set of mutually orthogonal eigenvectors. So like this is a property, special property of eigenvectors, that if A is a real symmetric matrix having distinct eigenvalues, okay, A has to be real symmetric matrix, and if its eigenvalues are distinct, then we say that the eigenvectors will form a set of mutually orthogonal vectors, orthogonal eigenvectors. I hope now you know what do I mean by mutually orthogonal eigenvectors, because I have proven it to you. What do I mean by mutually orthogonal eigenvectors? So let's discuss about another type of matrix, that is similar matrix. What are similar matrices? Similar matrices are nothing whose eigen values will be same, trace will be same, determinant will be same. So if A and B are both similar matrices, right? If A and B are both similar matrices, then their trace will be same, their determinant will be same, and their eigenvalues will be same. And how are they related? They are related like this. B will be equals to A P inverse AP, where P will be called as the similarity matrix. So if A and B are similar, then there will exist a matrix P such that this relation will be followed. Now you will say, do I need to memorize this relation? No. And how are my eigenvalues same, how are my determinants same? Here I have done the proof, right? Simply you use this equation ax equal to lambda x, and like you can also write this, right? So ax equal to lambda x, or you can write bx equals to lambda x, anything you can like, and you replace your b with this value. You will observe that the eigen values will remain same, but the eigenvectors will change. And you can see the proof here. If you don't understand it, don't worry, there is a GATE PYQ that we will solve later on. There I will explain this. Okay, here I am not repeating it over again. So that is the summary of similar matrix. Okay, I will derive while solving the question. Don't worry, while solving the question I will derive it, but you can see from the here, you can also do it by yourself. Okay, so but I will derive it while doing the question. But this is my similar matrix. Do I need to remember this equation? Not important, because in GATE this equation will be given to you, but it is good to know that something like this exists. Okay, this is called as similarity transformation. We are transforming A to B, where A and B both will be my similar matrices. Like if I take the determinant on both sides, right, this determinant and this determinant will be cancelled, so determinant of A will be equal to determinant of B, so that is sorted. And your eigenvalues will be also equal, eigenvectors will be different. What will be your eigenvectors? That I will derive in the question. Okay, so yeah, another kind of matrix, like another kind of property of a matrix is diagonalizable matrices, right? What do I mean by diagonalizable matrix? So basically a matrix is said to be diagonalizable if and only if there exists an invertible matrix M such that your D matrix will be this. D matrix contains all the eigenvalues in the diagonal element. So all the diagonal elements will contain eigenvalues and all other elements will be 0. This is called as a like diagonalizable element, and there has to exist a matrix M. Now what is this M, right? How can I define this M? So that I will explain. So let us try to diagonalize this particular matrix. With this example we will understand. Okay, so for us to diagonalize this matrix, we have to find out the now M, right? M is nothing but a modal matrix formed by the eigenvectors of A. So M will contain all the eigenvectors in series basically. So corresponding to lambda 1 I will have eigenvector v1, corresponding to lambda 2 I will have eigenvector v2, corresponding to eigenvector eigenvalue lambda 3 I will have eigenvector v3, and so on. Okay, and so on. So this is my lambda 1, lambda 2, lambda 3, right? So I will show you with example. Let's say let's take this matrix, let's diagonalize this matrix. Is this matrix diagonalizable or not? We will see that. So for that, first of all we have to calculate the eigenvalues. So if I want to calculate the eigenvalues, what will be my eigenvalues? So eigenvalues I can solve using the characteristic equation. It will come out to be 1 and 3. So corresponding to 1 I have found my eigenvector, that is 2, 1. Okay, like alpha 1 is just a like constant term. I can assume alpha 1 to be 1. 2, 1 is one of the eigenvector, and alpha 2, if I corresponding to 3, right, my eigenvector is 0, 1. So my modal matrix M will be eigenvector corresponding to 1, eigenvector corresponding to 2, 0, 1. So this is my modal matrix. You see, this is my modal matrix M. Okay, and I know basically whether my matrix is diagonalizable or not, I will apply this operation, right? M inverse into M, M inverse into A into M, and I will get back my diagonal matrix. So if I am able to, like, if M inverse exists, then I say that the like the matrix is diagonalizable. Basically diagonalizable means that the matrix, right, I can do some transformation and I will get all the eigenvalues in the diagonal of the matrix if I do this transformation, right? So that is what diagonalizable means basically. Okay, so here if I do perform this operation, M is this. What is M inverse? You can calculate the M inverse. It will be just a shortcut. You will swap these two values and you will change the sign of these two elements. Okay, then divide by the determinant, that is 2. So 1 by 2. So now if I apply this operation, right, M inverse A into M. M inverse is this. A is this 1 0 minus 1 3. This is my A, right? If you remember, this is my A. 1 0 minus 1 3 into M. So you will see that you are getting this matrix. It is nothing but matrix D, right? This is nothing but matrix D. That is this is lambda 1, this is lambda 2, right? So this matrix A is diagonalizable, right? This matrix A is diagonalizable. Maybe they will ask in question, is this matrix diagonalizable? So what do you have to verify? You basically have to verify whether my M inverse exists or not. That is the only the problem, right? Because if M inverse does not exist, then I will not be able to write this equation. So M inverse has to be, like M inverse have to exist. For M inverse to exist, what needs to happen? Determinant of M must not be equal to 0. So determinant of this matrix must not be equal to 0. That basically means my eigenvectors must not be dependent on each other. My eigenvectors all should be linearly independent of each other. So that is the condition basically. A of order n cross n is diagonalizable if and only if all the n eigenvectors are independent. All my eigenvectors are independent. Even if eigenvalues are repeated, that is fine, but all the eigenvectors should be independent of each other. If I have linearly dependent eigenvectors, then the determinant of my modal matrix will be 0, and then M inverse will not exist, and then I will not be able to diagonalize my matrix. So they can ask you a question like this, that whether matrix A is diagonalizable or not. So you have to find out the eigenvectors and check whether your eigenvectors are independent or not. If your eigenvalues are distinct, right, all your eigenvalues are distinct, then you can safely say that my eigenvectors also will be independent. So you can safely say that yes, this matrix will be diagonalizable. If your eigenvalues comes out to be repeated, then you have to find the eigenvectors and then check for those repeated eigenvectors whether my for those repeated eigenvalues whether my repeated for those if your eigenvalues are repeated. So for those repeated eigenvalues, you have to check whether my eigenvectors are independent or dependent. If they're dependent, then your M matrix would not exist, then you will not be able to diagonalize. That is a summary. Okay, so now we will discuss about vectors. So vectors, we have briefly discussed what are vectors. Vectors in physics, we know that vector has a magnitude and a direction. Okay, it is a geometric entity that has both magnitude and direction. Vectors in linear algebra is a matrix which has either only one row or one column. Okay, so a matrix having only one row is called a row vector, having only one column is called a column vector. Okay, so row matrix and column matrix are called vectors. So I can write this in a row, that is 1 2, this will be called as row vector, or I can write this vector in a column, this will be called as a column vector. So these are also called as ordered pair. Okay, so because here I have two quantities pair, right, two quantities, here I have three quantities, so these are called ordered triplets. If I have 4, this will be called ordered quads. Okay, so what are set of vectors? So basically we have in physics we use vectors, right? So matrix is also used to store the vectors. Matrices are also used to store the vectors, right? So because we can store it in computers, otherwise how can we store vectors? So we can use matrices to store vectors in computers. So now what is a set of vectors? Set of vectors are those vectors which are together. Okay, here let's say I have three vectors a b, or two vectors a, that is let's say I plus 2j cap, and b vector is 3i plus 4j cap. Okay, so a and b are called as set of two vectors. Set of two vectors. So I can write x1 vector to be 1 2 and my x2 vector to be equals to 3 4. So these are my set of two vectors. Now what are set of linearly independent vectors? So a set of vectors are called as linearly independent if no vector can be expressed as a linear combination of the other one. So here can I express x2 in terms of my x1? No. If I multiply 2 here, right, the bottom element will be same but the top element will not be same. But if I choose a vector x1 as 1 2 and x2 as 2 4, right, then these are called as linearly dependent vectors. X1 and x2 are linearly dependent. So in this set of vectors I have only a single vector that is linearly independent, this one or this one, any one you choose, other one will be dependent. Here in this set of vectors I have two vectors which are linearly independent. Both these vectors are linearly independent, I cannot write the other vector in terms of the other one. So pictorially, how can you define that? Let's say I have three vectors. Can I write this vector C in terms of A and B? Is that possible? Okay, if that is possible, then C will be linearly dependent. So I will have only two linearly independent vectors. Okay. So basically here the same thing I have done. So if A, B, C are linearly dependent, then C will be a linear combination of A and B. Okay. So that is what we mean by linear dependence. Basically they have to follow a linear equation like this. All the vectors has to follow a linear equation like this, that is this will be equal to 0 if they are linearly dependent with each other. Okay. Okay, this is another question. What will be the relation between A, B, C, D if A, B, C, D are set of linearly dependent vectors? So basically then lambda 1 into A, lambda 2 into B, lambda 3 into C, lambda 4 into D will be equal to 0, right? If they are linearly dependent. Now don't confuse this lambda with eigenvalue. This is not eigenvalue. Okay. And remember, at least like out of this, right, at least one of them will be non-zero. Otherwise, if all of them are 0, then this equation is anyways not invalid, right? For any value of A, B, C, D, this will be always valid. So at least one of them has to be non-zero. Then I can surely say that these are set of linearly dependent vectors. So how can I say if a vector is set of linearly dependent vectors? If I can write C in terms of A and B like this, or if I rearrange my equation, right, then simply if I can write A, B, C as a linear combination, that equals to 0, and at least one of them has to be non-zero. Similarly, if four vectors are linearly dependent, then I can write the all four vectors as a linear combination equal to 0, and at least one of them is non-zero. Okay, at least one of them is non-zero. Okay. Okay, now if this equation is satisfied, lambda into x1 equals to lambda into x2 equals to lambda into x3, and magnitude of lambda 1 plus lambda 2 plus lambda 3, these are not equal to 0, then x1, x2, x3 will be a set of linearly dependent vector. So like this is what you say like in literature, but mathematically how can I define this? Mathematically we define it like this. So this, right, tells me at least one of them will be non-zero because I am taking the magnitude, right? So at least one of them has to be non-zero. Even if all of them are 0, then this will be equal to 0. That will, like, that is this condition will be invalid then, right? So at least one of them has to be non-zero. So this condition tells me that at least one of them has to be non-zero. Then only my set of vectors will be linearly dependent with each other. Okay. If this condition is not satisfied, right? If I am not able to write lambda into x1 plus lambda into x2 plus lambda into x3 equals to 0, basically either one of these coefficients, like if all the coefficients are 0, that means I have set of linearly independent vectors. Okay, if all the coefficients, that is lambda 1, lambda 2, lambda 3 are all 0, that means I will have a set of linearly independent vectors. Okay, so the same thing I have already told you. There must exist three scalars, at least one non-zero, such that this equation is followed here, right? If x1, x2, x3 are three linearly dependent vectors, first of all their orders must be same, and this condition must be satisfied, which I have already discussed, right? So how to find dependencies on vector? How can I find dependencies on vector? We can find dependencies on vector by finding the rank, by combining all the vectors together. If rank of A is equals to number of vectors, that means I will have a set of linearly independent vectors. So let's say this, right here. If I combine these two vectors with a matrix A, what is the rank? Rank of A is 1. Rank of A is 1. So I will have set of linearly dependent vector, right? As you can see, yes, these two vectors are linearly dependent. Here, what is the rank? Here, if we see, rank of A will come out to be 2 because your determinant will not be 0. So if rank of A is equals to the number of vectors, then I will have a set of linearly independent vectors, as I have written it over here. If rank of A is equals to number of vectors, then I will have set of linearly independent vectors. If rank of A is less than number of vectors, then I will have set of linearly dependent vectors. Okay. So I hope that part is clear. So yeah, that was about vectors. Now let us discuss about vector space. Now these are just small terms that can be asked in the exam. So that's why knowing what these terms are is important. Mostly they focus on like these topic, right? Vector and vector spaces. Mostly they focus towards CSIT, but sometimes they ask good questions from ECIN as well. Okay, be careful about this. So we have set of vectors having common property called vector space. So if we have a set of vectors which have common property, then those set of vectors are called as vector space. Okay, if I have a set of vectors which have common properties, then those set of vectors are called as vector space. Okay, so yeah, standard vector space. So if I have a vector space here which is r raised to power 1, what does it mean? Basically it covers single dimension, so it will cover the whole number line. So x can take any value. So I will have a set of vectors of all real numbers. So it's a space which contains all the real values. So what is a vector space? Like 2, 0, -1. So it's a 1D vector, right, which contains real numbers. So this is called a vector space in 1 dimension. Vector space in 2 dimension, x and y, where both my x and y are real. So example is this, right? So 2, 1, 1, 2, 1, 1, all these are set of vectors and all the elements of these are real. So this is a vector space in 2 dimension. Okay, similarly vector space in n dimension will be, I will have basically n dimension, basically that is r raised to power n. So r raised to power n is here, right? I will have x1, x2, x3, xn, and all of the elements will belong to real. So that is a vector space in n dimension. So basically this r tells me that it is a real, all the elements will be real of the dimension, and n represents the number of dimension. R raised to power 1, 1 dimension, r raised to power 2, 2 dimension. So r raised to power 2, 2 dimension, r raised to power 3, 3 dimension, r raised to power 4, 4 dimension. Okay, so that is what dimension is. So vector space actually follows few properties. First of all, what is the difference between vector space and vectors? So vector space is a collection, it is a group of objects which is multiplied by scalars and combined by vector space axioms. So we will discuss about few vector space axioms. But vector space basically is a group of vectors, and vector is a single vector, right? It is just a single vector. Okay, vector 2, 2, 1. So this, right, v1 equals to 2, 1. This is just a single vector. If I say vector space r square, that means all the vectors that are 2 dimensional where my x and y are all real. Now it will contain everything. It will contain 2, 1, it will contain 1, 2, it will contain 3, 1, 2, 2, 2, 0, 0. So that is what my vector space is. Okay. Now there are few vector space axioms. Don't need to worry. Okay. Just simply they are stating you what is a plus operation and what is a multiplication operation. No need to worry. So basically what they are telling you that a plus operation is an operation which will follow commutative law. That is basically if I am doing x plus y or y plus x, both should yield me the same result. Okay, x plus y will be equal to y plus x. It should follow associative law. Basically x plus y plus z should be equals to x plus y plus z. Basically if I am doing this first, then I am adding x, or if I am doing this first, then I am adding z, both will yield me the same result. Also it should follow the inverse addition, additive inverse. For each vector x in V, there is an additive inverse minus x to get a solution of V. So basically if I do x minus x, right, I should get a null vector 0. That is what they are telling. So if I apply this operator, so basically what they are telling, x plus minus of x, if I apply this operation, right, if I apply this plus operation and if I am adding the inverse of that, additive inverse of the x, right, I should get a null matrix. That is what they are telling, that additive inverse should exist. They are telling us that for each vector x in V, additive inverse should exist. Okay, that is what they are telling. Now what is scalar multiplication? It is nothing but it has to follow multiplicative rules. So what does multiplication follow? Multiplication follows this associative law, right? In matrix, right, if you remember, multiplication does not follow commutative. So a into b will not be equals to b into a, but they definitely do follow associative, which we have discussed. Distributive also they should follow. C plus d into v should be c into v plus, sorry, this will be D into V. Okay, yes. And they should follow distributive law. Distributive law meaning if I have C dot x plus y, this will be like, these are the same thing, right? C into x, C into y, yeah, same thing only. And unitary law also they should follow that. If for all vectors x in V, if I am doing 1 into V, this should be equals to V into 1. This should be equals to V. Basically, if I am multiplying by 1, I should get back the same vector. So basically nothing, right? They should follow all these properties. So basically, if I am doing scalar multiplication, then for proper scalar multiplication, they should follow all these properties. That's it. Okay. Now, what is vector subspace? As from the name, I hope you can understand what do I mean by subspace. It is a subset of my actual vector space. So if my actual vector space is this, right, then if V is the vector space, then W will be the vector subspace. Okay, so if I have a vector space V1 that is R square, and if I have a vector space that is V2 that is 1 minus 1 minus 1 1, then I can say that V2 is a subspace of V1, because V1 contains all those vectors in which V1 contains all those 2D vectors. Okay, one more condition is also given. So be careful. So if I am writing V1 is R square, that means V1 contains all those vectors whose x and y are real. Okay, V1 contains all those 2D vectors whose x and y are real. Now as soon as I make a condition here, V1 R square x plus y equal to 0, what does it mean? So V1 contains all those vectors all those 2D vectors whose x and y are real. First point. Next point is they must satisfy this condition, x plus y equal to 0. That is x should be equals to minus of y. Now we get a condition. So basically I can have 1 minus 1, 2 minus 2, minus 1 1, minus 2 2, and so on. Okay, and so on. So out of this, right, is V2 a subspace? Yes, V2 is a vector subspace of V2 is a vector subspace. V2 is a vector subspace of V1. So how do I, like, instead of writing all this long thing, right, we have a symbol. This is the symbol basically. So V2 belongs to V1. That's how we define. Now if let's say I have another vector that contains a vector V that contains all 2D vectors, right? It does not have any condition like this, right? It contains all 2D vectors. Then can you say that V1 is a subspace of V? Definitely, because here, right, this also is containing like real elements only, right? And it is a 2D vector, but it is satisfying some particular condition. But definitely I can say V1 is a subspace of V. Also I can say V2 is also a subspace of V, because this also contains 2D vectors and all the elements are real. So that is what my subspace means basically. Okay, so notation, I hope you have understood. Here I have written again notation. So if V, I think this should be squared here, right? This should not be cube, this should be square. So if V is R square and x equals to 2y, that basically means that all my vectors will be two-dimensional vectors. All the x and y will be real terms, and they have to satisfy this condition, x will be equals to 2y, right? So basically it can be 2 into alpha 1 by alpha 1. So basically what does it mean? Basically it will be alpha into 2 comma 1. So alpha can be any real number, right? Any real number. So I can have any infinite number of possibility vectors here. Okay, so that's how you do the notation. So I am teaching you all this because this kind of notation will be shown to you in the question paper. So you must understand like what does each notation mean. Okay, then we have linear span. What does linear span means? The span of a set of vectors also called linear span, is the linear space formed by all the vectors that can be written as a linear combination of the vectors belonging to the given set. So basically if I have been given a set here R square, two vectors, so will these two vectors span all the vector space? Yes, right? So with these two vectors, can I span this whole two dimension? Yes, you can span. So you can span any, like this will be alpha into 0 1 plus beta into 1 comma 0, right? I can span any point or any place at this two dimensional space, right? So basically this will be what, alpha into j cap plus beta into I cap. So basically alpha beta can be any values, so I can span any point on my 2D space. That's why these two vectors are called as linear span. So basically let's understand this with example. Here I have, I think, yeah, here I have example, right? So here let's say I have a vector v, that is a set of vectors, three vectors. Okay, now let x belong to R cube. What does it mean? X includes all those vectors which are three dimension of real elements, like of real values, right? Does vector v spans x? What does it term? What does this term means? So what is the meaning? Meaning is, with a linear combination of v, will I be able to produce vector space x? So it basically means that what is my vector space v? What is my like vector space v? So my vector space v contains three vectors, right? What are those? What are those three vectors? 1 minus 1 0, 2 0 1 and 1 2 4. Okay, now with these three vector, right, can I write a linear combination? Let's say some alpha 1 into v1 plus alpha 2 into v2 plus alpha 3 into v3, so that I am able to write any vector in three dimensional space. Basically I am able to form R cube. Okay, so how can I write it? Basically, like how can I mathematically write it, right? How can I write it? So this will be equals to my x, where x belongs to R cube, because x belongs to R cube, they told me. So x is what? X is a 3D vector xyz, where xyz can be any real value, correct? So if I break it down, right, if I break it down, like here I have written alpha 1 into v1 plus alpha 2 into v2 plus alpha 3 into v3, will be equals to x. That is alpha 1 into v1 is this, v2 is this, v3 is this. Okay, now if I further solve this, right, if I further solve this, we will get a system of equations where x, y and z all belong to real quantity. So this is a these are my constant terms, these are my like coefficient matrix. So I can form a augmented matrix with this. And what needs to happen for us to get a solution, right, like alpha 1 alpha 2 alpha 3, for us to get a unique solution, right, the system of equation needs to be consistent. Basically my rank of a colon b must be equals to rank of a for all values of x, y and z. So basically my like I will find out the rank of a colon b here, and then I will equate it with rank of a, and both of these must be equal. Then only like I can safely say that my x, sorry, my v spans vector space x, because with linear combination of v am I able to form x. With linear combination of v am I able to form x, right? So here if I see that okay, where did it go? Let me form the like augmented matrix first. So let me form the augmented matrix here. So the augmented matrix will be nothing but the like this coefficients, right? So it will be a colon b will be equals to this coefficients 1 minus 1 0 2 0 1 1 2 4. Okay, and this is my x, y and z. And now so basically my x, y and z, both all of them belong to real numbers, so they are not homogeneous. So this is not a homogeneous, like this can be homogeneous equation as well, this can be non-homogeneous as well, right? So for us to get a proper solution, right, proper solution, either I can have infinitely many solution or I need a unique solution. Like zero solution is not a possibility, right? No solution is not a possibility. If I have no solution, that means what? The system of equations are inconsistent. Then I will I will not be able to write my x, y and z in terms of linear combination of v1, v2 and v3. Correct? So basically the thing is, either I will need infinite solutions, or I will need a unique solution. Either one will work. At least I need a solution. I just need a solution. If I need a solution, that means the system of equation must be consistent. For the system of equation to be consistent, basically rank of A colon B has to be equal to rank of A. That is what we have learned in the initial stages, right? Okay, I hope that is clear. For all values of x, y and z, for all values of x, y and z, this should satisfy always. This should always satisfy. That's why we are calculating the rank of A colon B. So this is my A colon B. What is rank of A? So if I see the rank of A, right, can I find out the determinant here? If I find the determinant, if I find the determinant here, what is determinant of A? So this will be, let me first make a 0 here. If I add these two rows together, right, this will be, this thing will be same. I'm adding this row, this will be 0, this will be 2, this will be x plus y, this will be 0, this will be 1, this will be 4, this will be z. Okay, so yeah, so now what will happen is, now if I find the determinant is actually non-zero. Determinant, if I find the determinant of A, right, just A, this will be 2 into 4 minus 3, so this is equals to 5, so which is not 0. So rank of A colon B equals to 3. Sorry, A is 3, rank of A is 3, and what is rank of A colon B? It is also 3. Rank of A colon B is also 3, because if x, y and z are 0, or if x, y and z are any value, I don't care what x, y and z are, right? I don't care what is x, y and z. If it is all 0, then also it is 3. If it is not all 0, then also it is 3, because this is always 3, right? This part is always 3, and overall it becomes a 3 cross 4 matrix, correct? So it does not matter, I don't care about this. So for any values of x, y and z, rank of A and rank of A colon B are always same. Even if it's all 0, if it's not 0, I don't care about this row, right? This column at all, correct? So I can say that yes, basically I can say that my V spans vector x. V spans vector x. V spans vector x, or in other words, what I can say, in other words, x is a linear span of V. So linearly, if I write my V, right, alpha 1 into V1, alpha 2 into V2, alpha 3 into V3, if I write the linear combination of V, I'll be able to get x. So don't get confused by these terms, okay? Both terms are saying the same thing. If I say, does my V span x? Yes. If I say, x is a linear span of V, yes. X is a linear span of V, or x, we can say, basically x is a linear combination of V. In simple layman terms, I can say x is a linear combination of V, or you can say, in other words, x is a linear span of V, or you can say that V spans x. Okay, V spans x. So please, like same thing I have explained it over here as well, that V is spanned by x. or x spans v. Like these two things, please keep these things in mind. So when I say x is spanned by v, if I say x is spanned by v or v spans x, that means I can write my x as a linear combination of v. V spans x, that means I am writing my linear combination of v as x, right? So that is what I mean by x is spanned by v or v spans x. Now what is meant by v is spanned by x? V is spanned by x means by linear combination of x I can write v, or x spans v, that means by linear combination of x I can write v. So please keep these things like keep these terms in mind. How am I explaining the things? Okay, I hope you that thing is clear. What is spanning? What is linear span? Okay, now x belongs to linear span of v. That basically means that with a linear combination of v I can write x. Same thing, right? X belongs to linear span of v. So linearly combining v I can get to x. Okay, x belongs to linear span of x. Same thing, right? By combination, linear combination of x I can get to v. I hope that part is clear, right? So yeah, these are very important things to understand. Now the last few things are left, that is basis vector. Okay, only two things are left here, basis vector and dimension of vector space. So what is basis vector? So basis vector are those vectors basically in terms of which I can define other vectors, right? So in a two-dimensional space, Ij are my basis vector. So I hope you have heard about this basis term. So basically I can write any other 2D vector, right, in terms of my basis vector, right? I think the definition would be also would it be written? No, it is not written here basically. So basically it is some default vector, right? So I in 2D space I cap and j cap are default vectors. So I can write any vector like 3i plus 2j as a combination of I cap and j cap. So that's why I cap and j cap will be my basis vector. Okay, I and j will be set of basis vector space, okay, in a matrix format. If I have okay, so if v1 is a vector space containing only basis vectors and I have x1 which contains 2D vectors, right, then I can say that my v1 is forming a basis of x1 because these contain basis vectors, and with this combination of vectors I can write any vector that contains in x. Okay, just few like these terms are there for EC. Actually these are not that important. For CSIT this can be asked, but like we have to go through all of this, right? So we have to study everything. So again, if let's say I have basis vector in 3D space, I cap, j cap, k cap. I have basis vector in 3D space and x2 is a combination of like any three-dimensional vector, then v2 will form basis of v2 because I and j and k we know these are fundamental vectors, right? Basis vectors with which we can define any three-dimensional vector space. Now how can you check whether a vector is basis or not? So few observation we can see that if a vector is basis, right, the dot product with itself is always equals to 1, which is not 0. Something comes into your mind and the dot product with the other vectors comes out to be 0. Something clicking, orthogonality, something is coming into your mind, right? So orthogonal, something like that. So yes, the vectors must be orthogonal with each other, right? So this similar dot product must be 0, similar dot product must be not equal to 0. Basically they must be set of mutually orthogonal vectors, which we have discussed previously, right? Okay, they must be set of mutually orthogonal vectors, then those vectors will be basis vector in that space. Okay, so in matrix inner product is known as A transpose into A transpose A dot B, or it can be said as A transpose into B. Okay, previously I told you their inner product and outer product, that was wrong. Outer product is actually cross product. Sorry. Previously if I told you inner product and outer product, right, that was wrong actually. Inner product is this, that's how we write inner product, and this product is called as similar inner product and this product is called as dissimilar inner product. There I mentioned inner and outer product, that is wrong. I should mention similar inner product and dissimilar inner product, that was wrong on my behalf. It will be similar inner product and dissimilar inner product. Okay, so similar inner product means A transpose into A, dissimilar meaning A transpose into B, the other product, right? So a basis vector is a set of linearly independent vectors that can be used to represent any vector within that vector space. So it is same as spanning. So basically it spans the whole vector space. So if it is R cube, it will span whole vector space, whole R cube, right? So how to check whether I have like a basis vector, like vector space? So what we can do is we can form this matrix. Like if I have, let's say, a vector space B, and if X is R cube, and I want to check if B is a basis of A, how can I check it? So first of all, we'll check the determinant. Okay, if I have three linearly independent vectors, then it will be a basis of that particular dimension, right? So if I check the determinant of this matrix, what is the determinant? So how will I calculate the determinant? This will be okay, I can do this 1 3 2. This will be 2 times this 6 minus 4, 2 times this minus 4, 0 minus 8 minus 5, 3 times this minus 5. So this will be basically 20 plus 32, 52, which is not equals to just 20, oh sorry, 20 minus 32, right, minus 12, which is not equal to 0. So that means my rank is 3. That means by basically rank of B is 3. That basically means that I have 3 set of linearly independent vectors. If I have 3 set of linearly independent vectors and my dimension is also 3, that means these 3 will be, this can form a basis vector. But for that, again, I need to check whether my this vector, first of all I need to check the determinant, right? Then I need to check whether my B spans X, or X is a linear span of B. So checking this much also is enough, right? Whether B forms a basis vector of X, right, where X is R cube. This is also how we can check whether it forms a span. It forms a linear span of X or not. So how can I check it? So again, the same method, right? We'll have to write the matrix. So even though we can see the determinant is not 0, right? So that means your rank of B is anyways 3, right? That we already know. So that's why we calculated the determinant earlier. So if I form the matrix, this will be 1 2 3, this will be 3 2 1, this will be 2 0 1, okay, and this will be my X, Y, and Z. So if I see, of course, we already know that we have already calculated the rank of A colon B, or sorry, B colon B is 3, because the determinant is not 0. So basically also I can see that it does not matter whether my X is 0 or non-zero, right? Automatically your B colon X also is equals to 3, and system is consistent. If system is consistent, then we can say that B spans X, and if B spans X, right, B can be written as linear combination of X, then I can safely say that B is a basis vector space. Hence B is a basis vector space. Simply you have to just check whether B spans X or not. If B spans X, then B will be a basis vector. That's it. Bottom line is, if B spans X, then B will be basis vector. So these things, small things you need to keep in mind. And like, this is just a small topic that I have not seen much get asked in EC, but again, everything is important and I'm not skipping any concept. I'm trying to cover every single concept, so I have to explain every single thing. Now we have this thing. So this, right, this will always form a basis vector in R square. This will always form a basis vector in R cube. This will always form a basis vector in R raised to 4. There can be other basis vectors as well. There can be other basis vectors as well, not only these vectors, right? This is nothing but, this is I, this is J, this is I, J, K, okay? So this definitely form basis vector in R cube, definitely. But other vectors are also there. They can also form basis vector. How can I check it? By checking span. I hope that is clear by you. Now, one more thing is there regarding the dimension of vector space. What is the dimension? The number of distinct vectors in a basis for V is called as the dimension of vector space. So if I have a vector space V, let's say this R cube, how many distinct basis vector of this vector space do I have? That will be the dimension. For vector space R cube, what will be the dimension? 3, because I can have 3 distinct basis vector. For vector space R square, I will have 2 distinct basis vector. Okay, for vector space R raised to power 4, I will have 4 distinct basis vector. Okay, that's why the dimension will be 4. Same thing is written over here. Okay, that's how you calculate the dimension. Now there are few properties of dimension, that is, if you are combining two vector space, right? Let's say I have a vector space V1 that contains R square, and I have a vector space V2 that contains R cube, and I am combining a vector 3 V3 that includes V1 union V2. What does V1 union V2 means? It combines both V1 and V2. It contains both vectors V1 and V2. So basically it contains R square and R cube. So what shall be the dimension of V3 then? So the dimension of V3, as from the formula we can see, it is similar to probability, right? It will be dimension of V1 plus dimension of V2 minus dimension of V1 intersection V2. So what is dimension of V1? Dimension of V1 is simply 3, because dimension of V1 is 2 because it is R square. Dimension of V2 is 3. Now what is dimension of V1 intersection V2? What is dimension of V1 intersection V2? So basically, which vectors are included both in V1 and V2? Can you tell me which vectors are included? So if V2 is a vector space that contains R cube, right? What does R cube actually mean? R cube means that I will have these kind of vectors, right? 1, 2, 3, 2, 3, 1, and so on. And what does V1 means? V1 is R square, like 1, 2, 2, 3. Now you will say, sir, there is nothing in common between these, right? Nothing in common. No, there is common. So you make the k cap coefficient 0. So it will become R square only, right? If you make the third coefficient 0, k cap coefficient 0, it will be R square. So basically you will have 3, like I cap plus j cap plus k cap. These are my combinations, right? And if I make this k cap coefficient 0, right, I will only have the x component and y component, correct? So actually my V2 or V1 is a subset of V2. V1 is a subset of V2, right? So what is the common dimension of both of these vectors? What is the common? Common is this V2 will contain all the R square elements, right? Because it will contain 1, 2, it will contain 2, 3 when the third element is 0. So basically V1 intersection V2 is nothing but R square. V1 intersection V2 is nothing but R square, right? So what is the dimension of R square? That is 2. So this will be 2. So overall the dimension of V1 union V2 comes out to be 3. Now is there any other way to understand this? Yes. So what is V1 union V3? Union meaning it will V1 union V2, it meaning it will include everything, right? So what is V1? V1 is R square. V1 is R square and V2 is R cube. So it will include everything. So already I have told you, right? V1 is a subset of V1. V1 is a subset of V2, right? So already V2 actually includes everything that V1 includes, right? So it is nothing, V1 union V2 is nothing but R cube, because V2 already includes V1. Because if I make the third term 0, right? Third element 0, then already this is included in V1, right? So it is R cube only, right? Just making the coefficient of the third term 0. It is R cube only. So V1 union V2 is R cube. So what is the dimension of R cube? 3. It is same as we have solved it here. Okay. So that was about the dimension. Now there is one more thing known as null space. What do we mean by null space? So what is null space of matrix? Basically the solution of this equation, right? A into x will be null space of A. And the dimension of my null space is called as nullity. it is equals to n minus rank of A, the formula. Okay, dimension of null space is called as nullity, that is equals to number of free variables, that will be equals to n minus rank of A. I will come to that. Let us find out the null space for the following matrix. With this we will understand what is actually a null space. Okay, so basically null space is nothing but the solution vector of A into X equal to 0. So it will be solution vector of this one. So this is my A, 3 minus 1, 2, 2, 0, 1, 1, 1 minus 1. Into x1, x2, x3. Okay, this will be equals to 0, null matrix, null solution. So here I will get few equations, right? So this will be a homogeneous equation. This is a homogeneous equation. And what kind of solutions do we get for homogeneous equation? So either we will get zero solution, or either we will get trivial solution or non-trivial solution, right? When do we get non-trivial solution? When the determinant of my matrix A is 0, then we get a non-trivial solution. So we will find out the determinant of this matrix and we will check if it is 0 or not. So if I find out the determinant of this matrix, right, this will be, I will copy the elements. This will be 3 into minus 1. Okay, let me just solve this properly. So what I will do is I will multiply 2 and then subtract. So this will be 1, 1 minus 1, 2 and then subtract. This will be 3. I'll multiply 3 and then subtract from the row 1. So 3 times this and minus 4 minus, so this is 3 times this, that is 5. Okay. So this will be okay, so this will be 1 into 1 into 4 into minus 4 into 3 into minus 2 into 5, right? So this will be minus 12 plus 10, which is minus 2. So it is non-zero. So if it is non-zero, that means my rank of A is 3. That basically means then I will not have infinitely many solutions. If you remember the determinant, right, this was my Kramer's rule, where in the bottom I used to have the determinant of A and in the top the determinant of that matrix x1, right? So if both of these is 0, then only I will have infinitely many solutions. So here, right, determinant of A is 0 and determinant of dx1 is already 0, right? And determinant of A is not 0. Determinant of A is not 0. So the solution will be x1 will be equals to 0 actually. I hope you remember. Go back to the pages where we discussed that if both the determinant of A is 0, then, and it is a homogeneous equation, right, then I will have infinitely many solutions. But here determinant of A is not 0, then I will not have infinitely many solutions, right? I will have trivial solution, x1 equal to 0, x2 equal to 0, x3 equal to 0. This is my only possible solution. Okay, so my my null space for this particular matrix, right, is 0, 0, 0. So basically all the variables are fixed. x1, x2, x3, all the variables are fixed. That means my nullity is 0. I don't have any free variables. What is nullity? Nullity is 3 minus rank of A. Previously also I discussed about nullity, right? So here I am calculating the null space of A. So nullity will be 3 minus rank of A, that is rank of A is 3, so it is 0. So I don't have any free variables, 0 free variables, right? Because all the variables are set to what value? 0. All the variables are set to value 0. Okay, let's do it for the second one, right? Second matrix. So it is 1, 2, 3. 1, 2, 3, 3 to 1, and 4, 4, 4, 4, 4, 4. If I check the determinant of this matrix, right, what will happen if I check the determinant of this matrix? So this will be how can I solve it? So again, what I will do is I will uh, multiply by 3 and then subtract. This will be minus of 4, this will be 3 and then minus of 8, this will be 4 times this will be 0, this will be 4, it is minus of 4, this will be 4 borrow minus of 8. So here actually the determinant is coming out to be 0. Determinant is coming out to be 0, right? Because these two are identical, determinant will be 0. Now if determinant is 0, now you check the inner matrix. So inner matrix, this determinant is coming out to be non-zero. That means the rank of A is 2. So nullity will be actually 1, that is n minus 2, that is 1, right? So I will have a free variable. Can you verify it? Yes, we can verify it. How can I verify it? I can show you. So let me form the augmented matrix, right? What is my augmented matrix? 1 2 3 here, okay, 1 2 3, and on the right hand side I have 0 0 0. How do I find out the solutions? So simply what you can do, right, I have to find the solutions of x1, x2 and x3. So I will convert this into row echelon format, right, or Gauss elimination method. So if I add these two rows and then subtract, this will be totally vanished, right? So this will be gone. So if I add these two rows, if I do, so row, I can do one thing, row 3 will be changed to row 3 minus row 1 plus row 2. So this will be totally gone, vanished. This will be 0 0 0 0, this will be 3 2 1 0 1 2 3 0. Now I will vanish this particular element. So I will multiply 3 and then subtract. So if I multiply by 3 and then subtract, what will this become? This will be 1 2 3. If I multiply by 3, right, and then subtract, this will be 0, this will be minus of 6, and multiply by 3 and then subtract, this will be minus of 8, sorry, minus, not minus of 6, minus of 4 and minus of 8, 0 0 0 0 0. So from this last equation, right, what do I see? That 0 is equals to 0. So I am free to choose any value for x3, or you can assume anything. Basically 0 is equals to 0 is always valid, right? This equation is gone, so only this equation is left. So from here what I can deduce that my minus 4 into x2 minus 8 into x3 is equals to 0. Okay, so from here x2 is equals to minus of 2 x3. This is one equation that I get, x2 equals to minus of 2 into x3. And in the third one, right, let me just arrange a bit of space. Okay, this one is the second question, this one is the first question, right? So what I can say, so here, right, okay, let me write the next equation. Next equation is x1 plus 2x2 plus 3x3 equals to 0. So basically from this equation, right, I can say that I know this, right, x2 is equals to minus 2x3, so I can replace my x2 with x3. So this will be x1 plus x1 minus 4x3 plus 3x3 equal to 0, or x1 equals to x3. So I get the third equation. So basically now I can form my solution vector of the null space. I can form my null space. Basically what will be my null space? That is x vector. It will be like x1 is x3, and x2 is minus 2x3, and of course x3 is x3 itself, right? I'm just writing in rough, please don't assume that my handwriting is like this, because we're writing in rough because we're doing revision here, right? So we're writing things in a fast manner. So x2, x3 is x3, right? So if I take common, if I assume that x3 is some alpha, right? So my null space becomes alpha into 1 minus 2, 1, correct? So how many free variables I have? 1, x3. I can choose x3 to be any value, right? Automatically x1 and x2 will be set. So number of free variables is 1. That is what we have calculated. That is nullity, dimension of my null space. Okay. This is my null space. This is my null space. Okay. This is my null space, and the nullity is 1. One variable is free. Okay. So the third one, I want to try you out by yourself. I want you to try. Okay. It will be a bit lengthy. I'm not solving it. I can tell you the solution. Basically, the solution would be like, you can try it out and tell me in the comments below how many free variables we'll have. The rank of A will come out to be 2. That is the answer that I can tell you. So tell me in the comments below how many free variables I will have. What will be the dimension of my null space if the rank of A for the third question is coming out to be 2. Okay, that is what I'm leaving you up to as a homework. Okay. So there are few small things, few small matrix as well. Rotation matrix. Okay, these sometimes have came in GATE actually. So rotation matrix is nothing but just like a transformation. So if I have a rotation matrix here, and if I have a xy vector, right, and if I multiply by the rotation matrix, it will be transformed by theta angle. Its magnitude will be same, just that we will transform it to theta. It is nothing but I'm shifting this vector by a theta angle. I'm rotating this vector by theta. Magnitude I'm keeping same. I'm just rotating the vector by theta. That is what a rotation matrix does. There are like rotation matrix will be orthogonal. First of all, rotation matrix will always be orthogonal. Okay, and the format will be something like this. Like there are for 2 cos 2 matrix, right? There are mainly these two types of rotation matrix: cos theta minus sin theta cos theta. One thing you will observe is that the magnitude of the row and the magnitude of the column, right, is always, length of the row and length of the column is always 1. What do I mean by it? So if I find out the length of the row, how do I find out length? So I square each elements, right? Square each element in the row and then take the under root. Sin square plus cos square theta is 1. So under root 1 is 1. Again, you will find out the length of the column is also 1. Also the dot product, right? If I do the dot product and then add those components, it will come out to be 0. So basically each vector, right, let's say this is x vector x1 and this vector is x2. So x1 transpose x2 will come out to be 0. The inner dot product will come out to be 0 basically, right? Inner dot product will come out to be 0. You can try it. So x1 vector is cos theta sin theta, and x2 vector is minus sin theta and cos theta. Okay. So what is x1 transpose into x2? So x1 transpose will be cos theta sin theta x1 transpose into x2, that is minus of sin theta cos theta. So if you calculate this value, right, if you calculate this value, what will you get? So I'm just doing this here itself. So you will get 0. So cos theta into minus sin theta will be minus cos theta sin theta, and sin theta into cos theta will be plus cos sin theta cos theta. This will come out to be 0. So basically their inner dot, if a matrix is said to be rotation matrix, right, basically their inner dot product must be equals to 0. That is x transpose into x2, x1 transpose into x2 will be 0, and of course they must be unit normal. So basically their length will be 1. So basically rotation matrix is nothing but a subset of orthonormal matrix, right? Orthonormal matrix. So we have taught what is orthonormal matrix. I hope you remember it, right? That is what my rotation matrix is. In 3D, you can represent your rotation matrix like this. There are many variations. Do we need to remember? No, actually, but at least we remember the 2D format. Maybe they will ask someday, but 3D format, don't need to remember. Just see how a rotation matrix works. Okay, and last matrix is normal matrix, where my A theta. I hope you remember what is theta. Theta is basically conjugate and then transpose, right? We take the conjugate and then take the transpose. That is what my theta is. So if I am performing A theta into A, and that is equals to A into A theta, but it is not equals to I, identity matrix, then it is actually not unitary matrix, it is called as normal matrix. So maybe this term can be asked, so that's why I am covering everything. So I have tried to cover every single thing, even though this vector space, these very few people cover these things, right? Still I have covered every single thing. I know few things will be a bit difficult, because if you are studying for the first time, this can feel bit of overwhelming, but the initial stages I have explained very well. The eigenvectors, eigenvalue also I have given my best, okay, because that is the most important part, right? Determinant, eigenvector, eigenvalues, and solutions of linear equation. So from there only mostly question will be asked. Types of matrix they can ask, and vector space I have seen little question get asked from EC domain. From CSIT they will ask many questions, but from EC they ask smaller amount of questions. So now we will start with the question solution. So yeah, let's now solve few GATE PYQs. So first we will solve EC, then EE, then IN, and so on, right? So this is the first question. This came in GATE 2021. So here, like, trust me, you will be able to solve most questions whatever we have discussed in today's lecture, right? In today's video, you will be able to solve with that knowledge. You will be able to solve most of the questions. Okay. So yeah, this is a question. So which we says that we have a real 2 cross 2 non-singular matrix. That means its determinant is not 0 with repeated eigenvalue is given as this. Let x is a positive real number, the value of x will be. So we have repeated eigenvalues. What does it actually mean? If I have repeated eigenvalues, if I write down the characteristics equation of this particular eigenvalue, right, it will be lambda square minus of trace of a, that is 4 plus x, okay, plus determinant of a. Determinant of a is 4x plus 9 equal to 0. And they are telling we have repeated eigenvalue. Repeated eigenvalues mean that if lambda equals to 1, 1 or lambda equals to 2, 2, right? So that means it has to be a perfect square. It has to be some format lambda minus alpha whole square equal to 0. Then only I will get repeated eigenvalues. Otherwise, there is no possibility of getting a repeated eigenvalue. In this case, lambda will be equals to alpha comma alpha, right? So basically, it has to be in this format: lambda square minus 2 lambda plus okay, not 2 lambda actually, minus so here there will be some. So if I break this down, right, if I break this down and repeated eigenvalue they're telling me, so this will be lambda square minus 2 alpha into lambda plus alpha square equal to 0. So I can equate minus 2 alpha and alpha square, correct? So yeah, if I equate this alpha and minus 2 alpha, right, so 2 alpha will be equals to 4 plus x, and alpha square equals to 4x plus 9. Okay, alpha square is 4x plus 9. So how can this help me? Okay, and alpha x is a real positive number. We have repeated eigenvalues. If I have repeated eigenvalues, that means okay, if I have repeated eigenvalues, yeah, this has to satisfy. So it will be a perfect square. So it will be 2 alpha will be equals to this. Yeah, alpha square equals to this. Okay, and x is a real positive number. So if I multiply by 4, right, this will be 8 alpha. This will be just give me 1 second, it will be turn off the Wi-Fi. If I multiply by 4, this will be 8 alpha, 16 plus 4x. Okay, 16 plus 4x. And now just give me 1 second. Now what will I do is we can actually okay, we can do one more thing, right? Okay, we can do one more thing. So I already know what is my alpha. Alpha is equals to x plus 4 divided by 2. So I can put the value of alpha in this equation. So this will be x plus 4 divided by 2 whole square equals to 4x plus 9. So this will become, so this can go, this 2 can go on that side. This will be x square plus 8x plus 16 equals to 4. So 4 into, so 16x plus 36. Okay, so this will become x square minus 8x minus 20 equal to 0. From this we can get the solution of x, right? Now we will obviously ignore the negative solution. We will only take the positive solution because they have mentioned in the question that x is a real positive number, correct? So x is a real positive number. So if I solve this quadratic, minus of b plus minus b square minus 4ac, so plus 80 divided by 2a. So that is, this is under root 144, that is 12, right? So 8 plus minus 12 divided by 2. So this is actually 10 and minus of 2. Of course, we will not take the negative solution, we will take the positive one because they have mentioned that x is a positive number. So x equals to 10 will be my answer for this particular question. This is a good question, right? So it's not that simple, but it's not that difficult as well. They have told you that x, like we have repeated eigenvalue, so it will be like a perfect square. If it's like a perfect square, I can break it down, then I will compare my 2 alpha and alpha square, and from here I will get the value of alpha, and that value of alpha I will put in this equation, and then I will solve this quadratic equation. I will get two values, out of which I will remove the negative solution, I will take the positive solution. This was a good question actually. Okay, let's solve this one. Now if the vectors this and this in R cube vector space are linearly dependent, if they're linearly dependent, what does it mean? Basically the rank will be less than 3, the rank will be less than 3. And when does a 3 cross, like how can I satisfy the rank is less than 3? Basically if I take the determinant of this matrix, right, the matrix formed by the vectors must be equal to 0, then only the rank will be less than 3. Rank has to be less than 3, right? Rank of these 3 vectors v1, v2, v3 must be less than 3, then only they will be linearly dependent. Already we have been discussed about this. So if I combine this v1, v2, v3 vector, right, that will be this. v1 is this, v2 is 7 3x, and your v3 is 2 3 1. This has to be equal to 0. So from this I can easily calculate what will be the value of x. So I will add these two rows so that I can make this 0 over here. So this will be 1 7 2 0 10 5, and then if I multiply 2 and subtract right, if I multiply 2 and subtract, this will be 2x minus 14 minus 3 equal to 0. Am I correct? So I'm multiplying by 2 and then subtracting, so this will be gone. This will be x minus 14, this will be 1 minus 4, that is minus 3. I'm adding these two, this will be 10, this will be 5. So the determinant of this will be minus 30. So 1 into minus 30 minus of 5 into x minus 14 equal to 0. So x minus 14 will be equals to minus of 6. Okay, x minus 14 will be equals to minus of 6. So x will be equals to 4 4, that is 8. Yes, x will be equals to 8. This will be the answer for this particular question. Pretty straightforward and easy, right? Not that difficult, just basic concepts. So we have learned what is vector, how are they linearly dependent. Let's move on to the next one. So this is how simple the questions will be. This is how simple the questions will be. So with this marathon also, you will be able to solve most of the questions. Obviously, I cannot guarantee 100%, but you will be able to cover most of the questions. Okay. So let's solve this one. Consider a system of linear equations ax equals to b. Okay, the system of equations admits unique solution, infinitely many solution, no solution, exactly two solution. This is anyways gone, so we have never studied this, right? Exactly two solution, no. Either these three are the possible cases. So what do I see is, first of all, what is the, how many number of unknown variables I have? 3, right? Because this is x1, x2, x3. Okay, and first of all, I see I have only two equations, so I cannot have a unique solution, not possible at all. So unique solution option is automatically gone. It is an inconsistent set of solution, like, sorry, unique solution option is gone. Either I can have infinitely many solution or no solution. So we have to check that. When I will have infinitely many solution, when my rank of a b will be same as rank of a, then I will have infinitely many solution. Anyways, rank of ab is, and it is less than number of unknowns. In this case, anyways, it is less, right? First of all, I can see that I only have two equations and three variables, so unique solution is gone out of the picture. So we will find out rank of A. So if I see what is the rank of A, I see row 2 and row 1 actually are linearly dependent, right? So row 1 is negative of row 2. So simply the rank of A, right, is simply 1, because the rows are linearly dependent on each other. What about rank of AB? So if I see the rank, one second, let me change the color. Yeah, rank of AB. So what is my augmented matrix AB? So that will be 1 minus root 2 minus 1 root 2 3 minus 3 1 3. Okay, this is my augmented matrix. So what I can say, that the augmented matrix, right, if I include the augmented matrix, now what will be the rank become? The rank will be 2 actually, because you see that now row 1 is not equals to minus of row 2, right? I cannot linearly write my row 2 in terms of row 1. That is not possible, because this 1 and 3 is not negative. These are not negative of each other. I cannot do it. So now the rank of A colon B combined is basically equals to 2, but rank of A is 1, so that is not equals to rank of A. So what kind of solution is this? This solution is inconsistent, right? There is no solution. So if there is no solution, that means option C will be correct, right? Very simple. So all these things we have already learned, right? So they are asking from these things only, the simple things only they will ask. Okay, let's solve the next question. So we have this alpha beta, which are two non-zero real numbers, v1 v2 be two non-zero real vectors of size 3 cross 1. Okay, v1 v1 v2 are two non-zero real vectors of 3 cross 1, right? So basically v1 will contain some alpha 1, beta 1, gamma 1, and v2, I hope now that's why I was putting emphasis on what does vectors mean. Okay, so because these things will be there in the question, you have to understand what do they mean, right? What does this vector term means? v1 is alpha 1, beta 1, gamma 1, and v2 is alpha 2, beta 2, gamma 2. Okay, so what I can say, one more information they have given to us, that the this v1 dot v2 is 0. So basically the v1 and v2 are orthogonal, and the like inner product is 1. Sorry, and this is 0. So basically the vectors are v1 and v2 are orthogonal. Directly I can say v1 and v2 are orthogonal of each other, right? This property is nothing but orthogonality property. Let A be a 3 cross 3 matrix which is a combination of alpha into v1 v1 transpose and beta into v2 v2 transpose. The eigenvalues of A will be, okay, what will be the eigenvalues of A? Okay, so what you can do, you can take any example, you can take any example. Okay, B2 non-zero, B2 non-zero real vectors. Okay, if you are having difficulty understanding this, you can solve this with example. Let us take an example that, let me assume that V1 is 1 0 0 and V2 is 0 1 0. So this is also a non-zero three-dimensional vector, and these two vectors are orthogonal with each other, right? I will take the simplest case. I will take the simplest case. So if I do inner product, that is V1 V1 transpose, what will it be? So V1 V1 transpose, right, is nothing. So V1 is 1 0 0 and V1 transpose is 1 0 0. Okay, this will be 1 and 1 into 1, this is gone. Then the first row and the second column, this will be 0, this will be 0, this will be, all this will be 0. Okay, into alpha. Alpha is here. And what will be V2 into V2 transpose? V2 into V2 transpose will be same, right? But in the second column. So this will be now, so V2 into V2 transpose, right? So V2 will be 0 1 0 into 0 1 0. This will be equals to zero. This first row will be always 0, second row will be 0 1 0, third row also will be 0. So I am adding these two, and that is my A matrix. So A matrix will be basically, A matrix will be alpha 0 0 0 beta 0 0 0 0. So what are the eigen? They're asking me what are the eigenvalues of A. Eigenvalues of A, it is simply a diagonal matrix, right? So this will be alpha, beta and 0. Okay, so alpha, beta and 0 are my eigenvalues of my matrix, correct? So option A, option A is correct, that alpha, beta and 0 are my eigenvalues. Now how can you actually solve it without all this, right? Without taking an example. Can I solve it without taking an example? So what is my eigenvalue property? That A into x must be equals to lambda into x. Okay, and my A is this matrix, right? A is this matrix. Okay, A is this matrix. Okay, give me 1 second. Yeah, hello, mic testing. Yeah, I'm just checking the mic. A into this, right? So A into lambda. So A is this vector. So I can break this A down here. So this can be broken. A is what? A is alpha into V1 V transpose, V1 V1 transpose plus beta into V2 V2 transpose. Into x. Okay, into x. So x is there, that I don't care. Okay, okay, already this V1 into V1 is 1, right? That is already given to me, right? So this is I. Actually they are kind of okay. V1, so V1 into V1, V1 transpose into V1 is given to me is 1. Okay, so the question is already done, right? So still I am doing something, I'm thinking about something. So one thing I am thinking, that if I with A, right, this is my A, this is my actual equation, this is my actual eigenvalue equation, this is my A. So if I multiply, if I post multiply V2, if I post multiply V2, what will happen? If I post multiply V2 on both sides, A into V2. This will be alpha V1 transpose into V2 plus beta V2 transpose into V2. Okay, and I know V1 transpose into V2 is nothing. V1 transpose into V2 is nothing but 0. So this will be 0. Right, this is 0, and V2 transpose into V2 is 1. V2 transpose into V2 is 1. So this will be 1, this will be 0. So my A into V2 becomes beta into simply V2. So this is nothing but the eigenvalue equation. So here what is my eigenvalue? What is my eigenvector? Eigenvector is V2 eigenvector, right? And eigenvalue is beta. Similarly, if I multiply by V1, A into V1. If I multiply by V1, this will be alpha into V1 transpose into V1 plus beta into V2 transpose into V1. So this will be again 0, this will be 1. So your A into V1 is equals to alpha into V1, right? So again your eigenvalue is alpha, eigenvector is V1. So similarly another eigenvalue is simply 0. Anyways, you can see from all the options one eigenvalue is already specified 0, right? So we don't have to check for that one. So obviously option A will be correct. So I told you two methods, right? Taking an example or directly solving it. Okay, let's solve the next one. So these kind of questions actually do get asked, right? This vectors and stuff, you should understand what is a vector, what is a mutually orthogonal vector, all those things you should understand. So let the sets of eigenvalues and eigenvectors for B matrix B be lambda k, where k is between 1 to n and vk be 1 to n. So basically eigenvectors are these is my eigenvector set. Let's say v1, v2, v3, so on, right? This is my set of eigenvector for matrix B, and set of eigenvalues for matrix V is lambda 1, lambda 2 and lambda 3. Okay, for any invertible matrix P, the sets of eigenvalues and eigenvectors of a matrix A where B is P inverse AP respectively are. So do you remember some format like this? This is nothing but a similar matrix, right? Similar matrix. And in a similar matrix, what have I taught you? In a similar matrix, your trace like A and B, they're asking me what are the, for any invertible matrix P, the sets of eigenvalues and eigenvectors of matrix A. So we know A and B, this equation, if this equation is written, right, that means A and B are similar matrix. I have taught you, right? I have taught you everything. A and B are similar matrix. Now if A and B are similar matrix, right, that means what? That basically means that your trace of A will be equals to trace of B. Your determinant of A will be equals to determinant of B. Your eigenvalues of A will be equals to eigenvalues of B. But your eigenvectors, right, will not be equal. Vectors of A will not be equals to eigenvectors of B. These will not be equal. Okay. So your eigenvalues will be same. So I can see option B, C, D, all of them are saying eigenvalues will be same. But how can I find out the eigenvectors? So you can easily find out the eigenvectors. So what will be my eigenvectors? So I know that my B matrix, right, that's why you should know how to derive, because you will not be able to remember every single thing. Even if you forget about the eigenvalue property as well, still you will be able to solve this question. That's why I have told you how can I derive everything, right? So here if you see that this property will hold B into V, let's say Vi will be equals to lambda I into Vi, correct? If Vi is an eigenvector, then its corresponding eigenvalue will be lambda I and it will be times Vi. Now what I will do, is I will replace my B with A. I will try to do that, right? So my B is P inverse AP, correct? B is P inverse AP. So I will replace my B with A. So this will be P inverse A P into Vi equals to lambda I into Vi. So I will pre-multiply by P. I will pre-multiply by P. Okay. So now if I pre-multiply by P, this will be AP. APVI equals to lambda. Lambda is just a scalar, right? So if I pre-multiply by P, so P inverse into P will be simply I. So this is anyways gone. This will be P into Vi. Am I getting a symmetry here? So eigen value of A is lambda I, but eigen vector of A is P into Vi. Eigen vector of A is P into Vi, right? Because it is nothing. Let's assume this. Let me write this as X, right? So this gets in the format A into X equals to lambda I into X. This P into Vi is a matrix X. So it is nothing but the characteristics equation format. So this X is eigenvector. So eigenvector is P into Vi. So eigenvector changes to P into Vi, P into Vk. Here also it becomes P into Vk. It is not Vk. Eigenvalues will be same. If you see, eigenvalues are same, right? Eigenvector changes. So it becomes P into Vk. Okay. But eigenvalues will be same. Okay. So that's why option B will be correct answer. Sorry, not option B. Sorry, option C will be correct answer for this question. So that's why even if you forget the properties, right, always remember how to derive things. If you remember how to derive things, you will be able to solve. Even though if you don't know what is a similar matrix, still you will be able to solve this question. That's why always I have emphasize on the derivation, right? I have told you how to derive things. In this particular case, I had not derived the eigenvector property, but it was there, right? It was shown, the derivation was there. Okay, so I hope you remember the stuff, correct? So yeah, let's now move on to the next one. So here we have x, which is a column vector, okay, and the length of x is x1 transpose into x whole under root. The trace of a matrix P x transpose will be equals to what? Okay, so x is a column matrix, so we can choose any random column matrix, right? I can choose any random column matrix according to my wish. Okay, so yeah, let me choose a random column matrix. Just give me 1 second. Okay, so let me assume that it is 1 comma 0. So what is the length? Length is under root of x transpose x, so 1 0 into 1 0, so which is 1. So this is 1 only. Okay, this is 1. Okay, so now what they are asking, what will be the trace of matrix P, that is x into x transpose. So x into x transpose is basically 1 0, sorry, 1 0 into 1 0. So it is this row, this will be 1 0, this will be 0 0. So the trace here is 1. So either it will be option A or option C. Okay, so by basically by taking an example, I have broken down into option A or C. You can now choose any random values actually. Okay, let me choose a random value. Let me choose it to be alpha beta. So this will be alpha beta, alpha beta. So this will be under root alpha square plus beta square basically, and x into x transpose will be basically your alpha beta into alpha beta. So this will be alpha square plus alpha beta and alpha beta plus beta square. So basically the trace of this matrix, right, is sum of the diagonal elements. It is nothing but alpha square plus beta square, which is basically square of my length. It is square of my length, so it will be L square. So L square will be my correct answer for this question. Simply you can solve, right? You can simply assume any random values and then solve. You could have also assumed to be a 1 cross 1 matrix. That also would have been valid actually. So you could have just assumed alpha. If it was alpha, right, then what would have been your length? Your length would have been just alpha, right? What would have been your p? P would have been alpha into alpha, that is alpha square. So it is simply L square, right? So that's how simply also you can take, like you can take the easiest of example. You can take n equals to 1, that is alpha, and your trace will come out to be like your p matrix will come out to be alpha square, and trace of a 1 cross 1 matrix is the same element itself, that is alpha square. So it is L square. That's why L square will be your correct answer for this particular question. Okay, option A will be correct answer for this particular question. Let's now solve the next one. So this is the next question. So okay, actually this is not a proper math question, because it is related with control system, but still we will be able to solve it. Okay, so the state equation of a second order system is given, where x of 0 is the initial condition. Suppose lambda 1 lambda 2 are two distinct eigenvalues of A. V1 and V2 are the corresponding eigenvectors. For constants alpha 1 alpha 2, the solutions of xt of the equation will be. Okay, so they are asking me what will be the solutions of xt. So actually this is not a but still we can say this also as a solution. What will be the solutions? What will be the solution of xt? So okay, we will take this question in control, because this question is actually for control. We will skip this question. This question is for control. Okay, because this is a state space equation. We have few theory left for that, so we will do it in control system. Let's solve this one. So we have a let me change this is question 7. We have a 3D vector space contains set of real numbers and the value of alpha for which the set does not form a basis of R cube. Does not form a basis. What forms a basis? If all these three vectors are independent of each other, then it will form a basis, right? If they're dependent, then it will not form a basis. So basically what I have to do, I have to equate with 0. I have to make the determinant 0. It is just a repeated question, right? Just they have told you in a different format, that's it. They have told you in a different format, but you have to make the same thing, that is make the determinant equal to 0, make them dependent. If they are dependent, then only they will never form a basis. We have discussed, right? If they are independent of each other, then they can form a basis. With a linear combination, I can cover any three-dimensional space. So this, right, if I want to find the determinant of this, how can I find the determinant of this? So what I can do is, this 1 times 3 I can subtract here, and 1 times 2 I can subtract. So this will be 1 times 2, 0, times 2 if I subtract, this will be 10, 7. This will be 2, so alpha minus 14. So 2, 0, 10, 7, alpha minus 14. And if I subtract 3, 1 times 3 and 0, then 3 if I subtract 15, 16, 3 minus 18, 321 minus 18 minus 5, equal to 0. So this will be 1 into 7 into minus 18, right, minus 16 into alpha minus 14. Okay, where numbers equal to 0. So if I solve this, right, this will be 7 into, so 8 into 7 is 56, 56 and 7, so 126. Okay, I can simplify this, right? If I divide by 2 on both sides, this will be 7 into minus 9 minus 8 into alpha minus 14 equal to 0. So this will be minus 63, minus sign anyways will go away. This will be 63 plus 8 alpha minus 32 112 equal to 0. So your 8 alpha comes out to be this comes out to be, I think I'm doing some mess up here. Let me just check. So this will be one time twice. Okay. No, this is alpha minus 14, correct. So 10 minus 3 is correct. 3 times this, so 15. Okay. Sorry. This will be actually not 16. This will be 14. 3 times this, 21. Yeah, minus 18, correct. Yeah, correct. So this will be 14. This will be 14. This is 7. So this is 7. This will be 7 times 14. So 28. 98. So this will be 35. So 7 alpha equals to 35. Alpha will be equals to 5. Alpha will be equals to 5. This is the answer. This is the answer, basically alpha equals to 5. Let's solve the next one. So this question will be 8 question, not 7, 8 question. So consider the matrix, this right word K is a positive real number. Which of the following vectors is eigenvectors for the matrix? So you simply have to solve this using the characteristics equation, and then you will be able to find out the eigenvector basically. Or you can individually multiply each of them, right, and then check which will be eigenvector. Is it MSQ? It is MSQ, is and R, right? So what you can do, either you can find the eigenvectors by yourself, or you can simply multiply. So the like a vector will be eigenvector if I multiply by that vector, right, and I get back the same vector, it will be a eigenvector. I don't care what is my lambda. So let me multiply these two matrices. So if I multiply these two matrices, it is 1k and 2 1 into 1 under root 2 by k. Okay, so what do I get? This will be 1 times 1, that is 1. This will be k, which is some coming out to be some negative under root 2k, right, which is actually yeah, which is something else. So I can actually, let me just, okay, let me fully do it, right, let me fully do it. 2 minus under root 2 by k. So can I take anything common here? No, right? Can I take anything common here? 1 minus under root 2k. No, I cannot take anything common here, right? No, let me keep it for now. Let me solve these two, right? These two seems but also this also can be answered. Okay, so let me check for other options. Option B, if I check, right, this will be 1k 2 1. Let me check for option C, under root 2k 1. So this will be under root 2k plus k. This will be under root 2k 2 into under root 2k plus 1. Again, can I take, okay, yeah, now I think I can take something in common, or can't I? So if I take this one as common, so I have to basically take under root 2k plus 1 common, right? Is that possible? No, that is not again possible. Let me check this one. Okay, let me anyway solve it, right? Otherwise it seems like I will, like, this is also a valid method. Let me first let me use the normal method, that is finding out the eigenvalues. So let me find the eigenvalues. 1k, like of course you can take the value of k anything, then solve. Like let's say you can take the value of k to be 2, right, and then solve. You can do it actually, but I don't. Okay, you can do it, because if I take the value of k equals to 2, right, then everything simplifies. This will be 1 minus 1, this will be 1 1, this will be 2 1, this will be 2 minus 1. Okay, you can do that. You can take the value of k to be 2 and then solve. So if I take the value of k to be 2, right, then this will be much simpler. This will be 1 2 2 1, and let me check for the first option, option A. Option A will be 1 comma minus 1. Okay, so 1 comma minus 1, if I do, this will be what, 1 into 1, 2 into minus 1, so this is minus 1, and 2 minus 1, so 1. So yeah, this is actually proper. This, like for this, like if I take the minus 1 common, right, this will be 1 minus 1, which is same exactly as my eigenvector. So we are getting proper. So A is possible. A is possible. Let me check for B. So again 1 2 2 1 1 1. If I do 1 1, I think this will not be possible. This will be 2 plus 1 plus 2, that is 3. 1 plus 2, that is 3. Oh, this is also possible, right? Yeah, this is also possible. If I take 3 common, right, I'm getting 1 1. So 3 is my eigenvalue and 1 1 is my eigenvector. So this is also possible. So let me check for C. So I can only have 2 eigenvectors, right? I cannot have 3, right? Because it is a 2 cross 2 matrix. So I will cross verify whether these are also coming out to be true. This should not come out to be true, right? We can cross verify. So I will have my matrix to be 1 2 2 1 and eigenvectors to be 2 1, correct? Because this is like 2 into 2, under 2 into 2 is 2 comma 1. So this will be equals to 2 into 1, that is 3, and this is also equals to 2 into 4 into 1, that is 4 plus 1, that is 5, right? So again it is not getting scale, right? It is not getting scale. These are not same, correct? So yeah, this is not an eigenvector. And again let's check, you can check this one also will not be eigenvector. This one also will not be eigenvector. You can check this. Okay, like also you can do it using the same method. You can do a minus lambda I. You can keep the k as it is, find the determinant equal to 0. From there you can find the eigenvalues. Okay, you will solve, you will get these values. So whenever you're in the exam, right, try these tricks, take few examples. Okay, don't try to solve it using k. That will mess up, right? You will like it will take you more time to solve, right? Of course you don't want to consume more time, you want to save your time. So because initially I was doing something wrong, then I backtracked, right? Then I backtracked and finally I'm able to solve it properly. Okay, so I hope this part is clear. How am I solving it? Okay, so yeah, let's now go and solve the next question. This one, this came in EC 2025. So here we have a matrix A, alpha beta gamma. For what combination of alpha beta gamma, the rank of A is at least 3. Rank of A is at least 3. Okay, so at least it has to be 3. If gamma is non-zero, right, if gamma and beta are non-zero, okay, gamma and beta are non-zero and alpha is 0, and here are so if alpha is non-zero, so alpha is non-zero, correct? So alpha is 0. If alpha is 0 and beta is non-zero, if beta is non-zero, right, what is the determinant of this matrix? What is the determinant of this matrix? So determinant of this matrix, right, this is 0. So this is anyways gone. This will be 3 times 7 minus 6 times 4, which is non-zero, right? 3 times 7 is 21, 6 times 4, which is non-zero. So the determinant of this 3 cross 3 minor is non-zero. So rank will be definitely 3 here at least for the first case. For the second case, if all of them are 0, if alpha beta gamma all of them are 0, this is 0 0 0, so this 2 rows are automatically gone, then rank automatically becomes 2. So this anyways will not be valid. My rank must be at least 3. Let's now see the third option. So in the third option they are telling me that beta and gamma are 0, alpha is not 0. So beta and gamma is 0, alpha is not 0. Okay, if alpha is not 0, again if I check the determinant of, like, this is 0, right? If I check the determinant of this one, right, it will be 3 times 8 minus 6 times 5. So 24 minus 30, which is again non-zero because alpha is non-zero. So again 3 cross 3 determinant is coming out to be non-zero. That means the rank will be at least 3. So again this option is again correct. Now alpha, beta, all of them are not equal to 0. This will be again true. If all of them are not equal to 0, again, anyways this option was already satisfying. This option will also be satisfying, right? So option 4 is also correct, that my rank will be 3. So option only 1, 2, 1, 3 and 4. These 3 options will satisfy where my rank will be 3 at least. Okay, very good question, very simple question, but very elegant question. Okay, so you are seeing, right, they are asking questions from rank, they are asking questions from this linear dependency, they are asking questions from solutions, they are asking questions from eigenvectors, eigenvalue, even they are asking questions from vectors. So I have covered everything. Did you had any difficulty while solving the questions, right? So that's why PrepFusion. That's why PrepFusion. If you are enjoying, make sure to comment down below, and of course press the like button. So let's solve this last one, last easy question. Okay, and don't worry, I will take the state space question, but in the state space. That is actually a control system question. I will not take it here. Okay, so we have a real valued scalar variable x. Okay, and a and b are given, and minimum of x. This is nothing but Euclidean normal. Basically it is nothing but the length of this matrix. Okay, so what is the value of the minimum of the length of this matrix? Ax into b. That is what they are asking me. Okay, for a real valued scalar variable, what will be the minimum of this, right? So basically it is the length, right? So what is ax minus b? So ax minus b, so x will be some, x is a scalar variable, x is just a scalar variable. So what is a into x? It is simply 1 into 1 into x. X is just a scalar variable, so I will multiply it with all the elements. X is just a scalar number, right? I'll multiply it with all the elements, so x. So I have to do ax minus b, so x. Just give me 1 second. X minus b. B is 0. (302). Okay, so this will be equals to x minus 302, and we have to find out the length of this, right? Length, simply it will be x square plus x minus 302 whole square. Okay, and this we have to minimize. So this whole under root is some variable y, right? And we have to minimize this variable. So what I will do is I will square this. I will square this function, right? Y square, that I will name another function g of x, right? And I will minimize this function because we have to minimize this. They have asked me what is the minimum value. So I will simply minimize this. So how to minimize? Differentiate it, right? Differentiate it with respect to x. So I will differentiate this with respect to x. So I have to write the minimum of g of x. Basically minimum of y will happen when y square will be minimum, because it is square root, right? When y square will be minimum, y also will be minimum. For my simplicity, that's why I have just squared it, because I don't like square root. Okay, so this will be minimum of g of x, right? So what I have to do, I have to do g dash of x and equate it equals to 0. So g dash of x will be 2x plus 2 into x minus 3 root 3, okay, equals to 0. This will be 4x, or I can divide by 2 on both sides. This will be 2x is equals to 3 root 2. for x equals to 3 by root 2, right? What are those? They are asking me the minimum value of this. They are not asking me at what x value this is minimum. They are asking me what is the minimum value of this, right? So at this value this will be minimum. So I'll put this x in this equation. I'll put this x value in this equation, in not in this equation, actually in this equation. Why? Because I have to find out the minimum of this, right? I have to find out minimum of y. So I'll put the value of x here. So this will become, so y minimum will be under root of x square, that is 9 upon 2 plus x minus 3 root 2. So x is 3 root 2 minus 3 root 2 whole square. Nine by 2 plus, okay, so what will this be equals to? This will be 3 minus 6, so minus 3 by root 2 actually whole square, which is same, right? 9 by 2, so this will be actually 18 by 2, which is 9 under root 9, which is 3. So your answer will be simply 3, right? 3 will be your answer for this question. So yeah, with this we are done with all the easy questions. Now we will start with double E questions. So let's begin with double E PYQs. So this is the first question where we have been given two like a matrix and PQ, which are two real numbers, where it is given that p square plus q square equals to 1. The eigenvalues of the matrix will be equals to what? What are the eigenvalues? So I know one thing, that the sum of my eigenvalues, right, lambda 1 plus lambda 2 will be equals to the trace of the matrix, and trace is coming out to be 0. So the sum must be 0. So here I see this is not possible, because here the sum is 2, here it is possible sum is 0, here it is also possible sum is 0, here also it is possible sum is 0. Next thing is that the determinant of my matrix is equals to my product of my eigenvalues, right, for a 2 cross 2 matrix. So it is actually minus of p square minus of q square, or minus of p square plus q square. So p square plus q square equals to 1, correct? So this will be minus of 1. So the product must be minus of 1. So 1 into minus 1 becomes minus of 1. So this is possible. J into j is minus 1. Already I have a minus sign here. So this is not possible. This becomes plus 1. PQ into minus PQ becomes minus p square q square. So again, this is also not possible. Only option B is the correct answer for this question. 1 and minus 1 will be my correct answer. Okay. Or you can simply solve this. Okay, this is the method 1. Right. Method 2 is what? Solve this equation. A minus lambda I equal to 0. There you will find the roots. Okay, you can solve it, no problem. And you will you just put the value of p square and q square there. Okay, I hope that much you can do. So like the similar only. So let's solve the next one, question 13. So we have a 10 cross 10 matrix such that a raised to power 5 is a null matrix. Okay, a raised to power 5 is a null matrix. Let I be 10 cross 10 identity matrix. The determinant of a plus I will be. What shall be the determinant of a plus I? So for that I need to find out what is the determinant of a, or a, I will let us find out what is the matrix A. So I know a raised to power 5 is a null matrix. So A is a nilpotent matrix. A is a nilpotent matrix, and there is a property of nilpotent matrix. Actually, I forgot to mention that property of nilpotent matrix is that all eigenvalues of nilpotent matrix are 0. Equal to 0. Okay, so all eigenvalues of nilpotent matrix will be 0. So if all eigenvalues of nilpotent matrix are 0, right, how will I find out the determinant? So determinant of a plus lambda I. So I have to find out the determinant of a plus lambda I. So if I am able to find out the eigenvalues of a plus I, let us assume that b is equals to a plus I. right? B is equals to a plus I. If I am able to find out the eigenvalues of B equals to a plus I, and if I multiply lambda b1, lambda b2 and so on together, I will be able to get my determinant of a plus I, right? So how can I find out the eigenvalue? Basically, uh, the let's say the first eigenvalue, right? I can use the Cayley-Hamilton theorem or reverse Cayley-Hamilton theorem. So eigenvalue of lambda b1 will be equals to lambda a1 plus I. I has eigenvalue as 1 only, right? The eigenvalue of I is 1. So lambda a1 is 0. So lambda b1 comes out to be 1. Again similarly lambda b2 will come out to be 1. Lambda b3 will come out to be 1 and so on, right? So the eigenvalues are all 1, correct? Basically I am using reverse Cayley-Hamilton theorem. I am replacing my b with lambda b1 and I am replacing my a with lambda a1. That's it. I am just doing the reverse Cayley-Hamilton theorem. I have taught you how to use the reverse Cayley-Hamilton theorem. So all my eigenvalues are 1. So if all my eigenvalues are 1, then what is the determinant of this matrix B? It will be product of all my eigenvalues. So determinant of a plus I will come out to be simply 1. So 1 will be your answer for this question. That's it. That's how you solve it. So all the eigenvalues are 1. 1 will be your answer for this question. Let's solve the next one. Consider a matrix A which is given. The matrix satisfies the following characteristics equation where C and D are scalars. I is identity matrix. C plus D will be equals to what? So they are asking me what is C plus D. So it is like it will be similar to a characteristics equation, right? So I will compare this with my characteristics equation. So first of all I will write this properly because here A inverse is there, right? So I will multiply by A on both sides. So this will be 6A inverse into A, that will become I. So 6I just give me 1 second. 6I equals to A cube plus CA square plus DA, or I can write my equation as A cube plus 6 A square plus DA plus minus 6I equal to 0. Now I can use my reverse Cayley-Hamilton theorem. So I can replace my A with lambda, right? So this will be lambda cube plus 6A square plus, sorry not 6A, sorry 6 lambda square plus, this should be not 6 actually, this should be C, sorry this will be C, right, not 6. What am I doing? D lambda minus 6I equal to 0. Okay, so what was if you remember, we used to have here plus minus plus minus, and this was supposed to be my determinant of A, this was supposed to be my trace of A, right, this term. So negative sign is there. So here I've, because it is plus C but it is supposed to be negative of trace, right? So I have to write negative of trace. So C is equals to negative of trace of A, because here it is supposed to come as minus trace of A into lambda square, if you remember it, right? And here it will come as this, what was this? This was the sum of my minus of diagonal elements. Okay, so you can verify whether minus 6 is coming, like whether 6 is coming. So this is already negative sign is there, right? So determinant should be 6. So I see what is the determinant here. Simple, it is 6. So it is verified, yes, it is correct. So what will be my value of C? Value of C will be minus of trace of A. So I see what is the trace. Trace is simply 6, right? C will be negative of 6. Okay, and what will be D? D will be plus of all the principal diagonal elements, sum of all the minors of principal diagonal elements. So what is the minor? It is 4 plus 2, that is 6. Four plus 2, that is 6, right? Then I have this element, right? What is this one? It is 1. Okay, plus this is 4. Okay, so this will be 6 plus 8, 6 plus 4, 10, 11. So D is 10 and we have to find out C plus D. This will be simply 5. That's how simple the solution is. If you remember this particular format, that's why I have told you to remember this. That's why we have taught every single thing. We have not skipped anything. So what is the method 2? Method 2 is simply using this equation, right? Determinant of A minus lambda I. If you solve this, right, if you solve this equation, you will get back to the same equation and then you will compare. You will use, after this you will get your equation in lambda and then you will use the Cayley-Hamilton theorem, Cayley-Hamilton theorem to replace your lambda with A, okay, and then you will compare the two equations. That's it, compare these two equations. Okay, so here 11 will be my correct answer for this particular question. Okay, yeah, that's it basically. So let's solve the next one. So we'll solve the next question. So it's not 11, sorry, what did I, 5 will be my correct answer. 5 will be my correct answer for this question, not 11, what am I talking about. 5 will be my correct answer for this question. Okay, so let's solve this one. If e raised to power a denotes the exponential of a square matrix A, suppose lambda is an eigenvalue and V is the corresponding eigenvector of matrix A, then e raised to power lambda is a eigenvalue of e raised to power A, V is an eigenvector of e raised to power A. So which statements are true? So for this, right, you can actually expand your exponential. So what is a exponential series? So I know this, if A, they are telling me that A has an eigenvector V. So this equation will be followed, that is A into V will be equals to lambda into V, right? This is the standard equation of eigenvector. This relation will be followed. Now what is e raised to power A? Can I write this in terms of polynomial? Because I cannot simply do exponential, right, of a matrix. So I have to write this in terms of a polynomial. If you remember, the exponential series is something like this. A by 1 factorial plus a square by 2 factorial. Like here it is simply a raised to power 0 by 0 factorial. That is what this is, right? Then plus a cube by 3 factorial and so on. Okay. So this will be basically 1 plus a by 1 plus a square by 2 plus a cube by 6. Okay. So we know, so what will be the, we know one thing, right? We know what is the eigenvalue. If A has an eigenvalue lambda and eigenvector V, then what is the eigenvalue of A square? It is lambda square. Eigenvector remains same, A, right? V. How? I can prove it to you. So let's solve it. So we know A into V equals to lambda into V. So if I multiply by A on both sides, so this will become A square into V equals to lambda into A into V. Lambda is just a scalar and A into V is nothing but lambda into V, right? So this will become lambda square into V. So A square V is lambda square V. So eigenvector remains same, but the eigenvalue changes. Corresponding eigenvalue changes. So simply what is happening? Whatever I do, right, a square, a cube, a raised to power 4, the eigenvalue will change. So this, right, what will be my eigenvalue of e raised to power a? Eigenvalue of e raised to power a will be simply, I can use the Cayley-Hamilton theorem, right? Lambda by 1 factorial plus lambda by 2, lambda square by 2 factorial plus lambda cube by 3 factorial. And this is what? This is nothing but e raised to power lambda. So this is simply e raised to power lambda. So eigenvalue becomes e raised to power lambda. But I have told you that if I do a square, a cube, all these will not change my eigenvector. Eigenvector remains same. So eigenvector will still be V. So the matrix will have an eigenvalue e raised to power lambda and eigenvector will still be V, right? So statement 1, e raised to power lambda is an eigenvalue of e raised to power a, correct. Statement 2, V is an eigenvector of e raised to power a, absolutely correct. So both statements are correct. So option C will be my answer. So we are not just like in any other institute, they will just tell you to mug up this thing, right? Just tell you to mug this one up. But we are actually going by the concept. How is the eigenvalue same? How is the eigenvector same? So eigenvalue changes and how does the eigenvector remain same? So that's why the derivation is very, very important in this case. Let's solve this question. Consider a 3 cross 3 matrix whose element is given like this. Then the matrix A will be what? So we can actually construct the matrix, right? We can construct the matrix simply. So element is I minus j. So I and j are the basically the ith row and the jth column. That is what they're talking to us. So ij, when I equals to 1, j equals to 1, that is the first element. It will be 0. When I equals to 1, first row and second column, it will be minus 1 whole cube, that is minus 1. And in the in the first row and the third column, this will be 1 minus 3, that is minus 2 whole cube, that is minus 8. Okay, 1 minus 3, that is minus 8. Then we have this 2 minus 1, so 1. So I am just constructing the matrix. This will be 0, this will be 0. It is a skew symmetric, right? We can see this is 3 minus 1, this will be 8. It is a skew symmetric matrix simply. This element will be 3 minus 2, 1 again, and this element will be minus 1 because this will be 2 minus 3, right? Minus 1. Yeah, it is a skew symmetric matrix. Simple. Like I don't feel there is anything much to say. Just construct the matrix and see what kind of matrix there is. So they're asking questions from types of matrix as well. So every single thing is not important. Actually, mostly they ask eigenvalues, eigenvectors, and solutions of equation. But sometimes they ask from types of matrix as well. It all depends on them. So this is the next question. In the figure, u and v are related as seen, right? So basically, I am transforming my v into u by a transformation matrix A. So the correct correct matrix will be, what will be my correct matrix? So what is my v? V is simply 5 comma 0, 5 0, right? And I'm multiplying A as shown in the equation to transform it to u. U is 4 comma 3. So what you can do, you can check any of the options, like you can put these values in this equation and see which options are matching. That is one way to go about. Or if you remember that we had a transformation matrix. So what was the transformation matrix? You see everywhere, right? There is 4 by 5, 4 by 5, 4 by 5, 4 by 5. So the first element is 4 by 5. And what is this angle theta? So how much have I moved actually? So 4 comma 3 means 4 is the base, 4 is the distance base, and 3 is the height. So what is this angle? Tan inverse y upon x, tan inverse 3 upon 4 is nothing but 37.86. I guess I can do it as well. 3 upon 4, yeah, not 37, sorry, 36.86. 36.86. So that is what my tan inverse 3 upon 4 is, correct? So we had, I see this is positive and I remember something, right? So what is 4 by 5? 4 by 5 is actually cos of 36.86. You can verify. If I do cos of this angle, right, it is 4 by 5. So actually the first element will be cos theta. And once you get the first element, you know the next element, if I remember, it has to be negative. Right? Here it has to be minus of sin theta. And here we used to have sin theta and cos theta. Right? So why? Because you can have minus sin theta here as well. That is also a possibility. But this was the standard matrix that we derived. So this actually comes out to be here 4 by 5 minus 3 by 5. Like theta is 36.86. This will be 3 by 5 and this will be 4 by 5. Okay. So this is present in option B. Option B it is present. Let me check whether it is actually matching or not, whether we are able to do it, because I will verify obviously. So we will put the values over here. 4 by 5 minus 3 by 5, 3 by 5, 4 by 5. So this will be 4 and this will be this will be 3. Yeah, this is actually matching. So it is absolutely correct, right? So this one satisfies my option, right? Option B. Minus of this, right, multiply by 4 is 0. This is, yeah, this is 3, 0. Yes, this one satisfies my option. So option B will be correct in this case. Okay, option B will be correct in this case, because what is my, okay, sorry, okay, one slight mistake I made. We are not going from, sorry, V to U, we are actually going from U to V. I'm extremely sorry, we are going from U to V. Okay, that is a problem, right? We are going from U to V, not V to U. So actually this will be swapped. So you might make a mistake over here, that is the problem. Then I don't think this will work. This will not work. So this will come out to be something else, right? You can solve. I think this will be 16 plus 16 plus minus 9. So this comes out to be 16 minus 9, 7. The top comes out to be 7. Sorry, 7 by 5. And this will come out to be, yeah, this will come out to be something else actually. 12 plus 12, 24 by 5. No, this is not correct. So option B is not correct. I was wrong actually. Now, right, basically this was for going from this vector to this vector. I'm going in the, like, this matrix was actually, I had not specified that at that point of time. This was going in the anti-clockwise direction. This matrix was for going in the clockwise direction, right? Because I'm going from U to V, it will be inverse. Already I have told you, right, how to simply solve it without even memorizing all this. Just verify the options, just put the values and verify the options. That's it. That part is done. I'm just telling you extra. That part everyone will say you. I'm just telling you additional things. Okay. So to move in the anti-clockwise direction, I have to take the inverse. So what is the inverse of a 2 cross 2 matrix? Determinant is 1. Determinant is 1. Just swap the main diagonal elements and change the sign of the off diagonal elements. So this will become plus sine theta, and this will become minus sine theta. Okay, plus sine theta, minus sine theta. All right. So now yeah, so now this will be the matrix actually. So matrix will be actually the same matrix, but the signs will change. This will become plus 3 by 5, and this will be minus 3 by 5. This will be 4 by 5. Now it will work. So option A will be correct actually. You can verify. So we will verify obviously. So this will be 4 by 5, 3 by 5, minus 3 by 5, and 4 by 5 into 4, 3 equals to 50, right? So I will check what is it equals to. So this will be 12 plus 9, that is 25 by 5, that is 5, and this will be 12 minus 12 plus 12, that is 0. So yeah, this is absolutely correct. Okay, so but like in this question you will solve using options only, no problem. But in some other question maybe options will not be there, right? So for those kind of situations I'm just telling you, right, that how can you solve it without the options. Of course with options you can easily solve it, no problem, right? But I'm telling you some other methods as well. Let's solve this question. Here, right, we have to, which of the following matrix has an inverse? So a matrix will have inverse if it is non-singular, if the determinant is not 0, right? So they are asking me which of the following matrix has inverse. Like they are asking very simple things, right? So if I see this row and this row, right, they are linearly dependent. If I multiply 2, I will get back this row. So this is anyways gone, right? So this has determinant equal to 0. So this is anyways gone. Again, if I see this, right, if I am, okay, if I multiply 2 by this row, right, I will get back my row 2. So again, this determinant is also 0. If I see here, okay, here, right, I see there is very little dependence. Let me check the option D first. Then if D is not the correct one, then of course C will be the correct one. I will verify with determinant, checking the determinant as well. So if I see here, right, if I multiply 3, I am getting my row 3. So simply again the rows are dependent, so determinant will be 0. So only C will have determinant not equal to 0, we can verify it as well. So let me verify it, right? So what I will do is I will find the determinant of this matrix 4 8 0 4 2 1 to 4. Okay, so this will be if I subtract these two rows, right, this will be 1 4 8 0 4 2 0 minus 2 minus 4. Okay, so now if I find the determinant, this will be minus 16 plus 4 equal to 0. So, oh, not 0, sorry, equal to minus 12, which is not equal to 0. So definitely the determinant is not equals to 0. So definitely what I can say is that it will have a inverse. It has an inverse. So option C will be correct. Let's now move on to the next question. What will be the sum of the eigenvalues of this whole square? So let us assume that like you can do one thing, you can square it, then find the eigenvalues, or a basic thing you can do is like that is a lengthy method, right? So you find out a square, then you find out the lambda of that lambda a square, and from there you do the sum of the eigenvalues. You can definitely do it, right? But we can easily find out the sum of the eigenvalues, right? How? If I know, if I assume this to be my matrix B, right, this inside matrix which is squared, so A is equals to B square. So if B has eigenvalues as lambda, then A will have eigenvalues what? Lambda square. We know by property, right? It will have lambda square. So what are my eigenvalues of uh, my B? So I can easily find out my eigenvalues of B, right? Or okay, is there any other easier way? I can definitely find out the eigenvalues of B. Yeah, that is possible. So what will be my eigenvalues of B? I can use the characteristics equation. So lambda square minus trace of A minus trace of B. Trace of B is 5. Sum of diagonal elements is 5 into lambda plus determinant. Determinant is 4 minus 6. 4 minus 6 is minus 2 equal to 0. So 4 minus 6, 4 minus 2 equal to 0. So lambda, okay, what will be the roots for this? Lambda equals to minus of B plus minus B square 25 minus 4AC, that is plus 8 equals to 2A. Lambda will be equals to 5, 5 plus minus 33, under root 33, right? So this value will be under root 33, that is 5.7, then minus 5 divided by 2, that comes out to be 0.3723, and 5 plus under root 33 divided by 2 will be 5.37. So what will be the eigenvalues of A? So it will be just square, right? If I square it, it will be 28.8614, and another eigenvalue will be like that will be very low value actually, 0.3723 whole square. It comes out to be 0.138. So basically approximately it will be 29. So if I add these two eigenvalues, right, because I have to find out the sum of the eigenvalues, it will be approximately 29, because in integer they are asking me in integer. So sum of lambda square, lambda 1 square plus lambda 2 square will be 29. So that is the easiest way. Of course you can square it and then find the eigenvalues of A square, that is also totally fine. Or another easy way is without doing this, right, another easy way is you directly square this. You square this. What is this square? This will be 1 2 3 4 1 2 3 4. So this will be equals to 1 plus 6, 1 plus 6 that is 7, 2 plus 8, 2 plus 8 that is 10, 2 plus 8 that is 10, 3 plus 12, 3 plus 12, 3. Although these elements are not required for me, right? Simply I just need the diagonal elements because I have to find out the sum of the eigenvalues. So I just need to find out the diagonal elements. So which will be 6 plus, so the last element 6 plus 12 that is 18. 6 plus, sorry, 6 plus 16. So this will be 22. So simply write like it, this one is bit lengthy actually. This one is the easier one, right? Simply find out the sum of the eigenvalue, that is 7 plus 22, that will be my trace, that will be equals to 29. So 29 will be my answer. Okay, this was actually much simpler than the previous case, right? Okay, so sometimes I also go wrong. So there are multiple ways in which we can solve. Ultimate thing is I am telling you all the methods, so that in exam hall you have all the tools. Even if you forget one method, you can still solve the question, because this exam is not an exam of speed. Okay, this exam is not an exam of speed. Let v1 and v2 be two eigenvectors corresponding to distinct eigenvalues. Okay, we have distinct eigenvalues. Then which of the following statements is true? v1 dot v2 not equal to 0, v1 transpose dot v2 equal to 0, v1 plus v2 equal to 0, v1 minus v2 equal to 0. So if I have two eigenvectors that are corresponding to two distinct eigen values, that means my v1 and v2 will be linearly independent of each other. If they are linearly independent of each other, right, that means their dot product will not be 0. If their dot product is 0, that means they are linearly dependent. Correct? They have to be orthogonal vectors. Orthogonal, like this example, right? Like this 1 0 and 0 1. So what is the dot product? Dot product, it is simply I cap and j cap. Dot product is 0. Sorry, yeah, dot product is 0. Dot product is 0, right? Whenever we have linearly independent vectors, their inner dot product is 0. Basically, they behave like orthogonal vectors. They are set of orthogonal eigenvectors. Okay, so they are linearly independent. They are set of orthogonal eigenvectors. When vectors are independent, their dot product is 0. So how do I represent dot product in matrix format? v1 transpose into v2. So this is absolutely correct, right? Are these options valid? No. So here if I rewrite v1 equals to minus v2, so I can linearly write v1 in terms of v2. Here also I can linearly write v1 in terms of v2. So they are independent, they are not dependent. So they will not be, obviously I cannot write v1 in terms of v2. That is not possible, right? So only this one and this one is there. So how can you verify? Simply you take examples. Whenever you are in the exam hall, take examples that what are my two linearly independent vectors? These are my two linearly independent vectors and their dot product comes out to be 0. So that means that they have to be orthogonal, even though I also don't remember that they are orthogonal, but still I will take some example, and with this example I will solve my question. Okay, that's how you will solve these kind of questions. Let's now move on to the next question. So we have this next question. This is also GATE EE 2025. So let A be equals to this, B equal to this, then the system of linear equation has infinitely many solutions, no solution, finite solution. That is what they are asking. Okay, so simply we can first of all find out the rank of A. So I observe that this and this row are totally negative of each other, and I see this and this also is negative, right? So rank of A is simply equals to rank of A colon B. So and it is less than the number of variables, so it will have infinitely many solutions. Directly by seeing I can actually do it, okay, without even touching my pen, but still let's do it properly. So what is rank of A? So rank of A, I see that this is my matrix, right? 1 1 1, then minus 1 minus 1 minus 1, then 0, 0 1, this will be 1 by 3, minus 1 by 3, 0. Okay, Oh, first of all, I was actually calculating rank of A. So if I calculate rank of A, right, I see my row 1 is simply equals to minus of row 2. So definitely it will be like at least it will be 2 or lower. So if I see this, if I take this 2 cross 2 matrix, right, I see the determinant is non-zero. So definitely I have a minor whose determinant is non-zero. So rank will be 2. Okay, rank will be 2. I can check rank of A is 2. What about rank of A colon B? For that, right, I have to minimize this. Again, if I minimize this, right, rank of A colon B, again I will have, so yeah, let me minimize this further. So I will just add these two rows. This will totally be vanished. This will be totally 0. Now, can I eliminate this row as well? Is it possible to eliminate this row? Can I eliminate this row? No, I cannot eliminate this row because this will be 0, but this will be still non-zero, and this also will become non-zero. So no. So rank of A colon B is also 2. Right? So rank of A colon B equals to rank of A, which is less than the number of variables, that is 3, right? Because the order of my A matrix is 3, so I have 3 variables. So it will have obviously infinitely many solutions. Let's solve this question. I think this one is the last question. So we have been given a identity like P matrix and we have to calculate P square. Very simple. Either you can directly calculate P square or you can take help of the characteristics equation. Okay. So what you can do is, what is my, okay, should I take help of the characteristic equation? Okay. Because they are just asking you P square. Okay, yeah, I can take help of the characteristic equation, but for that I will need lambda. So this is not even a upper triangular matrix. Yes, we can actually convert this matrix, right? But if I do some row transformations, the eigen values might change. Okay. Or okay, you don't do using eigenvalue, you simply do what you do. Like we can use the property of eigenvalue. What do I mean? So I can find the eigenvalue of this P, right, lambda. Then, oh, okay, one thing is there. The eigenvalue, one of the eigenvalue will be 1 because all the rows are adding up to be 1. Yeah, let's not do it. So I can find the lambda, right? So the value of P square will be like, if I convert this into lambda, this will be lambda square. So here I will replace my P to lambda. So this will be 2 lambda minus 1. This will be lambda. This will be 1. This will be lambda plus 1. So basically I will find out the value of lambda and value of P square in eigenvalue domain will be lambda square, right? So if I replace my P with lambda everywhere, right, I will cross verify the options, whichever one will match, I will solve it. But maybe you to find lambda, right, it will take you some time because it is a 3 cross 3 matrix. So I can simply do what? I can simply do our basic thing. I can multiply P twice, okay, to be absolutely sure. So yeah, let me solve this. P square will be, give me 1 second. 2 1 0 minus 1 0. I will show you the other method as well. 0 0 1 into twice. This will be twice multiplied. This will be 2 into 2 4, 2 into minus 1 and 0. So 4 minus 1 3, 2 into 2 into 1 2 1 0 2 0 minus 2 0 minus 1. This will be 0. This will be 0. This will be also 0. This will be 1. Okay, what is it equals to? So it is basically twice of P minus 1. Yeah, if I do twice of P and then subtract 1, I will get back my option A. So this is nothing but you can see it is 2P minus I, not 1, sorry, 2P minus I. So option A is correct, right? Now what was the other method that I was talking about? So if you find out one of the eigenvalues, right, what do I see if I add all the rows of my P matrix? This becomes 1 1 and 1. So definitely one of the eigenvalue will be 1. How can I say? So there is a property, if all the rows, right, become same element, one of the eigenvalue will be that only. How? So if I do, like, what you have to do, we have to find out determinant of p minus lambda I, right, equal to 0. So here, right, what is p matrix is this, right? I have just done some row operation, that is valid. So if I do the row operation and then do lambda I, so it will be 1 minus lambda plus 1 1, then minus 1 0 0 0 0 1. Okay, I was wrong. If all the elements add up to, because this then this will not be lambda I, right, equal to 0. No, I was wrong actually. No, there was a property, if I remember it correctly. What was that property? Okay, this was supposed to become minus lambda, this also becomes 1 minus lambda. I'm just forgetting that property, kind of. Okay. Minus lambda. Okay, let's not solve it like this. I forgot some property. There was some property. Okay. Otherwise, you have to find the lambda, right? That will be a hectic task. Like, I'm forgetting. I also don't remember. There is some property here. I'm forgetting. I'm missing some property. You just have to find the value of lambda, and with that you can solve. Okay. Let me find the value of lambda. Can I find the value of lambda here? Let me, before this, right, let me solve this further. So this, right, I can further simplify. I don't think this is allowed actually. This is not allowed. This thing is not allowed actually. Oh, I'm missing the point. No. What we have to do is we have to write. We cannot change the. We cannot do transformations before doing this, right? First of all, we have to do this actually. P minus lambda I. So this will be determinant of p minus lambda I, that is 2 minus lambda 1 0 minus 1 minus lambda 0. Oh, now I'm remembering. That's why I was going wrong actually. Yeah. So like we cannot do row transformations or change rows and stuff before applying this operation p minus lambda I. After doing this p minus lambda I, then I can do it, because ultimately we have to find out the determinant of this matrix p minus lambda I. I cannot change my p matrix. If I change my p matrix, the eigenvalues also will change. So don't mess this up. I was also messing it up, right? First do p minus lambda I and then you find out the determinant. Now this property will be valid. What will we do is we'll add all the rows together to the first row. So row 1 will be changed to row 1 plus row 2 plus row 3. So this will become 1 minus lambda. This will also become 1 minus lambda. This will also become 1 minus lambda. That is what I was missing actually. Sorry for that. Minus lambda 0 0 0 1 minus lambda equal to 0. So now I can take this 1 minus lambda common. So definitely one of the eigenvalue, right, will be definitely 1. So that's why I was telling that if I add all these rows, right, and if all the elements comes out to be same for the first row, that means one of the eigenvalue definitely will be that value 1. Okay, so I don't care what is this, right, I am just taking this common. So one of the eigenvalue will be definitely 1. So I can replace my lambda equals to 1 in this equation. So if I replace my lambda equals to 1 in this equation, right, things will be difficult, because lambda equals to 1, if I replace with p, this will be 1, p square will be 1, p square will be 1. Here also 2p minus 1 will be also 1, this also will be 1, this also will be 1, only this one will be 2. So I can only eliminate this option. So I have to find out another lambda value to cross verify. So this will be 1 1 1 minus 1 minus lambda 0, this will be 0 0 1 minus lambda. Okay, now we can actually simply solve this determinant actually. So if I open this determinant about this, right, this element, so this will be 1 minus lambda already is there, again 1 minus lambda into minus lambda plus 1. So it is 1 minus lambda again. Okay, that is interesting. So basically all the eigenvalues are 1 itself. So you will not be able to verify this. You will not be able to verify. So you have to simply do p square only. So what I was talking about, for example, if one of the lambda comes out to be minus 1, right, one of the value, then I would have replaced here minus 1 and then I would have checked, right? Which one is satisfying? But unfortunately, you will not be able to do it in this case, okay, because all the values of lambda coming out to be same. Okay, so with this we are done with electrical PYQs. Now we will solve ion PYQs. So let's start with ion questions. So this is the first one where we have to find the determinant, like very basic question. We have to simply find out a determinant, right? So I can observe that this is kind of a upper triangular matrix, and for upper triangular matrix, the determinant, finding the determinant is very easy, but not exactly, because this element is not 0 and this element is also not 0, right? So can I somehow make this element and this element 0? So what do I have to do? I have to simply find out the determinant of m, that is 1 2 0 0 3 4 0 0 0 0 4 3 0 0 2 1. Okay, so we have to find out this determinant. So this one, right? What I can do is I can apply this operation, that row 3 will be changed to row 3 minus 3 row 1, okay, so that it's not row 3, sorry, row 2, and row 4 will be changed to row 4 minus 0.5 row 3, so that I can get a upper triangular matrix. And we know the determinant of a upper triangular matrix is simply but nothing but the multiplication of the diagonal elements, right? So my main purpose is to simply convert this into a upper triangular matrix. So this will be 1 2 0 0. If I subtract by 3 times, this will be 0, this will be minus 2 0 0, this will be 0 0 4 3, this will be 0 0 0, and 0.5 into 3, 0.5 into 3 is 1.5 minus 0.5 determinant, right? So this will be equals to 1 into minus 2 into 4 into minus 0.5, 1 into minus 2 into 4 into minus 0.5. So this will be equals to uh, uh, 1 into 4, so 4, so 4 will be the answer. Okay, so sometimes they ask some like basic questions as well, so 4 will be my answer for this particular question. Let's move on to the next one. So given that the matrix is this, what will be the value of the determinant of this matrix? Okay, so how will I solve this? So there are many ways to solve this actually. So let's assume that this is a matrix B. P equals to a raised to power 4 minus 5 a cube. Like you can solve it using the lengthy method. You will find out a raised to power 4, you will find out a cube, you will do a square, you will then add 2i, and then ultimately that equivalent matrix you will find out the determinant, right? But there is a simpler way using the Cayley-Hamilton theorem, right? So B is equals to a raised to power 4 5 cube plus 6a square plus 2i, right? So if A has eigenvalues lambda, then B will have what eigenvalues? Lambda raised to power 4 minus 5 lambda cube plus 6 lambda square plus 2. I hope I don't need to explain why. Eigenvectors will be same. They will have same eigenvectors, right? Only eigenvalues will change, correct? So I just need to find out the eigenvalues of A, and it is very easy. It is just an upper triangular matrix, and for upper triangular matrix, the eigenvalues are 2 and 3. Like say, simply the diagonal elements. You can verify. You will see that eigenvalues are coming out to be lambda are coming out to be 2, 3. So what will be the lambda of B? So for lambda equals to 2, right? This will be 2 raised to power 4, that is 16 minus 5 into 2 cube, that is 8 plus 6 into 2 square, that is 4 plus 2. So this will be okay, this will be minus 24 here, minus 24 here, plus 24 2. So this also comes out to be 2. For lambda equals to 2, what about the other value? So what about lambda equals to 3? So for lambda equals to 3, this will be 3 raised to power 4, that is 81. Okay, 81 minus 3 cube, that is 5 into 27, right? So 135 plus 6 into 9. 6 into 9 is 54 plus 2. So this will be 135, 81 plus 54 plus 2. So which is equals to 2. So eigenvalue comes out to be 2. Now what will be the determinant of matrix B? I just need to find out the determinant of matrix B. So determinant of matrix B, it is also 2 cross 2 matrix, right? It will be also 2 cross 2 matrix because all these are 2 cross 2. So determinant of matrix B will be lambda B1 into lambda B2, which is 2 into 2, which is 4. Now of course this is the simplest method. You can obviously find out in method 2, you will find out a cube, you will find out 6a square. You will do all this, right? Then finally add those up, you will get a 2 cross 2 matrix, and then you will find the determinant of that 2 cross 2 matrix. Okay, that will take you a bit longer. Okay, that's how you can do it. That's how you can solve these kind of questions. Okay, let's now solve this question. Given matrix M, which of the following statements is or are correct? Okay, so rank of M is 2. So let me check, do I have any dependencies? So if I multiply by 2 with the first row, I see that I am getting the second row. So definitely rank is not 3. So automatically this option is gone, and this is a MSQ, right? Which of the following options is / are correct? So rank of M is definitely not 3. Determinant of M is definitely 0, because like linearly dependent rows are there, determinant will be 0. The rows of M are linearly independent, again wrong. No, we have row 1 and row 2 which are linearly dependent with each other, correct? Now what about the rank is 2? So only have to check option A. So for that I can take any 2 cross 2 minor. If I check this matrix, right, 2 into 4 is 8, 8 minus 18 is minus 10, which is non-zero. So rank is definitely 2 because I have a non-zero minor and the order of that minor is 2 cross 2. So rank is definitely 2. So option A and D will be my correct answer for this question. So that's how simple these questions are. Like I hope the revision series has helped you immensely, because we are able to solve questions in less than 1 minute. Okay, we're not taking that much time, and I have covered every single topic. I have not left out any topic. Okay, so yeah, let me solve this next one. The matrix A have eigenvalues this, the eigenvectors will be. So they have already given me the eigenvalues. Even if they would not have given me the eigenvalues, still I would have been able to find out the eigenvectors, but they have done the task for me. They have given me the eigenvalues. So now it's very simple, right? So if eigenvalues are given, I know A into X or A into V will be equals to lambda into V, right? So A is this 4, 4, 3, 9 minus 2. Just give me 1 second. Four, 3, 9 minus 2, and V is x1, x2. Okay, and this is equals to, let's take the first eigenvalue, that is minus 5. So minus 5 into x1, x2. So this will be 4x1 plus 3x2 equals to minus 5x1. Okay, so your I get that my 9x1 equals to minus 3x2. So my x2 is equals to minus 3x1. Okay, and what about the next one? So I get this equation, another equation I have, 9x1 minus 2x2, equating the second row, will be equals to minus 5x2. Okay, so here what values I will get? This will be 9x1 will be equals to minus 3x2. So x2 will be equals to minus, okay, I think both come out to be 0 over here. both are coming out. So x2, just give me 1 second. This is -5 -5. Oh, here also we're getting the same. X2 equals to -3x1. So we're getting the same equation actually. So basically x2 will be equals to -3x1. So yeah, this one is valid. 2 minus 6. This one is satisfying the first equation, right? So x2 will be equals to -3x1. Option C is satisfying. Let's now check for the next eigenvalue. So all the other options, I don't see that my x2 is -3 of x1, right? Here none of the options x2 is -3 of x1. Only option C is satisfying. Let me check for lambda equals to 7. So if lambda equals to 7, right, here what do I have to do is simply I just have to put here lambda equals to 7. That's it. So if I put lambda equals to 7, this will be 4x1 plus 3x2 equals to 7x1. So x1 equals to x2. x1 is equals to x2. Okay, so x1 will be equals to x2. That is only present in option A, right? In all other options x1 is not equals to x2, right? So option A and C will be the correct eigenvectors corresponding to -5 and 7. So option A and C will be my answer. So I don't even need to solve the other one. Other one also will come out, will give me the same equation. x1 will be equals to x2. You can do it. Let's solve the next one. So this is actually a pretty good question that came in GATE IN. Pretty good question. So choose solution set corresponding to the system of equation. So we have to choose the solution set corresponding to the system of equation, right? So what will be my solution? So I am only given two equations. So there is no possible of unique solution. That's why you see there are possibility of infinite solutions, because alpha and beta can be infinitely any values, infinitely many solutions, right? Any real. So but the nature will be similar. So we will check which solution are actually satisfying. Okay, we'll check that. So R denotes any set of real numbers. So first of all, I will convert. This is a homogeneous equation, right? And I know for a homogeneous equation, the determinant is coming out to be 0, because if I assume that the other equation is 0, 0, 0, 0, determinant is coming out to be 0. And if determinant comes out to be 0, we get infinitely many solutions. So that's why all the solutions are infinite. There is no possibility of no solution, because it is a homogeneous set of equation, right? So what I can do, I can simply solve this, right? So I can convert this into my matrix format. This will be 1 -2 1 1 0 -1, just putting the coefficient of z, coefficient of y, coefficient of x, right? And here I have my x y z equals to 0, null matrix, 0 0, right? Just converting this into my matrix format. Now if I simply solve this, if I solve this further, what I can do is I can subtract these row 2 to row 2 minus row 1. So this will be 1 minus 2, 0, 2, minus 2. This will not change. This will be x, y, z only. This will be 0 minus 0 is 0 only, right? So 0. So ultimately, what will it become is, can I further minimize it? Yes, kind of. So if I add these two columns, right? But column operation is actually not allowed. Column operation is never allowed. I forgot to mention, column operation you will not be able to do. Only row operation you will be able to do. So yeah, now what I can see is 2y minus 2z equal to 0. That is y will be equal to z. So y will be equal to z. Y has to be equal to z, right? That is one of the solution. Then in the next equation, if I solve, right, so x minus 2y, so 2y is z, I can write minus 2z plus z equals to 0. So again x is equals to z. So y equals to x equal to z is a solution. So basically x can be any free variable, right? So basically I can have one solution alpha equal 1 1 1. This is one of the solution, right? Alpha into 1 1 1. Now is this a solution? Is this a solution? This is actually not a solution, right? Because here, like if I put beta equal to 1, so x equals to 1, y equal to 0, z equals to 1. If I put here, is this a solution? X equals to 1, it is satisfying this one. It is satisfying actually. X equal to 1, y is 0. Okay. But is this a... Okay. So if I assume my alpha and beta to be 1, let's assume that alpha beta equals to 1. So if alpha beta is equals to 1, then what will happen? Then this will become 2 1 2. 2 1 2, is it a solution? 2 1 2. So no. So if I put here, right, x equals to 2, y equals to 1, so this will be 2 minus 2 is 0, this will be 2. No, 2 is not equal to 0, right? So no, this is not a solution. Anyways, we are getting the solution. Our solution is this: x equals to y equal to z. This is the only solution that I am getting. Correct? Only solution that I get him. So x will be equals to y equal to z. X can be, I can assume z to be any value. Let's say alpha. So x, y and z all will be alpha. So alpha, alpha, alpha will be my solution. If I take alpha common, so 1 1 1 can be my solution. I am free to choose any value for alpha. So only option A will satisfy. Option, all these will not satisfy. Alpha, like this is also not a correct solution, right? 1 0 1 is not solution. Only option A will satisfy. So option A will be my correct answer for the question. Okay, all of them will be equal. I hope it is clear. Okay. Yeah, because if you assume x equal to 1, y equals to 1, what will happen? X and z will be 1, so this will be 2, y is 0, so 2 equal to 0, again not a valid equation, right? So all these are anyways not satisfying. Only option A is satisfying my solution. So obviously option A will be answer. You could have directly done it without doing all this. You could have directly put these values here, right, and checked which ones are satisfying my equations. The ones that are satisfying my equation will be my solution simply, right? So you can have directly put it in the options. Let's now solve the next one. The rank of the matrix A is the rank of the matrix given below is 1. The ratio of alpha by beta. Okay, rank, they are telling me rank is 1. If rank is 1, that means these rows will be linearly dependent on this row, because rank is 1, right? So I will have only a single row that is completely linearly independent, because rank, what does rank tells me? Rank tells me, I've already discussed, number of linearly independent rows or columns. Rows or columns, either way will work. I will assume row because I know that this row 2 elements, row 1 elements, all the elements. So rank of the gives me the number of linearly independent rows. So if it gives me the number of linearly independent rows, rank is 1, that means this row, all these other rows will be linearly dependent on this one. So if I see this is minus 3 times this one, right? So this also will be minus 3 times. So row 2 has to be minus 3 times row 1. So I can say minus 12 will be equals to alpha, and I can see that this is 6, this is 4. So what do I have to multiply to row 1 to get to 6? So it will be 6 by 4, right? So I can say that 6 by 4 into 1 will be equals to my beta. Now what are they asking? They are asking alpha by beta. So alpha is minus 12 and beta is 6 by 4. So this will be minus 2 into 8. So minus 8. So minus 8 will be my answer for this question, because they are asking me alpha by beta, right? Also, in other words, what does rank say? Rank says rank is the minimum matrix, order of the matrix whose minor is non-zero. So if I choose, like if rank is 1, right, that means only this determinant is non-zero, this determinant is non-zero. If I choose any 2 cross 2 minor, its determinant has to be 0, because rank is 1. So if I choose any 2 cross 2 matrix minor, the determinant has to be 0 because rank is 1. That is how we calculate the rank, right? So all 2 cross 2 minors will be 0 determinant. So if I find out the determinant of this matrix, right, small 2 cross 2 matrix, 1 4 minus 3 alpha. This has to be 0. From here also you will get alpha will be equals to minus 12. Again, if I choose these two rows, correct, 1 4 beta 6, again this has to be 0. So again you can get the value of beta from here as well. Okay, so there are two ways. I am telling you all the tools. I am giving you all the tools to solve a particular question. Let's now solve the next one. Now here again we have a matrix M that has been constructed using 3 column vectors v1, v2 and v3. Choose the set of the vectors such that the rank is 3. Okay, how will rank be 3? Simply v1, v2, v3 all has to be linearly independent of each other. Basically the determinant of M, right, has to be not equal to 0. If determinant of M is 0, that means rank will not be 3, obviously rank will be something less than 3. So if I see this first one, right, I see v1 is equals to nothing but v2 plus v3, right? So they are linearly dependent. v1 is nothing but v2 plus v3, correct? And v1 here is, okay, this is anyways all 0, right? If this is all 0, automatically the rank is 2, because one of the columns is all 0, rank is automatically 2. So this is anyways gone. If you find out the determinant, right, you will see this is gone. Here am I be able to find anything here? Currently I am not seeing anything. If I add these two, no, these are actually independent. But let's check the last option, D. If I check this one, right, if I add these two, okay, if I add this is also, this seems like independent, right? If I add these two elements, this will be 0, this will be 2. Oh no. So if I add these two, right, this will be what? This will be 0 2 0. I can take 2 common or minus 2 common, right? Yes, I can multiply minus 1 by 2 to get back to this. So what do I mean? So v3 will be equals to v1 plus v2 into minus 1 by 2. You can see that you will see that v3 is dependent on v1 plus v2. It is linearly dependent. But for option C, we can solve it actually. We can find the determinant of option C, 1 0 1 minus 1 0 1 1 minus 1 1. Okay, if you find out the determinant, right, what I can do is simply I can open my determinant about this element. So this will be minus of 1, this into 0, this into 0. Okay, this is also coming out to be 0. How? No, sorry. This will be this into 1, 1 into 1 and minus of 1 into 1. So this will be 1 minus of minus 1. So this will be 2. So minus 2, which is not equals to 0. So determinant is coming out not equal to 0. So definitely option C will be correct because its determinant is non-zero. That means it's like rank is 3. It is a full rank matrix. Okay, so option C will be my correct answer. For all the other cases, right, you can find out the determinant will come out to be 0 only. You will be able to write your other vector in terms of the other two vector. Okay, so that is the most thing about rank. Let's now solve this question. So here we have like they are telling us that P is a 3 cross 3 matrix with all real elements and has eigenvalues 1 by 4 1 minus 2, the value of determinant of P inverse. So if I assume this to be matrix B is equals to P inverse, right? So what will be the lambda of B? Lambda of B, right, will be simply inverse. Lambda of B will be simply inverse, or simply without even lambda also you can do. So what is the determinant of P? Determinant of P, right, will be multiplication of the eigenvalues. So 1 by 4 into 1 into minus 2, which is equals to minus 1 by 2. So what will be determinant of P inverse? It will be inverse of this, right? Simply minus of 2. That's it. So minus 2 is the answer. So that's how simple questions they are asking, right? Minus 2 will be answered. Like nothing much. I don't have to explain much, right? Okay. So yeah, let's now solve the next one. So this is the next question. So we have a 2n cross 2n matrix. It is a square matrix. Elements are given such that they are this, right, has where n is integer greater than 2 and beta is any non-zero real number. The rank of A will be. So let me choose the smallest, n. So n is greater than 2. So I can any integer greater than 2. Okay, I have to choose n equals to 3. That will be a bit hectic. But let me construct the matrix slowly. It is beta and minus beta, right? So when I plus j is even, when I plus j is odd, it is beta. So 1 plus 2, and when I plus j is even, that is 1 1 will be minus beta, this will be minus beta, this will be beta, this will minus beta, and so on. So again, if I'm lying around here, right, what is the, is it odd or is it odd or even? So it is row 2 column 1, so it is odd. So this will be, again, if it is odd, it will be beta. So this will be beta, and this will go on minus beta, and so on. So they are asking me what will be the rank. So if I add, right, if I'm able to add all the rows, like if I'm like, this will be just negative. So basically all the rows will be negative or positive of the first row. So all the other rows, right, are linearly dependent on the first row. All rows will be linearly dependent on the row 1. So basically what I can say, all rows are linearly dependent on row 1. Okay, all rows are linearly dependent on row 1. Okay, so what I can do is, basically I can say that, and beta is non-zero, right? Beta is any non-zero number, so row 1 is non-zero. So basically what will happen, the matrix will be 1 minus, if I assume beta to be 1, 1 minus 1, 1 minus 1, 1 minus 1, something like this, all other elements are 0. So one of the row is independent, right? One of the row is non-zero, all other rows are 0. So rank will be simply 1. So one row is independent, so rank of A will be 1, right? So rank of A matrix will be 1, option A will be correct. So question seems tricky, but is really simple. Okay, it is really simple. Let's solve the next one. If one of the eigenvectors of matrix A is along direction alpha to alpha, where alpha is any non-zero real number, then value of x will be. If one of the eigenvectors is in this direction, okay, then the value of x will be. Okay, so they are telling me that one of the eigenvectors is this. So what I can do is A into V will be equals to lambda into V. So I can say that A is this value, minus 1 x minus 4 equals to lambda into V. So basically I can assume that lambda is just a scalar number. If I take this alpha common, right, it will be alpha into, okay, it is in this direction, right? So if I take the alpha common, alpha is nothing but the eigenvalue actually, the scaling factor, because it is in this direction, right? So what I can say it, or let me keep lambda, so it will be lambda into alpha 1 2. I hope this is not a problem. Now of course here also there will be, I can take the alpha common, right? Alpha, it is in this direction, so if I multiply by the eigenvector, right, I will get back the same eigenvector but scaled. So alpha will be cancelled. So ultimately, right, because alpha is just a scalar number, so minus 1 x minus 4 1 2 lambda 1 2. Okay, now they are asking me the value of x. So yeah, I have two unknowns and two equations. I can find the value of x. So from the first equation, right, I will be able to find my value of lambda. So this will be minus 1 minus 2 equals to lambda. So lambda will be equals to minus of 3. Okay, and x minus 8, x minus 8 equals to 2 lambda. Okay, x minus 8 equals to 2 lambda. So from here, and lambda is equals to minus 3, so x will be equals to 8 minus 6, that is 2. So x comes out to be 2. So 2 will be my correct answer for this particular question. Okay, so we were able to solve, I think, iron questions in record time. because this was a easier set of questions. Electrical and EC comes a bit difficult. So now we will start with CSIT. So let's start with CSIT questions. So this one is the first one. We have to find out the largest eigenvalue of the above matrix. Okay. So we have to find out the largest eigenvalue of the above matrix. How can I find out the largest eigenvalue? So first of all, I see we have a property here, right? All the rows, if I add, it is coming out to be 3. So I will actually use that property. Okay. So first of all, how do I find out eigenvalues? So what we do is, we do A minus lambda I equals to 0. So first I will use this matrix A minus lambda I. So this will be minus of lambda. So I am writing it directly. So I hope you will not have any problems, right? I am writing directly A minus lambda I. So you can do it slowly, okay, but the answer will come out to be same. Like this result will come out to be same. Minus lambda 1 1 1 1 minus lambda 1 1 1 1 minus lambda 1 1 1 1 minus lambda equal to 0. So what I can do is, I can add all the rows together. So if I add all the rows together, then this will become, the first row will become, with row 1, right? The first row will become 1 minus lambda 1 minus lambda 1 minus lambda 1 minus lambda. Okay. So if I take this 1 minus lambda common, this will be 1 minus lambda. I can take this common, right? So this will become 1 1 1 1 1 minus lambda. So I can again copy this thing, right? Now one more thing I can do actually. Now I can add these 3 rows, right? Sorry, this will not be 1 actually, sorry, this will be 3 minus lambda, right? What am I talking about? This will be 3, right? Because I'm adding these 3. This will be 3 minus lambda 3 minus lambda 3 minus lambda. Yes, this will be 3 minus lambda. So one of the eigenvalue is 3, that is for sure. Okay. Now what I can do is, can I add these 3 together? No, but I cannot take anything in common, right? No, that will not be possible. So yeah, next what I can do is, I can simply make this element 0. Simply make this element 0 for easier calculation of determinant. So what I will do, I will just simply subtract column 1 from all the other columns. So this will be three minus lambda into just give me 1 second. This will be 1 0 0 0. This will be 1 minus 1 minus 1. This will be 0 0. This will be 1 0 minus lambda minus 1 0. This will be 1 0 0 minus lambda minus 1. So basically equal to 0. So what happens if I write the determinant, right? All these row elements are 0. So I just have to find out the determinant of this particular matrix, smaller matrix. So what is the determinant of this matrix? It is, again, these are all 0. So again the determinant is simply minus of, so this will be 3 minus lambda into minus of lambda minus 1 whole cube. That's it, equal to 0. So if I take the negative sign common, this will be lambda minus 3 into lambda plus 1 whole cube equal to 0. So basically my eigenvalues, right, are all 3 minus 1 minus 1 minus 1. So the largest eigenvalue is 3. So this will be my answer. So please don't get scared if some large matrix is given and they are asking you to find the eigenvalues. The eigenvalues will actually come out to be very simple. Very simple. The eigenvalues will come out to be very simple here. It will not be something very complex eigenvalue. If you apply it using the basic method, right, it will be much simpler. Okay. So don't get scared if some larger matrix is given to you. So this was the first question. Let's now solve this next question. So here we have this matrix P, 4 cross 5 matrix, such that every solution of the matrix Px equal to 0. Okay. So this is a homogeneous equation. It's a scalar multiple of this. So solution, that is x, right? X is a scalar multiple alpha times this. the solution, every solution of this equation px equal to 0, that means x, they're talking about the x value, that is 2 5 4 3 1 equal to is a scalar multiple. So what is the rank of p? Okay, this is actually a pretty interesting question. So do you remember one thing? It is a scalar multiple of all these values, right? So how many free variables I have? So this alpha, right, can go in all this. So all these other elements, right, are dependent on this last value, because if this is alpha, let's say, then this is 3 alpha, 4 alpha, 5 alpha, 2 alpha. So one element is fixed, right? One element is fixed. Sorry, one element is free. I'm free to choose any, like you can choose any of this, right? Once, let's say, if this is 2 alpha, and alpha can be any real number, right? Alpha can be scalar multiple, alpha can be any real value. Okay, so if this becomes 2 alpha, other ones, this will be 5 alpha, this will be 4 alpha. So what am I talking about? Let's say the top one, x1 is 2 alpha, and let's assume that alpha is equals to 1. So x1 is 2. Once I set x1 equals to 2, right, automatically the other values will be set. x2 will be 5, x3 will be 4, x4 will be 3, x5 will be 1. So other variables are automatically set. Correct? So basically what I can say is that how many free variables I have? Only one. So what is the nullity? Do you remember what was the meaning of nullity? In the last example I told you, right? So how many free solutions I have? So the rank of nullity of A, right, is actually equals to my total number of variables n minus the rank of A. Nullity of a matrix A will be, nullity means this equation, in this case it is P, will be equals to n, that is number of variables minus the rank of P. Correct? And they are asking me what is the rank of P. So what is the nullity? Nullity is the number of free variables. Okay, here I have only one free variable. So if let's say nullity was 2, right, what will happen is your x will be some alpha times, like I'm just taking a very small example, x will be some alpha times 1 0 and plus beta times 0 1, and these two vectors must be linearly independent of each other, and they are both scalar multiple. Then basically I am free to choose any value of x2, I am free to choose any value of x1. Both of them are actually totally linearly independent. So how many free variables I will have? 2. Okay, I'm just taking an example for a 2 variable question. Okay, so if nullity is 2, that means I have 2 variables to choose from. So basically there will be 2 constants, alpha and beta. Alpha and beta are any value we can choose, but here I have only one constant. So once this 2 alpha is fixed, all the other values will be fixed. If this 5 alpha is fixed, let's say 5, then all the other remaining values of x1, x2, x3, x4 are fixed. That's why only I have one free variable. That's why nullity is 1. How many number of variables I have? 5. x1, x2, x3, x4, x5. 5 number of variables. So 1 equals to 5 minus rank of P. So rank of P comes out to be 4. Very interesting question, very good question actually. Rank of P comes out to be 4. Okay, so 4 will be your answer for the question. So understanding everything is very important, and actually in GATE EC or EE, they might not focus this nullity concept much, but in CSIT they will focus on this concept. Okay, so make sure you study this concept very well, nullity and vector space in CSIT. So let's solve this next question. So we have been given this matrix, which of the following is or are the eigenvectors of the matrix? Like this will be lengthy, right? It is first of all a MSQ question, and I have to check for each of them that which one will satisfy. So you do, like, okay, I can solve it. So what you have to do, you just have to simply apply this A into V equals to lambda into V, that's it. Okay, so if for each one you have to actually verify. This will be hectic, right? This will be hectic. Okay, you can only calculate the first 2 rows. I think that should be enough. only the first two rows should be enough. Okay, so yeah, let me solve it. I will explain. So this is, let me write the matrix: -9, -6, -2, -4, -8, -6, -3, -1, 20, 15, 8, 5, 32, 21, 7, 12. Okay, let me keep it as it is: 21, 32, 21, 7, 12. I just need that first two rows. I actually don't need the other two rows, but still, let's keep it. Let me check for option A. 1, -1, 1, 0, 1. It is equals to lambda into -1, 1, 0, 1. So I will just check for the first two rows. So if the first row and the second row are coming out to be negative of each other, then I will say that yes, I'm correct, right? So let me solve this. This will be -9 into -1, this will be +1, -6 and 0, then this will be 4, -4. So this is coming out to be 1. And if I solve the next row, right, so this is row 1, row 2, this will be 8, -6, 8 minus 6, 0, -1. So this will come out to be equals to 2, 1, 1. So this is not correct, right? So these are not actually negative of each other. So this is not a eigen vector, right? Am I doing this correctly? This minus into becomes plus, this -1 into minus, this -0, -1, yes, 7, yeah, 1, yeah, these are, this one should be minus, right? This one should come, okay, this is minus only, right? Sorry, this is -1 only. So yeah, this is correct actually. So the row 1 is negative of row 2. So yeah, A option. Okay, if this is happening, right, if row 1 is negative of row 2, then I need to proceed to find out row 3 and row 4 as well, unfortunately. Okay, if row 1 was not equals to negative of row 2, then I would have stopped here and I would have said that no, this will not be eigenvector, because row 1 has to be negative of row 2, right? That is the relation that they follow in the right hand side. So in the left hand side also they have to follow the same relation. But yeah, as it is equal, so I have to proceed for calculating the row 3 as well. So what is my row 3? So row 3 I can calculate. Row 3 is equals to, this will be minus of 20, minus of 20 plus 15, 0 plus 5, which is coming out to be 0, which is present in the right hand side as well. So no problems with that. Again, so I have to further check row 4. Row 4 will be minus of 32 plus 21 plus 0 plus 12. Okay, so yeah, this will be 33 plus 33 minus 32, that is again 1. So which is again correct only, right? Because like basically from here you directly see your lambda is coming out to be 1, right? Lambda is coming out to be 1, and here also it is 1. So it is totally matching. So option A will be correct. I have to similarly check for the other options. This will be bit lengthy, but that's fine. So yeah, let's check for the other options. Oh no, not this. So if I check for other options, so in other option the vector is something else. So my eigenvector is this: 1, 0, minus 1, 0. 1, 0, minus 1, 0. 1 0 1 0 minus 1 0 1 0 minus 1 0. Okay, so this will come out to be okay, let me calculate the row 1. So minus 9 plus 0 plus 2 0, which is coming out to be minus 7. Let me now check the row 3, or let me check the row 2 itself. So row 2, right, this will be minus 8 minus 8 0 plus 3 0. Okay, this coming out to be 5, which is actually not equal to 0, right? Because on the right hand side row 2 should be 0, but here I am getting 5. So of course B will definitely not be a eigen vector. So B is gone. A is correct, B is gone. So for C I can stop here, right? As soon as I get a not equal to sign, I will stop. I don't need to check further because this is not equal, so definitely I don't need to worry about the other elements. So now I will move on to the option C. So option C, this is minus 1 0 2 2, minus 1 0 2 2, minus 1 0 2 2. So this, right, this will be basically if I check the first, this will match, actually this will match, right? Minus 1 is anyways matched because here also minus 1 matched, right? If you remember, minus 1 matched, so this will match. Let me check the yeah, let me check row 2. If I check row 2, row 1 will match, you can calculate, it will match. Row 2 will be minus 8 into minus 1, that is 8. This will be 0 minus 6 minus 2, which is coming out to be 0. Okay, this is matching, so I need to proceed further. So row 3, this will be minus 20 0 plus 16 plus 10, which is coming out to be 6. What about row 4? Row 4 is coming out to be, okay, this will actually not come out to be minus 1 actually. Let me calculate this. Minus this will be 9 0, then minus 4 and minus of 8. Okay, so this will be minus of 3. So lambda is lambda is 3 basically. So here also you see lambda is 3. So this is correct. Here also let us check the value of lambda. So basically the right hand side is minus lambda and the left hand side is minus 3. So lambda will be 3. Okay, lambda will be 3. Now here, right, let us check for row 4. Row 4, this will be minus of 32 plus 14 plus 24 plus 24. So this will be 38 and 32, that is 6, again 6. So here also lambda is coming out to be 3, right? So this is correct, this is totally matching. Lambda equals to 3, this will totally, like, it is scaling factor is 3, this is matching. So option C is correct. Okay, what about option D? Let us check for option D. So option D I need to check. Zero 1 minus 3 0. 0 1 0 1 minus 3 0. Yes, 0 1 minus 3 0. Okay, so this will be 0, so row 1, right, will be equals to minus 6 plus 6, and this is 0. So it is matching. Row 2 root will be 0 minus 6 minus 6 plus 9 0, so this will be 3. And row 3 will be 15 minus, so lambda here, right, lambda comes out to be 3 if it is valid. If I will check for the other ones as well. If I choose lambda equals to 3, so yeah, let me check the row 3. Row 3, why am I not checking for lambda like when it is 0? So like lambda into 0, right, is 0 only, and left hand side is also 0, so that's why I will not be able to compare lambda here. Whenever lambda is some non-zero value, then only I will be able to compare. So here also, that's why I was equating whenever it was 0, whenever it was not equal to 0. So there I cannot equate lambda, right? It has to be 0 because lambda into 0 has to be 0, and here also it has to have 0, then only the scaling will be happening. If it is some non-zero value, then I can compare lambda. Okay, I hope that part is clear. 0 into anything is 0 itself. So this is 15 15 minus 24, which is coming out to be minus of 9. Yeah, here also the lambda is coming out to be 3 only, because if I choose here lambda equals to 3, this will be minus 9. Minus 9 is matching. So let's now solve for the last row, R4. So R4 will be, this will be 21 minus 21, and this is 0, so this is 0, and 0 is matching as 0. So yeah, this is totally matching, and lambda equals to 3. So option D also will be correct. Option D also will be correct. So D is also correct. So A, C, D, all these three options are absolutely correct for this particular question. Okay. Okay, so yeah, let's now solve the next question. This is the next one. What they're telling us is, we have these two matrices. Determinant of A and B are denoted. Which of the following are true? So if I observe one thing, right, is that this row and this row are swapped, correct? Other things are same. Only row 2 and, sorry, not row 2, row 1 and row 3 are swapped. And if I swap a row, what happens? Then the determinant sign changes. So determinant of B, right, determinant of B, right, will be minus of determinant of A. That's it. That is it. Nothing else. So which of the following options is true? So it is a single multiple choice. So only option B is correct. That is, determinant of B will be negative of determinant of A. Okay. I think it, okay, I think this was a MSQ. Here they have not mentioned, but I think this was a MSQ. I think so. Because yeah, I have written the answer. Answer is also coming out to be C. So here, right? Okay. One more thing we can do. Like I did not knew whether it was MSQ or MCQ, because here, right, it is only written is here. So it should be is/r properly. So if I like this is telling that determinant of A is 0. Determinant of A is 0. Let me check what is the determinant of A. Okay. What is the determinant of A? Let me check that. Or okay, one, so determinant of AB, right? Determinant of AB will be equals to determinant of A plus determinant of B. Okay, let me first see this thing, that this is nothing. Okay, 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. Determinant of A is 0. So what I can do, right, I can actually, so if, for me to check determinant of A equal to 0, I have to check it. I have to simply make all the this element 0. So let me do it. But I think this was a single choice question. I don't exactly don't remember, but I have to check. So okay, I don't remember. Let me check. Let me check the determinant of A. So this will be 1 2 3 4. Like if it's a single choice question, then your question is done. If it's multi select question, then I have to check for this one as well, right? I am not able to see any dependency, so I have to solve determinant normally. So this will be 4 times this, so this will be subtracted 4, so this will be minus 7, 4, this will be minus 10, 4 times is minus 10, this will be 4 times this, four times 16, 3 minus 13, this is 3 times, so this will be 0, 3 times this minus 2, 3 times this minus 8, 3 times this minus 10, right? This is 2 times this minus 1, 2 times this minus 2, minus 8. So not minus 8, sorry, minus 7. So this will be okay, to find out the determinant of this matrix, right? Okay, so this will be 1 into determinant of this matrix. How will I find out the determinant of this particular matrix? Minus 7, minus 7, minus 13. Minus 2, minus 8, minus 10, minus 1, minus 2, minus 7. So what I can do is, again I can perform few row operations. So what I can do is I can multiply by 2 and then subtract from this row. So this will become 0, this will be minus 1, minus 2, minus 7. If I multiply by 2 and then subtract, this will be minus 4. If I multiply by 2 and then subtract, this will be plus 4. If I multiply by 7 and then subtract, this will be 0. If I multiply by 7 and then subtract, this will be plus 4. Multiply by 7, that is minus 49, and then subtract, so this will be 36. Okay, so the determinant is coming out to be minus 1 into 4 into 4, that is 16, plus 4 into 36. So this will be basically minus 4 into 40, not 40, sorry, minus 4 into 16 plus 36, that is 52, right? Yes, 52. So it will be minus 210. So minus 210 will be the determinant, which is coming out to be non-zero. Am I doing this everything correctly? Okay. Just give me 4 into 4, that is 16. Oh, sorry. So 4 into 4, right? This is also 4 into 4. So if I take 4 common, this will be 36 plus 4, that is 40. So this will come out to be minus 160. So determinant is coming out to minus 160, which is non-zero. So determinant of A is definitely non-zero. Okay, determinant of A is not equal to B. Determinant of AB will not be simply determinant of A plus determinant of B. No, because it will be minus 160 into minus 160. That is something else. Actually, this was MCQ, but I don't remember. Maybe some other options were also there. But yeah, if this was MCQ, right, only option B will be correct. I guess this was MCQ. I just wanted to calculate determinant of B. If some other, if it was MSQ, right, what could have happened here? That they could have written this option as well. The determinant of A, B will be equals to minus of determinant of A square. Without calculating the determinant, right, you can solve it still. Okay, so let's solve the next question. Let A be n cross n matrix over set of all real numbers. Okay, it is n cross n matrix of set of all real numbers. Let B be a matrix obtained from A by swapping the two rows. Which of the following statements is or are correct? So this is like the same question only, like they repeated the question again. Okay, so this was a 2024, 2023, and they repeated the same concept. So determinant of B will be negative of determinant of A, definitely. Okay, but it is a MSQ, right? If A is invertible, B also will be invertible. Yes, because if A is invertible, its determinant is non-zero, then obviously determinant of B also will be non-zero, but it will be negative, but it will also be non-zero. So this statement is true. If A is symmetric, B also will be symmetric. Now this one, let us take an example. Let me take a symmetric matrix, that is 1 2 2 1. Now if I swap the let me not keep the diagonal elements same, let me change the diagonal elements, then only this will, you will feel the difference. So if I swap the rows, right, this will be 2 3, this will be 1 2. So what you are observing is, yeah, it is not a symmetric matrix, right? Again you can take, I think you can take same elements as well. Let me take another example, 1 2 2 1. If I swap it, right, what will happen? Actually this will be symmetric, I guess. Yeah, 1 2 1 2, this will be symmetric. If the diagonal elements are same, then this will be symmetric. If the diagonal elements are not same, right, then it will not be symmetric. So no. If A is symmetric, B is also symmetric? No. Incorrect. False. If trace of A is 0, then the trace of B also will be 0. Again false, because the trace depends on the diagonal elements, and if I am swapping the row, the diagonal elements are changing. Okay, here although the trace is same, I can choose a different number, right? I can choose a different number, 1 3 2 7 3 7, right? Or I can choose any matrix, any random matrix. Okay, if I am swapping the rows, right, what will happen? B will be 4 7, this will be 1 3. What is the trace here? 8. What is the trace here? 7. So no, diagonal elements are changing, right? So of course if diagonal elements are changing, trace will not be same. So option D is also wrong. Only option A and B will be my correct answer for this particular question. Let's solve the next question. So let A this be matrix, then which of the following is A raised to power 8? So there are many ways to solve A raised to power 8. You can verify by the trace concept, right? Trace concept, or by the determinant. So what are the eigenvalues of this particular matrix? The eigenvalues of this particular matrix, right, will be, if I write down the characteristics equation, this will be lambda square minus of trace of A, trace is 0, plus determinant, sorry, plus determinant of A, determinant of A is minus 1 minus 4, so minus of 5 equal to 0. So lambda is plus minus under root of 5. Okay, so what will be the lambda of A raised to power 8? It will be lambda raised to power 8, right? And lambda raised to power 8 will be what? Actually it will be same, right? If I take it to the power of 8, right, this signs will become all plus. So this is 5 raised to power half, it will be 5 raised to power 4. So it will become 5 raised to power 4 comma 5 raised to power 4, because both the solutions will be plus only. Negative of minus 1 raised to power 8 and 1 raised to power 8, both are plus 1. Okay, so 5 raised to power 4 is nothing but 5 cube is 125, it will be 625 625. So the eigenvalues will be 625 625. I can see only option C has the eigenvalue 625 625. Or you can simply compute, you can find out A square, then again you can square it, right? You can multiply A square, again you will find out A raised to power 4, again you can multiply A raised to power 4, from there you can calculate, but simply you will get the answer will be C. You can check the trace will be this 1250, here also the trace is 1250. You can check the determinant, it will be 625 whole square. Okay, any way you can check, simply the answer will be option C. Option C will be the correct answer. Let's solve this next one. So here I have this question, let L, M and N be all non-singular matrices of order 3 satisfying the equations this L square, M equals to this, N equals to this. Which of the following is the value of determinant of M minus L? Determinant of M minus L, right? So what is my M? M is L raised to power 8. What is my N? N is L square. Okay, so I can do one thing, I can take L square to be common, so this will be L raised to power 6 minus I have to find out the determinant of this, right? The determinant of this will be determinant of L square into determinant of L raised to power 6 minus I. Okay, so what is the determinant of L square? So I can see from here, determinant of L square is 1 by determinant of L, right? It is L inverse. Determinant of L square is 1 by determinant of L. Okay. Okay. And one more thing I can comment. What can I comment? I can comment that my, if I multiply here L on both sides, if I multiply L on both sides, this will be L cube will be equals to L inverse into L, that is I. So L cube is I. If I now square, right, if I now square this, this will be I square, which is simply L raised to power 6 is also I. So L raised to power 6 is I. So I can replace my L raised to power 6 with I here, right? So this will become L square determinant into I minus I determinant, which is basically L square into determinant of null matrix, which is 0. So it will come out to be 0. So 0 will be your answer. Simply 0 will be your answer. There are many ways to solve this. Like you can solve it, you can solve the equation any way you like. Ultimately, you will reach the answer as 0. Okay. Let's now solve this last one. This is the last one. Consider the given system of linear equation x and y, where k is a real valued constant. Which of the following options is /r correct? There is exactly one value of k for which the above system of the equations has no solution. Okay. There exists infinite, exactly one. So they are basically asking me regarding the solutions. So what I can do is, first of all, I can check, I can find out the rank of A. So right, for finding out the rank of A, what I can do is I can calculate the determinant. So if I check the determinant of this matrix, determinant of A, right, coefficient matrix, it is coming out to be 1. So like the matrix is this, right? A matrix is 1, 1k, k, 1, 1k, k1, okay, and matrix B is 1 minus 1, okay. So if I find out the determinant of A, right, it is coming out to be 1 minus k square. So if I want my rank of A and rank of B to be not equal, right, what I can do is I can equate this equal to 0. I can equate this equal to 0, right? If I equate this equal to 0, k value is coming out to be plus minus 1. So when k value is minus 1, right? So my row 1 and row 2 is negative of each other. So this also, like what, okay, let me not do this. Yeah, here I get two values of k. Let me, k equals to plus minus 1. Let me now form the augmented matrix. So if I form the augmented matrix, this will be 1k, k, 1 minus 1. So if k is equals to 1, rank of A, if k equals to 1, okay, let me put it the values of k, then I will explain. If k is 1, that means this will be all ones, right? So rank of A is 2. No, rank of A is 1, right? Rank of A is 1, but rank of A colon B, if you see, it is 2, because here there is no linear relationship between row 1 and row 2, including both A and B, right? But if k is minus 1, if k is minus 1, then we get a relation. This will be 1 minus 1 minus 1 1, this will be 1 minus 1. So what do I observe? I observe that my, like, rank of A is definitely 1 and rank of A colon B is also 1. It is not 2 anymore, because I can directly see that row 1 is negative of row 2. So definitely both are same. So for one value of k, there is no solution. That is when my rank of A and rank of A colon B is not equal. So this option is actually correct. There is exactly one value of k for which the above system of equation has no solution. So option A is definitely correct. Okay, option A is definitely correct. There exists an infinite number of values of k for which the system has no solution. No, there does not exist infinite values of k. There exists exactly one value of k, that is k equals to minus 1. There exists one value of k for which the system has exactly one solution. One solution. No, there can exist infinite values of k for which the system will have one solution. That is, if I choose here k equals to 3, right, then there will be no dependency between this row and this row, correct? There will be no dependency. If I choose my k, like you can see, then the rank will be, then the rank will not be equals to 1, rank will be 2, and rank of A colon B also will be 2. Okay, if I choose k equal to 4, then also there the rank of A will be 2, rank of A colon B also will be 2. It is a full rank matrix, so I will have unique solution. So no, this option is incorrect. There exists exactly one value of K for which system of equations has exactly one solution. No, there exist infinite values of K for which the system of equation has one solution, that is unique solution. Last option, there exists exactly one value of K for which the system of equations has an infinite number of solutions. Yes, this is correct. What is that value? That value is K equals to 1. When K equals to, not K equal to 1, sorry, K equals to minus 1. When K equals to minus 1, right, my row 1 and row 2 are opposite of each other. I am sorry if previously I told you that this condition is for K equals to minus 1. No, this condition is for K equals to 1, where my rank of A is less than my rank of A colon B, and when they are not equal, that means there is no solution. So for K equal to 1, I will have no solution. For K equal to plus 1, I see, sorry, K equal to minus 1, I see rank of A is same as rank of A colon B, and it is less than the number of variables. Number of variables is 2, because it is a 2 cross 2 matrix, right? 2 variables I have. So definitely I will have infinite solutions for exactly one value of K, that is K equals to minus 1. So yeah, option D is also correct. For exactly one value of K, I will get infinite number of solutions. So with this whole video, I hope now every single point of linear algebra is cleared. I am able to install some confidence in you, right? I'm able to put some confidence in you regarding linear algebra. So if you are confident in linear algebra, tell me in the comments below you're confident. Make sure to hit the like button, and of course I will bring other R-PYQ videos as well. So if you are enjoying this content, so just the same thing, just like this video, share this video. Thank you, and I will meet you in the next lecture. Until then, happy learning.